Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So people, just let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Let me know in the chats quickly if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly, let me know in the chats. Quickly, let me know in the chats if all of you can hear me, if I am perfectly audible, visible to every one of you. Good evening, people, good evening and welcome back. So what's up, how are you all doing? Perfect. So my dear students, as you all must be knowing, today we are going to cover one of the most important chapters of your chemistry. And you already know the name of the chapter, right? It is going to be electrochemistry. Yeah. One of the most important chapters from which every year almost like 3-4 questions, including redox, right? They are asked. So today we shall be covering this particular chapter, that is the electrochemistry, in detail from the basics, from the scratch. Whether if you have studied the chapter before or not, does not matter. I'll be starting exactly from the basics, from the scratch. I'll try to cover all the concepts which can be asked from the chapter. I'll try to cover all the problem patterns from the electrochemistry chapter which can be asked in the upcoming NEET examination or even the JEE Mains examination. Yeah? So are you all ready? Are you all ready, people? Are you all ready? Let me know in the chats quickly. Well, session duration, I have no idea what is going to be the session duration, right? Till we complete this chapter in detail, I'll be here in front of you, okay? And I'm pretty much sure all of you will be with me till the end. So are you all ready for that? Are you all ready to be with me till the end? I would want this in the chats quickly. I would want it in the chats quickly. Are you all ready, people? Yeah? Okay, before starting the session, one question I'll ask you in the chats. Okay, you are going to answer me. Have you studied this particular chapter before? Just say yes or no in the chats, quick. Have you studied this chapter before? I just want to know that. I just want to know whether you have studied this particular chapter before or not. Let me know in the chats. Let me know in the chats, people. Have you studied this particular chapter before? Till then, I'll fix certain things. Is that? So again, I'm telling you the same thing, whether you have studied the chapter before or not, it does not matter because I'll be exactly starting from the basics only. You need not to worry about anything. And let me tell you the handwritten PDF of this particular session I'll be sharing on my Telegram. And I'm pretty much sure you all are already part of it, right? Which is Wassim Bhat Chemistry Official. If you're not the part of my Telegram yet, you guys can join the Telegram channel as soon as possible because after every session, I keep on sharing the session PDF, number one. Number two, I keep on sharing the DPP of every chapter which I complete over here. For example, today I'm completing electrochemistry. Tomorrow morning, I'll be sharing a DPP of electrochemistry with you, which you guys will be solving on your own. And I'm pretty much sure if you will be watching this particular session completely, from start till the end, let me tell you, my dear students, you will be in a position to solve each and every question from the chapter electrochemistry for sure, provided you remain with me till the end. Okay? So should we start? All ready? All ready, people? Quick in the chats. Exactly. Be the part of Telegram as soon as possible. The name of the Telegram channel is Wassim Bhat Chemistry Official. Okay? Perfect, guys. Perfect, perfect. I'll be starting from the basics only. Don't worry. Don't worry. I'll be starting from the basics. Perfect, guys. So let's get going then. Let's get started. And the ones who have not liked the session yet, I would want every one of you to smash the like right now. Do share this particular video with everyone. Whosoever is preparing for NEET 2025, right? Or even JEE examination, this particular session is for every single one. And the ones who have not subscribed to the channel yet, I would want every one of you to subscribe to the channel as well, right? And my dear students, I would say every entire chapter will be completely handwritten today, okay? Entire chapter is going to be handwritten. Perfect. I'll be writing here with you and you'll be also making the notes with me too. Perfect. All right then. So let's get going. Let's get started with the chapter Electrochemistry. So my dear students, the first topic which we are going to cover today, what is it going to be? It is going to be electrochemical cell. Electrochemical cell. So first of all, how do we define the term electrochemical cell? What electrochemical cell exactly is all about? Let me first of all write its definition and slowly you'll understand all the things which I'll be writing on the screen. Well, if I talk about the electrochemical cell, let me tell you, electrochemical cell is nothing but it is the device. It is the device that converts. The device that converts either chemical energy, the device that converts either chemical energy into the electrical energy, either chemical energy into the electrical energy, or vice versa. Any such device, any such cell that can convert chemical energy into the electrical energy or electrical energy into the chemical energy. What do we call that device as? My dear students, we will be calling that particular device as the electrochemical cell, right? So, any such device that converts either chemical energy into electrical or electrical energy into chemical energy, we shall be calling that particular cell as the electrochemical cell. Point number one. Point number two, my dear students, this electrochemical cell, I'm going to classify this into two parts. Basically, I'll be classifying it into two sections here. One is called as the galvanic cell, or you call this as the voltaic cell. Galvanic cell or the voltaic cell. Number two, that is going to be your electrolytic cell. That is going to be your electrolytic cell. So, electrochemical cell I classified into two parts here. One is going to be your galvanic or voltaic cell. Another one is going to be your electrolytic cell. Well, these are the two cells which we have to discuss in detail in this particular chapter. But before discussing these cells in detail, there are few points which I would want to write over here, right? I will just give you the overview of these two cells and then I'll be teaching you these cells in detail, right? First, few important things. See guys, galvanic cell is basically that electrochemical cell which converts chemical energy into the electrical energy. Galvanic cell is basically that particular electrochemical cell which is going to convert chemical energy into the electrical energy. Point number one. Point number two. My dear students, when I'll be teaching you these galvanic cells in detail, you'll find out one thing. What is that? You will see some reactions which I call as cell reactions. Cell reactions will be spontaneously taking place. cell reactions will be spontaneously taking place. In case of galvanic cells, the cell reactions are spontaneous. In few minutes, when I'll be teaching you the galvanic cell in detail, you'll observe one thing. You'll observe in galvanic cells, the cell reactions will be spontaneously. On their own, they'll be taking place, right? And you must be familiar about the fact, any process that is spontaneous, right? Any process that is spontaneous, its delta G at constant pressure and temperature is taken to be negative, right? Since in case of galvanic cells, we'll observe one thing. In case of galvanic cells, we'll observe cell reactions taking place spontaneously. So remember, delta G reaction over here, in case of galvanic cells, it is going to be negative. Okay. Next point, my dear students. In case of galvanic cells, I'll be using two electrodes. One I'll be calling as anode, another one I'll be calling as cathode. In case of galvanic cells, I'll be using these two electrodes. One I'll be calling as anode, another one I'll be calling as cathode. My dear students, you'll observe one thing in case of your galvanic cells. You will observe the rod of anode carries the negative charge and the rod of cathode carries the positive charge. Why rod of anode carries negative, rod of cathode carries positive? That is also something which will be discussed in some time. But right now, remember it, right? In case of your galvanic cells, I'll be using two electrodes. One is called as anode, one is called as cathode. My dear students, at anode, always oxidation takes place. And at cathode, always the reduction takes place. And you must be familiar about the fact, oxidation means loss of electrons and reduction means gain of electrons. Well, these are the few points which I would want you guys to remember for now. Okay? Electrochemical cell. It is that device that converts either chemical into electrical or electrical into chemical. Now we have got two types of electrochemical cells here. One is called as galvanic cell. What is the galvanic cell? Galvanic cell is that electrochemical cell which converts chemical energy into electrical energy. In this galvanic cell, you will observe one thing, that cell reactions will happen on its own. They'll be spontaneous. And any process which is spontaneous, for that process, delta G of the system at constant pressure temperature, that is taken to be negative. So delta G for the reactions will be negative here. Okay. In this particular cell, I'll be using two electrodes. One is called as anode, one is called as cathode. The rod of the anode here carries the negative charge. The rod of the cathode here carries the positive charge, right? Okay. At anode, oxidation takes place. At cathode, reduction takes place. Oxidation involves loss of electrons. Reduction involves gain of electrons. So these are few things which I would want you guys to remember for now. Okay. Similarly, I'll be discussing all of this in detail in some time. But before that, let's have an eye on the electrolytic cell as well. Well, my dear students, what electrolytic cell is going to do? I would say it is going to convert electrical energy into what? Into chemical energy. Electrical energy into what? Into chemical energy. Number one. Number two, in case of electrolytic cells, cell reactions, they do not happen on its own. In case of electrolytic cells, the cell reactions, they won't be taking place on their own. Okay, so I would say the cell reactions here are non-spontaneous. The cell reactions here are non-spontaneous. The cell reactions, they do not take place on their own. Let me tell you, in electrolytic cells, cell reactions are carried out. Cell reactions are carried out. Cell reactions are carried out with the help of external battery. With the help of external battery. So I would say in case of your electrolytic cell, cell reactions, they do not take place on their own. These cell reactions, they are non-spontaneous. They do not happen on their own. So in case of the electrolytic cells, cell reactions are carried out with the help of an external agent. Cell reactions are carried out with the help of the external agent. That's your battery. That's your battery. Okay. So I would say in case of your electrolytic cells, since the cell reactions are non-spontaneous, so delta G for the reactions will be positive in this particular case. And my dear students, at the same time, two things which I will tell you here also. In this particular cell, again, I'll be using two electrodes. One is going to be your anode and one is going to be your cathode. And you know, in the electrolytic cell, you'll observe one thing. The rod of the anode carries positive charge. Rod of the cathode carries the negative charge. Rest everything is same. At anode, oxidation will be taking place. Oxidation will be taking place. At cathode, reduction will be taking place. And rest, everything is same. Oxidation involves loss of electrons and reduction involves the gain of electrons. Well, these are few points which I would want every one of you to remember from now onwards. Okay? So people, these are the cells which we have to discuss in detail in this particular chapter. One is going to be your galvanic cell, which is what you call as voltaic cell. Another one is going to be your electrolytic cell. Okay? Now, my dear students, before getting into the details of these cells, before understanding each and every point in detail, right, there are again few things which I would want you guys to remember. What is that? First of all, if I ask you how electrode is formed, how do we make the electrode? How do we make the electrode? Understand, people. For example, I have to make a zinc electrode. Let's say I need to make a zinc electrode. Let me show you how the electrode is formed first of all. Let's say I need to make the zinc electrode. Well, in order to make the zinc electrode, what exactly I'm going to do? I will be taking a container over here. Imagine this is the container. And in this particular container, my dear students, I'm going to keep a salt of zinc. I'm going to keep a salt of zinc. For example, in this particular container, I'm keeping zinc sulfate. Let's say I have kept the salt of zinc in the container. Now, the zinc sulfate which I have introduced in the container, I would say this zinc sulfate would have dissociated into its ions. Its ions are zinc dipositives and SO4 dinegatives. So I would say in this container right now, there are equal number of cations and anions present. There are equal number of cations and anions present. Now, my dear students, what exactly am I going to do after this? After this, I'll be introducing a rod. Which rod it's going to be? It's going to be a zinc rod. I have introduced a zinc rod which is made up of zinc atoms. I have introduced zinc rod in this particular solution. Okay? People, do you see one thing? Do you see I have introduced zinc rod into the solution containing zinc ions? Yes. I have introduced zinc rod into the solution containing zinc ions. So let me tell you, this complete setup over here, I'll be calling as electrode. This complete setup over here, I'll be calling as electrode. For example, let's say I need to make the copper electrode. How do I make the copper electrode? So first of all, I'll be taking a container. Imagine this is a container over here. And in this particular container, for example, I'm keeping a salt of copper. Let's say I'm keeping copper sulfate. Now this copper sulfate in the container, I must say, it would have dissociated into its ions, and its ions are copper dipositives and SO4 dinegatives. Yes. So people, what exactly am I going to do over here? I am going to introduce a copper rod over here in this particular solution. So, do you see one thing? I have introduced copper rod into the solution containing its own ions. Yes, I have introduced a copper rod into a solution containing its own ions. So this complete setup over here, I'll be calling as the copper electrode, right? Similarly, my dear students, for example, I have to make hydrogen electrode. Let's say I need to make the hydrogen electrode. Well, the actual construction of hydrogen electrode, I shall be discussing in some time. But right now, few things, let me tell you over here only. Well, in order to make the hydrogen electrode, what do I need? I need one hydrogen rod. Or leave the hydrogen rod aside. In order to make the hydrogen electrode, first of all, I'll be taking a container. And imagine this container contains, let's say, I'm keeping HCl into this particular container. If I have kept HCl into this particular container, I must say this HCl would have dissociated into H positive ions and Cl negative ions. So in this particular container, what you will observe, you will have H positives and Cl negatives present, right? Now, what is the next thing? I have to introduce hydrogen rod over here in this particular container. I have to introduce hydrogen rod in this particular container. How do we make the hydrogen rod? We make the hydrogen rod with the help of platinum. Imagine this is one platinum rod. Imagine this is the platinum rod. Okay? Imagine this is the platinum rod. Perfect. Now, my dear students, hydrogen rod is made with the help of this particular platinum rod. So first of all, I'll be taking a platinum rod. Perfect. Now what you will observe, if you keep hydrogen gas in the vicinity of platinum, I would say hydrogen gas would get adsorbed on its surface. Hydrogen gas would get adsorbed on its surface. Now, imagine the entire surface of platinum is covered by hydrogen gas. My dear students, if entire surface of platinum, imagine this was the platinum rod, right? Imagine its entire surface is now covered with the hydrogen gas, right? So, does it look like a platinum rod to me, or it looks like a hydrogen rod to me now? I say it looks like a hydrogen rod to me now. Perfect. Now this hydrogen rod I'll be introducing here in this particular container. So in this particular container, I have introduced a hydrogen rod. Perfect. Well, its exact construction of actual hydrogen electrode, I'll be showing in some time, right? Over here, you can remember it like this. Perfect. So this is your hydrogen rod, which we have introduced in a solution containing its own ions. So I'll be calling this whole setup over here as hydrogen electrode, right? As simple as that. Yes? Right, people? It's as simple as that. Well, instead of platinum, you can take graphite as well. Instead of platinum, you can take graphite rod as well. Now, people, we are going to get into the actual stuff. So till now, whatever I was teaching you, this was some basics required to start the chapter. Now we are going to start the chapter. Yeah? Is every single thing clear till here? Is every single thing clear till here, people? Just let me know in the chats quick. Perfect. Now, my dear students, the first topic which we are going to cover here, what is that? That is going to be our Daniell cell. Well, my dear students, if you talk about the Daniell cell, let me tell you, Daniell cell is the most typical example of what? It is the most typical example of the galvanic cell. This Daniell cell, it is the most typical example of the galvanic cell. And we already know what the galvanic cell does. Galvanic cell converts chemical energy into the electrical energy. Galvanic cell converts chemical energy into the electrical energy. So now we are going to understand how this galvanic cell, whose most common example is the Daniell cell, how it is going to convert chemical energy into the electrical energy. Now we have to understand that in detail. Yes? So my dear students, understand few things. First of all, in case of Daniell cell, I'll be using two electrodes. One is going to be your zinc electrode and one is going to be your copper electrode. I'll be using two electrodes in case of the Daniell cell. One is going to be your zinc electrode, one is going to be your copper electrode. Now, my dear students, if you compare zinc with copper, let me tell you, zinc is considered to be more electropositive than copper. Zinc is considered to be more electropositive than copper. Well, people, if zinc is more electropositive, so zinc will have more tendency to lose electrons. Zinc will have more tendency to lose electrons. And loss of electrons is something which we call as oxidation. So basically, the two electrodes which I'll be using in the Daniell cell, out of the two electrodes at zinc electrode, what is going to happen? I must say, oxidation is going to take place. If oxidation is taking place at one electrode, on another electrode, what you will see? You will see reduction taking place at another electrode, right? And you already know oxidation involves loss of electrons and reduction involves gain of electrons. Reduction involves gain of electrons. Okay, so first thing, in case of your Daniell cell, which is the most common example of the galvanic cell, I'll be using two electrodes. One is going to be your zinc electrode and one is going to be your copper electrode. Perfect. Zinc electrode will be behaving like the anode, right, at which oxidation will take place. Copper electrode is going to behave like the cathode, at which reduction will take place. I have told you already, oxidation takes place at anode and reduction takes place at cathode. So one thing which you are going to remember from now onwards, when I talk about the Daniell cell, zinc electrode behaves like the anode and copper electrode, it's going to behave like the cathode. Okay. Now people, let's try to understand this in the detailed form. Understand properly what exactly I'm going to say. My dear students, for example, here You have taken a container. Imagine this is the container. In this container, let's assume that we are keeping zinc sulfate. Imagine I have kept zinc sulfate in this particular container. The zinc sulfate which I have taken into the container, I would say it would have got converted into its ions, and its ions are zinc dipositives and SO4 dinegatives, right? The zinc sulfate which I have taken into the container, it has got converted into its ions. I would say this solution right now, it is containing equal number of cations and anions. The solution right now, it is containing equal number of cations and anions. Therefore, this particular solution which I have taken in the container, my dear students, this particular solution right now, it is electrically neutral. It is electrically neutral. I have taken zinc sulfate into the container, and this zinc sulfate has dissociated into its ions. This particular solution right now contains equal number of cations and anions, due to which I must say this solution right now, it is electrically neutral. Yes. Now, my dear students, in this particular container, I'm introducing a rod, right? This is a zinc rod which I have introduced into this particular container. So do you see how introduced zinc rod into the solution containing its own ions? Yes, I've introduced zinc rod into the solution containing its own ions. So I'll be calling this particular setup over here as electrode. Which electrode this is? This is the zinc electrode. Number one. Number two. My dear students, over here I'm taking one more container. Over here I'm taking one more container. And in this second container, imagine that I'm taking copper sulfate. Imagine that I'm taking copper sulfate in this particular container. Now, the copper sulfate which I've taken into the container, I would say this copper sulfate would have dissociated into copper dipositives and SO4 dinegatives. So I must say this particular solution in which I have kept copper sulfate, I must say this particular solution right now contains equal number of cations and anions, due to which this particular solution right now is again electrically neutral, right? So I've taken copper sulfate, which has dissociated equally into their ions, into its cations and anions. So I believe this particular solution right now is electrically neutral. Now, inside this copper sulfate solution, imagine that I'm introducing a rod. This is the rod which I've introduced, and this is the copper rod which I've introduced into this particular container. So people, do you see one thing? I've introduced copper rod into the solution containing its own ions. Yes. So I'll be calling this particular setup over here again as the electrode. So over here I've taken two electrodes. One is your copper electrode and one is your zinc electrode. Perfect. Now people, these two electrodes, externally I'm connecting them with the help of ammeter. Externally I'm connecting them with the help of ammeter, which is going to measure the current. Okay. So externally I've connected them. Internally also I'll be connecting these two solutions. Internally also I'll be connecting these two solutions with the help of an inverted U-type tube. And my dear students, this inverted U-type tube which I've used over here, what is present in this inverted U-type tube? Let me tell you people, in this inverted U-type tube, what do we exactly keep? We keep the inert electrolyte. We keep the inert electrolyte like you have got KCl. It is one of the examples of the inert electrolyte. Okay. Let's say we have got NH4NO3. This is one more example of inert electrolyte. Perfect. So, in short, the inverted U-type tube which I've taken over here, in this particular inverted U-type tube, I'm keeping the inert electrolyte which is mixed with gelatin, or agar-agar. And let me tell you, when inert electrolyte is mixed with gelatin or agar-agar, what do we exactly get? We get a jelly-like paste. We get a jelly-like paste containing the ions of the inert electrolyte. We got a jelly-like paste. And this jelly-like paste is basically introduced here. So in this inverted U-type tube, what do we have? We have got a jelly-like paste over here. And this jelly-like paste, it contains ions as well, right? Imagine you have mixed KCl with gelatin. If you have mixed KCl with gelatin, you would have got a jelly-like paste, and that jelly-like paste would be containing Cl negatives as well as K positives. So in this inverted U-type tube, we have got a jelly-like paste containing anions and cations. My dear students, the ends of this, let me tell you, the ends of the inverted U-type tube, I'm closing the ends with the help of cotton balls. I've closed the ends with the help of cotton balls. Now, this inverted U-type tube in which we have kept the inert electrolyte which is mixed with gelatin or agar-agar, right? This inverted U-type tube is something which we call as salt bridge. This is something which you call as salt bridge. What is the function of the salt bridge? That is something we'll discuss afterwards. So this inverted U-type tube is something which we call as salt bridge, right? Now people, just understand some things. See, if I ask you whether this circuit is complete, whether it's closed or open, I would say the circuit is complete, the circuit is closed. The circuit is closed. Externally also, internally also. If the circuit is closed, what is going to happen? I told you already, the zinc electrode, it behaves like what? The zinc electrode, it behaves like the anode. And the copper electrode, it behaves like the cathode. And my dear students, you know it, at anode, oxidation is going to take place, and at cathode, I would say reduction is going to take place. I would say reduction is going to take place. And you know, oxidation involves loss of electrons. And similarly, I would say reduction involves the gain of electrons. The gain of electrons. So, what is going to happen over here now? My dear students, since the cell is complete, the circuit is closed. So, what is going to happen? At anode, oxidation is going to take place. At anode, oxidation is going to take place. Oxidation means loss of electrons. At anode, oxidation is going to take place. Oxidation involves loss of electrons. So, I would say something like this. This zinc rod, which is made up of zinc atoms, those zinc atoms of which rod is made up of, those zinc atoms will undergo oxidation, right? For example, over here, I'm showing the zinc atom over here, which is present on the rod, right? Of which the rod is made up of. The zinc atom will undergo oxidation. And after getting oxidized, it will get converted into zinc dipositives. And with this, we'll be getting 2 electrons. The rod was made up of zinc atoms. Those zinc atoms will undergo oxidation, will start getting converted into zinc dipositives. And with that, you'll be getting 2 electrons. My dear students, since the zinc atom has undergone oxidation, it has got converted into zinc dipositive. I would say that zinc dipositive is going to enter into the solution over here. The extra zinc dipositive, which is coming from the rod, that's going to go into the solution. I told you in the beginning, initially this solution was electrically neutral. Now extra zinc dipositive is getting inside this container. So I'll say this particular solution will start to acquire positive charge. And these two electrons over here, I would say these 2 electrons will get accumulated on the rod. Similarly, my dear students, when one more zinc atom from the rod will undergo oxidation, will get converted into zinc dipositive, that zinc dipositive will go into the solution again. I would say 2 more electrons are accumulated on the rod. Can I say continuously electrons will keep on accumulating on the rod due to the oxidation of zinc atoms of the rod? Yes. Now people, look here carefully. On the rod, there are electrons. Electrons carry negative charge. So I will say this particular rod right now, it carries which charge? The rod carries a negative charge due to the presence of electrons on it. Yes, which I told you already. The anodic rod, in case of your galvanic cell, in case of your Daniel cell, it carries a negative charge. So this is something which is happening at anode. Now, what will be happening at cathode? What would be happening at cathode? My dear students, at cathode, reduction takes place. Reduction of what? At cathode, reduction takes place. Reduction of what? See, in this particular solution, if you observe carefully, in this solution, there are copper dipositives and SO4 dinegatives. In this solution, there are copper dipositives and SO4 dinegatives. I would say these copper dipositives which are present in the solution, these copper dipositives are going to collide with the rod. They are going to take 2 electrons out from the rod. So copper dye positives which were present in the solution, they'll take 2 electrons from the rod and they'll get converted into copper solid. And this copper solid will start to deposit on this particular rod. This copper solid will start depositing on this particular rod. Since the copper dye positives which were there in the solution, those copper dye positives collided with the rod. So I would say from the rod, electrons are being snatched. And if from the rod, electrons are being snatched, the rod will acquire which charge? The rod will acquire positive charge, which I told you already. The cathodic rod carries the charge positive. Yes? Right, people? Now, if you look carefully, on this rod, electrons have been accumulated. Perfect. On this rod, positive charge has got developed. So, my dear students, the path is already created. The path is already created. Can I say electrons will start moving in this particular direction? The electrons which were accumulated on the rod, they'll start moving in this particular direction? Yes. Now, if I ask you, is it just the moment of electrons from anode to cathode, or should I be calling this as the directional moment of electrons? I would say this is the directional moment of electrons. This is the moment of electrons in a particular direction, right? And whenever charge flows in a particular direction, what will happen? I would say current will get generated. So can I say this emitter over here will be showing deflection in right now? Yes, this emitter will be showing deflection because over here electrons are moving in the external circuit from anode to cathode. So it is not just the moment of charge, it is the directional moment of charge. And whenever charge moves in a particular direction, a current is generated. Yes, a current is generated. So this emitter over here, it will be showing deflection right now. It is showing that, yes, current is being generated. And my dear students, do you remember what is the use of the galvanic cell? Why do we use the galvanic cell? To convert chemical energy into electrical energy, to produce electric current. Do you see current is being produced here? Yes, current is being produced here. Yes, current is being produced here. Now, the first question which will be asked to you, what is the direction of electrons? What is the direction of electrons? My dear students, I'll say electrons in the external circuit move from anode to cathode, or anode here is your zinc and cathode here is your copper. Perfect. So electrons are flowing from zinc to copper. And you know, whatever is the direction of electrons, opposite to that will be the direction of current. So if I ask you, what is the direction of current in this particular case? So I would say the direction of current in the external circuit is from copper to zinc. Is from copper to zinc. Yes. People, if you observe one more thing, do you see on this rod is undergoing oxidation. This rod was made up of zinc atoms. Those zinc atoms are undergoing oxidation. Those zinc atoms are getting converted into zinc dye positives. And those zinc dye positives are entering into the solution. So from the rod, slowly, one zinc atom is leaving, going into the solution. One zinc atom is leaving, going into the solution. So what do you think? Will the thickness of this particular rod increase with time or decrease with time? What do you think? I would say the thickness of the zinc rod. The thickness of the zinc rod. The thickness of the zinc rod will, I would say, decrease with time. Yes, thickness of the zinc rod will be decreasing with time. If I ask you what will be happening to the thickness of the copper rod, if I ask you what is happening to the thickness of copper rod, my dear students, you know, on the copper rod, copper is being deposited. So I would say the thickness of the copper rod is increasing with time. The thickness of the copper rod is increasing with time. This is one more conclusion, which I believe it's all clear to everyone. Now, people, if you look carefully, since this is my Daniell cell, right? This is my Daniell cell. Now, my dear students, one of the reaction is taking place at anode, one of the reaction is taking place at cathode, right? So in your, in your galvanic cell, one reaction is taking place here, one reaction is taking place here. Now, if I ask you, what would be the net reaction in the Daniell cell? How you guys are going to write the net reaction? In order to write the net reaction, you need to write the reaction at anode first. Then you need to write reaction at cathode first. After that, you're supposed to balance the electrons. And over here in these two reactions, electrons are already balanced. Electrons are already balanced, right? So what you can do, since the electrons are balanced, you can directly add these two reactions. if the electrons were not balanced, then you were supposed to balance the electrons. For example, over here, if there was one electron, then you were supposed to multiply this reaction by 2 first, so that electrons get balanced. But right now, electrons are balanced in both the reactions. So I can directly add these two reactions, add the left-hand side and the right-hand side. When you add them, these two electrons will get cancelled out. The net reaction is going to be zinc solid plus copper dye positive aqueous. It will get converted into zinc dye positive aqueous. And with that, you'll be getting copper solid as well. And people, how many electrons got cancelled here? 2 electrons got cancelled here. What does this mean? It means that N value here is 2. And what does this N indicate? N indicates the number of moles. N indicates the number of moles of electrons exchanged in the net reaction. So 2 moles of electrons are being exchanged in the net reaction. 2 moles of electrons are sent from anode to cathode in the external circuit. I believe every single thing till here is clear to you. If every single thing is clear, let me know once in the chats so that I'll talk about the uses of the salt bridge. Did you understand what that galvanic cell does? Galvanic cell converts your chemical energy into what? It produces current. Perfect, people? All clear? All clear till here? Amazing. Now, people, what is the use of this particular salt bridge? What is the use of this particular salt bridge? Now, over here, the salt bridge is completing the internal circuit. External circuit, we are completing with the help of ammeter. Right here in this particular case, the salt bridge is completing the internal circuit, right? The salt bridge is completing the internal circuit. Now, the first question which I'll ask you, without salt bridge, can the cell work? You might be thinking, no. Without salt bridge, how can cell work? Let me tell you, without salt bridge also, the cell can work. But the cell dies fast. What is the reason? Let's have a look in detail. The first thing, why we are using the salt bridge? Why we are using the salt bridge? My dear students, over here in this particular case, which I took over here, in this particular case, when I took 2 containers, the salt bridge is completing the internal circuit. So you can say, yes, the salt bridge completes the internal circuit. Yes, the salt bridge completes the internal circuit. But that does not mean without salt bridge, cell cannot produce current. That does not mean that. It completes the internal circuit. Number one. Number 2, it maintains the electrical neutrality. It maintains the electrical neutrality of both the solutions. It maintains the electrical neutrality of both the solutions. What is meant by that? What is meant by that? Have a look. Understand. My dear students, initially in this particular container, there were equal number of cations and anions. The solution initially was electrically neutral. What happened after that? Due to oxidation of zinc, extra zinc dye positives came into the solution, due to which the positive charge got developed in the solution, right? In this particular solution. Now look here. Initially, there were equal number of cations and anions in this solution. Initially, there were equal number of cations and anions here. But what happened later on? Reduction took place. Some of the copper dye positives, they collided with the rod, took 2 electrons from the rod, got converted into copper solid. And that copper solid got deposited on the rod, right? So, what is happening in this right container? Can I say Cu dye positives, they are being reduced, getting converted into copper solid, and that copper solid is being deposited here on the rod? Yes. So I would say the number of copper dye positives with time in the container decreased. Initially, there were equal number of cations and anions. Now with time, cations are being reduced, right? So number of cations in the solution would decrease. Anions are still the same. Cations are now decreasing. So effectively, can I say this particular solution is going to get negative charge here? Yes, this particular solution is going to get negative charge here. My dear students, as soon as positive charge gets developed here, as soon as negative charge gets developed here, at the same time, from the salt bridge, K positive is going to come, enter the solution and neutralize this positive charge. Sorry, Cl negative here. I would say as soon as positive charge is developed here, at the same time, Cl negative is going to enter into the solution and will neutralize this particular charge. Similarly, as soon as the negative charge gets developed here, at the same time, K positive will be introduced in the solution and this negative charge will get neutralized. So what is the use of the salt bridge? What the salt bridge is doing here? Salt bridge is neutralizing the charges which were being developed in the solutions due to oxidation and reduction. Right? So I would say the salt bridge, as soon as this particular solution gets positive, at the same time, Cl negative from the salt bridge will come, will neutralize this positive charge. As soon as negative charge gets developed here, at the same time, K positive will enter into the solution, will neutralize the solution. So I must say the salt bridge, what it does exactly, it maintains the electrical neutrality of both the solutions. Right? This was next point. My dear students, the third point. I would say the salt bridge, it avoids the liquid junction potential. It avoids the liquid junction potential. What does that mean? Salt bridge avoiding the liquid junction potential, what does that mean? Understand what exactly I'm going to say. People, over here, if you look carefully, I took two containers. Now, for example, instead of two containers, imagine that I'm just taking one container. Imagine instead of two containers, I'm just taking what? I'm just taking one container, a bigger sized one. Imagine instead of two containers, I'm taking one container, a bigger sized. Now, this particular container which I took over here, imagine I'm dividing the container into two equal parts with the help of a semi-permeable membrane. Imagine I've used SPM over here, semi-permeable membrane over here. Now, the left part of the container, imagine in the left part of the container, I am keeping zinc sulfate. Imagine in the left part, in the left chamber, for example, I am keeping zinc sulfate. The zinc sulfate which I have taken here, imagine the zinc sulfate has got completely dissociated into its ions, and its ions are zinc dipositives, SO4 dinegatives, due to which this particular solution right now is neutral. This particular solution right now is neutral because it contains equal number of cations and anions right now. Okay. Now, my dear students, in the right chamber, imagine you are keeping copper sulfate. Imagine in the right chamber, you are keeping copper sulfate. The copper sulfate which I am keeping in the right chamber, imagine it got dissociated into its ions, and its ions are copper dipositives and SO4 dinegatives. I believe right now in the right chamber, there are equal number of cations and anions, due to which this right chamber is also electrically neutral. So both the solutions which I've taken over here, they are electrically neutral. So what I'll be doing now, let me introduce a zinc rod in this particular container. This is the zinc rod which I've introduced. Similarly, let me introduce a copper rod in this particular container. I've introduced copper rod into this particular container. Now, my dear students, let me connect these rods with the help of ammeter externally. I've connected these rods with the help of ammeter externally. Do you see one thing? Zinc rod is introduced in a solution containing its own ions. So this is my one electrode. Copper rod is introduced in a solution containing its own ions. So this is my second electrode. And these electrodes are connected externally with the help of ammeter. Perfect. Now, internally, both the solutions are in contact. Internally, both these solutions, they are in contact with the help of SPM, with the help of semi-permeable membrane. So, internally, the cell is already completed. The cell is already complete internally. You need not to use the salt bridge to complete the circuit. The circuit already is internally completed because these solutions, they are in direct contact, right? It's a closed loop now. It's a closed loop. Perfect. So this is my galvanic cell right now. This is my Daniel cell. This is my Daniel cell. So, first of all, as I told you in the beginning, if a question is asked without salt bridge, can the cell work? Yes, the cell can work. Yes, the cell can work. Because over here, the solutions, they are in direct contact. Perfect, with the help of SPM. So you need not to use the salt bridge here to complete the internal circuit. Internal circuit is already completed. Internal circuit is already completed. Now, my dear students, Since you have taken two electrodes, they are connected externally, internally. What is going to happen at anode? At anode, oxidation is going to take place. At anode, oxidation is going to take place, right? Now, the zinc rod is made up of zinc atoms. Those zinc atoms will undergo oxidation. They'll get converted into zinc dipositives. Those zinc dipositives, those additional zinc dipositives, they are going to enter into this solution. This solution initially was electrically neutral. Now, due to the presence of extra zinc dipositives, the solution is going to acquire positive charge. Similarly, I would say 2 electrons will be accumulated on the rod, due to which rod gets negative. Similarly, in the cathode, what is going to happen? Reduction. Copper dipositives, they are going to collide with the rod. They are going to take 2 electrons from the rod. So, from the rod, electrons are being snatched. So, rod carries positive. Now, copper dipositives, which are colliding with the rod, they are taking 2 electrons from the rod, getting converted into copper solid. That copper solid is being deposited here. That copper solid is being deposited here, due to which, inside this solution, what is happening to the number of cations? What is happening to the number of copper dipositives? They are decreasing. Due to which, this solution will effectively get which charge? It will effectively get negative charge. Perfect. Positive got developed here, negative got developed here. I would say they would attract, and after attracting, let's say they got accumulated here. Positive, negative. Similarly, when one more zinc dipositive comes here, again positive charge. Similarly, again negative charge, and that positive negative is going to attract. So positive negatives are going to arise here. Positive, negative. Perfect. My dear students, look at the junction. This is your SPM. This is your junction. The left side of the junction is at positive potential. Left side of the junction is at positive potential. Right side of the junction is at negative potential. Do you see at the junction a potential difference getting created? At the junction, I must say, potential difference is getting created. And this potential difference that gets created at the junction, I'll be calling this potential difference as the liquid junction potential. I would be calling this as liquid junction potential. The potential difference that got created here at the junction, I'll be calling it as liquid junction potential. Perfect. So without salt bridge, a new potential difference getting created here. That is the liquid junction potential. Now, imagine if I had used the salt bridge. Imagine if I had used the salt bridge. My dear students, let me tell you. First of all, this potential difference which is getting created here, what I'll be calling it? Liquid junction potential. And due to liquid junction potential, cell is going to die soon. Cell is going to die quickly. Right? Due to the accumulation of this potential difference at the junction, the cell is going to die quickly. The cell is going to discharge quickly. The cell is going to discharge quickly. Now, if I would have used salt bridge, what would have happened? As soon as positive charge would have got developed here, at the same time from the salt bridge, anion would have come, neutralize this charge. As soon as negative charge was established here, from the salt bridge, positive ion would have come and neutralized this. Due to which, there would be, in presence of salt bridge, there would have been no positive and no negative here. If there was no positive, no negative in the solutions, what do you think? Would this potential difference getting created here? Would this potential difference get created here? In presence of salt bridge, this potential difference is not going to get created here. Yes, in presence of salt bridge. Because as soon as this positive gets developed, at the same time, from the salt bridge, anion will come, will neutralize it. As soon as this negative gets developed here, at the same time, from the salt bridge, cation is going to come, neutralize it. There would be no accumulation of positive and negative at the junction. So there'll be no liquid junction potential. So I would say salt bridge, it avoids the liquid junction potential. Without salt bridge, cell can work, but only for a smaller time. Sorry. Without salt bridge, cell can work, but only for a smaller time. But only for a smaller time. Why? Because without salt bridge, this junction potential gets created. In presence of salt bridge, cell works, number one. Number two, the salt bridge does not allow this liquid junction potential to be created over here, due to which cell lasts for the longer time. Right, people? All clear? Now, I believe salt bridge functions are clear to you. Now, people, there is one more thing. In the salt bridge, what did we keep? We kept the inert electrolyte in the salt bridge. We kept inert electrolyte in the salt bridge. If you observe one thing, this is the net reaction. In this net reaction, do you see any ion of the inert electrolyte? In this net reaction, do you see Cl negative or K positive? No. There is no Cl negative or K positive in this particular net reaction. So let me tell you one thing. Which inert electrolyte we are going to use? Let me tell you, people, the main condition for the inert electrolyte to be used here, I must say, the ions of the inert electrolyte. The ions of the inert electrolyte must not participate. The ions of the inert electrolyte must not participate in the net cell reaction. They must not participate in the net cell reaction. Point number one. Point number two. The ionic mobility of cation and anion of the inert electrolyte must be the same. Must be the same. What does that mean? See, over here we have used Cl negative and K positive, right? Their ionic mobility must be the same. That means the speed with which Cl negative enters into the solution, with the same speed, K positive should also enter into the solution, so that there will be no potential difference getting created at the junction. So remember these 2 points as well. I would say the ions of the inert electrolyte, they must not participate in the net cell reaction. At the same time, the ionic mobility, the speed with which the cation and anion enters into the solutions, that speed must be the same. Am I clear with this? Am I clear with this, people? Quickly. If this is clear, then there is one more thing which you must know. What is that? That is effect of external battery. Effect of external battery on the galvanic cell. Effect of external battery on the galvanic cell. This is again one important thing directly given into an NCERT and from which question can be asked easily, right? Effect of external battery on what? On the galvanic cell. But before teaching you this particular stuff, tell me once in the chat, is every single thing clear till here? Quickly, I would want the chats to run like crazy. Is every single thing clear? Quickly. Yes? Perfect. Let's have a look on the effect of external battery now, guys. Let's have a look on the effect of external battery. What the external battery does in case of the galvanic cell. So over here, I'm again making the same setup. Imagine this is your zinc electrode and this is your copper electrode. Imagine this is your zinc rod introduced in zinc sulfate solution and this is your copper rod. This is your copper rod introduced in copper sulfate. So one is your anode, one is your cathode. This you know, this is your anode and this you know, this is your cathode. Perfect. And how do you connect them externally? I mean, you connect them with the help of emitter. This is the emitter which I'm using here. And in this particular case, I'm using the salt bridge here. So this is your galvanic cell. This is your Daniell cell. This is your Daniell cell, right? This is your Daniell cell. Now, my dear students, something which we all know. Since the circuit is closed, what will be happening? The movement of electrons will be taking place from anode to cathode. The direction of current will be from cathode to anode, right? Direction of current will be from cathode to anode in the external circuit. Now, my dear students, this particular rod, you know, we have discussed it carries negative and this particular rod will be carrying positive. Perfect. Now, what I'm doing over here? My dear students, imagine I'm taking an external battery over here. Let's say this is the positive terminal of the battery. This is the negative terminal. Positive terminal, negative terminal of the external battery. This external battery over here, I'm taking this external battery over here, I have taken. Now, my dear students, what exactly am I going to do? Let me tell you, the positively charged rod I'm connecting with, the positively charged rod I'm connecting with the negative terminal of the battery, the negative terminal of the external battery. Similarly, the positively charged terminal, the positive terminal here, I'm connecting with the positive terminal here, I'm connecting with the negatively charged rod. So can I say over here the external battery which I've taken? Can I say I'm connecting this external battery with the cell in reverse polarity? I'm connecting the external battery with the cell in reverse polarity. I'm connecting the positive end with the negatively charged rod. I'm connecting the negative end with the positively charged rod. Yes, with the positively charged rod. Now, my dear students, first of all, what this galvanic cell does, it produces current. Current is produced due to potential difference. Current is produced due to potential difference. So I must say people, between these two electrodes, there must be potential difference due to which current is produced by this cell. And that maximum potential difference in case of your Daniell cell, which I call as E cell, it is 1.1 volt. In case of your Daniell cell, the E cell, the maximum potential difference between the rods, right, which is what I call as E cell, that is 1.1 volt. Now understand. My dear students, the first point. If the voltage of the external battery, is kept less than 1.1 volt, if the voltage of the external battery is kept less than 1.1 volt, at that point of time, the cell is normally going to behave like a galvanic cell, in which oxidation will be taking place, reduction will be taking place, electrons will be moving from zinc to copper. This is the case when external voltage is less than the EMF of the cell. When external voltage is less than the voltage of the cell, right? At that point of time, the cell is normally going to work like a galvanic cell, in which at zinc electrode, oxidation takes place, and at copper electrode, reduction takes place. The direction of electron at that point of time is normal, that is from zinc to copper, and the direction of current at that point of time is from copper to zinc. This is the time when the voltage of the external battery is kept less than 1.1 volt. Okay. Now, people, there comes a case. If I slowly keep on increasing the voltage of this battery, if I slowly keep on increasing voltage of this particular battery, right? What would happen? This particular emitter, which was showing the maximum deflection in the beginning, if I slowly increase the voltage of this particular battery, since the positive terminal is connected with the negative one, the negative is connected with the positive one. So if I slowly increase the voltage of this external battery, the deflection is going to decrease. If I keep on increasing the voltage of external battery, the deflection over here is going to get decreased. And there will be a time when the arrow will be vertical upwards. And that is the time when external voltage would have become equal to the cell voltage, which is 1.1 volt. If external voltage is equal to 1.1 volt, at that point of time, the cell is not going to produce any current. Cell reaction stop. Cell will not produce any current. Cell will not produce any current when the voltage of the external battery becomes equal to the cell voltage. Why is that? Because I have connected the external battery with the cell in reverse polarity. I've attached positive with negative. I've attached negative with positive. Perfect? Right, people? So when the voltage of the external battery will be equal to the potential difference here, will be equal to the cell voltage here, I would say at that point of time, your cell will not produce any current. Cell will not work at that time. The third case. If external voltage is kept greater than 1.1 volt. Now this is the case. If external voltage is kept greater than 1.1 volt, what would be happening? Entire stuff will be reversed. Then at zinc, reduction will take place. At this copper electrode, oxidation will take place. Everything will be reversed. Okay? I would say, if external voltage is kept greater than 1.1 volts, then at that point of time, I would say at zinc, reduction will take place. And at copper, oxidation will take place, due to which the movement of electrons in the external circuit will be from copper to zinc, and the direction of current will be from zinc to copper. So at that point of time, I would say the cell is behaving like the electrolytic cell. At that point of time, the cell The galvanic cell which we took in the beginning, it is going to behave like the electrolytic cell. Is every single thing clear to people? Do you understand why it's happening? Because I'm connecting the external battery with the reverse polarity. I'm attaching positive with negative, negative with positive. Okay? You can remember it like this. You can remember it like this. See, what this positive is, if I keep on increasing the voltage of this battery, if I keep on increasing the voltage of this battery, do you see positive is attached with negative? If I increase the voltage of this battery, what will happen to the magnitude of negative charge here? If I increase the voltage of this battery, the magnitude of negative charge will decrease on this rod, right? Similarly, the magnitude of positive charge on this rod will keep on decreasing. Perfect? Right? Okay, when I keep on increasing the voltage of this battery. And similarly, when the voltage of the external battery becomes equal to 1.1 volts, at that time, the cell will not work. When the voltage of the external battery becomes greater than 1.1 volts, then the positive will dominate here and negative will dominate here. Then entire stuff changes. It reverses. Okay, you can remember it like this. Am I clear? Say yes or no in the chats quick. If this stuff is clear. Right, people? I believe every single thing is clear till here. Now, my dear students, how do we exactly represent the galvanic cells? How do we represent the cells? Representation of the galvanic cell. Representation of the galvanic cell. How do we represent the galvanic cell? What exactly you have to do? I would say nothing. Just two lines in the middle, which are going to represent the salt bridge. Perfect. So this is going to represent your salt bridge. On the left side of the salt bridge, you have to write anode. On the right side of the salt bridge, you have to write the cathode. On the left side of the salt bridge, you have to mention the anode. On the right side of the salt bridge, you have to mention the cathode. That's all. That's all. For example, let's say I have got a galvanic cell in which the net cell reaction is this one. Zinc solid plus copper dye positive aqueous. Let's say it gives your zinc dye positive aqueous plus copper solid. Let's say this is some net cell reaction that is given to me. This is some reaction which is happening in some galvanic cell. Now from this reaction, I have to represent the cell. How exactly I'm going to represent it? Understand. First thing, my dear students, look at the charge on zinc, 0. Look at the charge on copper here, +2. Look at the charge on zinc, +2. Look at the charge on copper, 0. So if I ask you what is happening to the oxidation state of zinc, 0 to +2. 0 to +2. 0 to +2 means increase in the oxidation state. Increase in the oxidation state is something which we call as oxidation. So zinc here is undergoing oxidation. Zinc here is undergoing oxidation. Perfect. Similarly, +2 to 0. Decrease in the oxidation state. Decrease in the oxidation state is something which we call as reduction. So my dear students, I got to know which one is undergoing oxidation, which one is undergoing reduction. Now my dear students, you know, oxidation takes place at anode and reduction takes place at cathode. Oxidation takes place at anode, reduction takes place at cathode. So first of all, if I need to represent it, put the two lines, they are going to represent the salt bridge. On the left side, you are going to write the anode. At anode, oxidation is taking place, right? During oxidation, zinc is getting converted into zinc dye positive. During oxidation, zinc solid is getting converted into zinc dye positive aqueous. Now, my dear students, tell me one thing. Do you see the phase of these two same or different? Phase is different here. This is solid, this is aqueous. When the phase is different, use a single line. When the phase is different, solid, aqueous, phase is different, use a single line. If the phase was same, imagine this was aqueous, then you were not supposed to use the single line here. You are supposed to use comma in between. When phase is different, use a single line. When phase is same, use comma. That's all. Yes? Now, on the right side of the salt bridge, what do you write? You write the cathode. At cathode, reduction takes place. Copper dye positive, getting converted into copper solid. So I would say, at cathode, copper dye positive aqueous is getting converted into copper solid. Is the phase same or different here? I would say phase is different. And when the phase is different, what I'll be using? I'll be using a single line. So this is the representation of the galvanic cell whose net cell reaction was this. Whose net cell reaction was this. I believe this is clear. Let me take few more examples. My dear students, imagine that there was a galvanic cell whose net cell reaction was this one. Now, from the net cell reaction, you have to represent the cell. How exactly? Use the same process. Oxidation state, here is 0. Here it is plus 2. Here it is again plus 2. Here it is 0. Right? Now, what is happening? 0 to plus 2. Increase. Increase in the oxidation state is what we call as oxidation. Oxidation takes place at anode. So, this iron is behaving like the anode. Similarly, plus 2 to 0, decrease in the oxidation state, is what we call as reduction. And this reduction, it takes place at cathode. This reduction takes place at cathode. So you identified your anode and cathode. Since you identified your anode and cathode, what exactly I'll be doing? Use the two lines. So they represent the salt bridge. On the left side, I'll be using anode. At anode, oxidation. Oxidation of what? Fe solid. Fe solid is getting converted into what? Fe solid is getting converted into Fe dye positive aqueous. Is the phase same or different? Phase is different. Use a single line. Now, on the right side, cathode. At cathode, reduction of what? Copper dye positive. So, copper dye positive aqueous is being converted into copper solid. Again, the phase is different. Use a single line. So, this is how you have represent the cell. Done and dusted. Yes? Perfect, people. Look at this particular cell. You have got some cell whose cell reaction is given to us. Now, from the cell reaction, again, you have to represent the cell. How exactly? See, oxidation state 0. Here, charge on hydrogen is plus 1. Charge on zinc is plus 2. Charge on this hydrogen is 0. So, what is happening? 0 to plus 2, increase. Plus 1 to 0, decrease. Increase in the oxidation state is what you call as oxidation, which takes place at anode. Similarly, plus 1 to 0, decrease. Decrease means reduction. And you know, reduction takes place at cathode. So you identified your anode and cathode. After the identification of your anode and cathode, people, these are the two lines which are going to represent the salt bridge. On the left side of the salt bridge, write the anode. At anode, zinc is getting converted into zinc dye positive. So you will say zinc solid getting converted into zinc dye positive aqueous. Now look at the phase. Phase is different. Use a single line. On the right side, cathode. At cathode, H positive is getting converted into H2. So H positive aqueous is getting converted into H2 gas. Is the phase same or different? Phase is different. Aqueous gas. Use a single line. But still, the representation is not complete yet. Because my dear students, no doubt, here you have used a normal electrode. You have taken the zinc rod, introduced zinc rod into zinc ions. You have taken zinc rod, introduced zinc rod into zinc ions. You got the electrode here. Now here, you are making the hydrogen electrode. Can you make hydrogen electrode normally? Like your zinc electrode? No. For the making of hydrogen electrode, we either need to take platinum or graphite, right? So, comma, I'll be writing platinum solid here as well. That means this hydrogen electrode I have made with the help of which rod? With the help of platinum rod. So, in short, remember one thing. Whenever you are unable to make the electrode under normal conditions, right? At that time, you have to use the platinum solid. At that time, you have to use the platinum solid. Electrode under normal condition means, for example, you have to make the copper electrode. You'll be simply taking copper rod, introduce copper rod into the solution of copper, right? You'll be making the copper electrode. Now, if you have to make the hydrogen rod, if you have to make the hydrogen electrode, how exactly? If you have to make the hydrogen electrode, how you'll be doing that? You cannot directly take the hydrogen rod. You have to use platinum for that. You have to use graphite rod, platinum rod for that. That's why I wrote platinum here with it. Okay. For example, this is some cell reaction which is taking place in some cell. Now, after looking at the cell reaction, I have to represent the cell. How exactly I'm going to represent it? So first of all, oxidation state 0, here it is plus 2, here it is plus 1, here it is 0. Look carefully. 0 to plus 1 means increase. Plus 2 to 0 means decrease. Increase is what you call as oxidation. So H2 is undergoing oxidation. So it's going to behave like the anode in this particular case. Similarly, this will be undergoing reduction. And if it is undergoing reduction, it's going to behave like the cathode. So you identified your anode and cathode. After the identification of your anode and cathode, these two lines represent the salt bridge. On the left side, anode. At anode, H2 is getting converted into H positive. So I would say H2 gas is getting converted into H positive aqueous. Perfect. On the right side, you'll be writing the cathode. At cathode, copper dye positive is getting converted into copper solid. So copper dye positive aqueous is getting converted into copper solid. So this is how you represent the cell, but it is still incomplete because on one side you have got the hydrogen electrode, which is made with the help of platinum solid. Okay, perfect. Right, people? I believe this is super clear to everyone. All right, this you can easily represent now. Look at this one. Look at this one, guys. Look at this one. This is some net reaction. This is some cell reaction which is taking place in some galvanic cell. Right? Right, people? This is some net reaction. Ria, it is a convention. Use it, and remember it. Okay? Okay, this is some cell reaction which is happening in some galvanic cell. And after looking at the cell reaction, I have to represent the cell. How exactly? Have a look. First of all, I'll calculate the oxidation state of this chromium. I believe you can easily calculate it. 2x, oxygen will be in -2, multiplied by 7 is equal to -2. The oxidation state of chromium here is +6, right? Similarly, oxidation state of iron here is +2. Oxidation state of chromium here is +3. Here it is also +3. Now understand, chromium is going from +6 to +3, decrease. Decrease in the oxidation state is what you call as reduction. So I would say the Cr2O7 dye negative, it's undergoing reduction. If it's undergoing reduction, then definitely a cathode. From +2 to +3, increase in the oxidation state. Increase in the oxidation state is something which you call as oxidation. And you know, oxidation takes place at what? Oxidation takes place at anode. So you identified your anode and cathode. Since you identified your anode and cathode, now put the two lines first, which represent your salt bridge. On the left side, write the anode. At anode, Fe dye positive is getting converted into Fe tri positive. At anode, Fe dye positive aqueous is getting converted into Fe tri positive aqueous. Do you see the phase same or different? Phase is same. So use comma here. Do not use a slash. Yeah? Similarly, on the right side, write the cathode. At cathode, Cr2O7 dye negative is getting converted into Cr tri positive. I would say Cr2O7 dye negative aqueous is getting converted into Cr tri positive aqueous. Still, I must say the cell reaction is not complete. The cell representation is not complete. Guys, this is the iron-iron electrode. This is also the iron-iron electrode. Perfect. How do we make the normal electrodes? Solid aqueous. Solid aqueous is the normal electrode. Zinc solid into Zn dye positive, because that is the normal electrode. So this is not normal one. So here, I'll be also using platinum solid to make this particular electrode. And here also, I'll be using the platinum solid to make this particular electrode. Okay. So apart from solid aqueous, whatever types you get, use platinum solid there. Perfect. Someone is asking how to find oxidation state. Check my last lecture, redox reactions. I have taken one shot. There you'll understand how to take oxidation state. All right. My dear students, look at this particular cell. See, there is some galvanic cell whose net cell reaction is this one. There is some galvanic cell whose net cell reaction is this one. By looking at the net cell reaction, you have to represent the cell. How? First of all, calculate the oxidation state of manganese. Keep it X. Oxygen will be -2. 4 oxygen atoms, net charge -1. So manganese here is in +7. Carbon here, this is going to be 2x plus oxygen in -2 into 4 is equal to -2. The oxidation state of carbon here is +3. Manganese here is in +2. Carbon here is in +4. Right? Simple oxidation states I'm calculating. Yes? Right, people? Now, manganese is going from +7 to +2. So, this MnO4 negative is undergoing reduction. If it is undergoing reduction, it is going to behave like the cathode. Similarly, +3 to +4 means oxidation. So, this particular species is undergoing oxidation. And if this species is undergoing oxidation, it is going to behave like the anode. So, you identified your anode and cathode. After the identification of anode and cathode, what exactly are we supposed to do? These are the two lines which are going to represent the salt bridge. On the left side of the salt bridge, you'll be writing the anode. At anode, your oxalate ion is getting converted into carbon dioxide. So C2O4 dye negative aqueous is getting converted into carbon dioxide. So again, I'll be using a slash here because the phase is different. But this electrode also cannot be made under the normal conditions. So I'll be using the platinum solid here. Go to the right side, cathode. At cathode, MnO4 negative is getting converted into Mn di positive. So write it directly. MnO4 negative aqueous is getting converted into Mn di positive aqueous. Again, I would say phase is same. If phase is same, put the comma here and use platinum solid here as well, because this is aqueous. So this is how, when the cell reaction will be given to you, this is how you represent a cell. I believe this is clear to everyone. Yes? Right, people? Phase change is used just here. Okay? This is just the platinum solid which is used to make this electrode. Phase change, over here there is no phase change. Okay? Similar, in all the other cases you saw, phase change is happening here, gas into aqueous. This platinum solid is just used to make this electrode, nothing else. Okay? Perfect. All clear, people? All clear with this? All clear with this? Now comes something super important. What is that? How to write the net cell reaction from a given cell. How to write a net cell reaction from a given cell. This is a very, very, very important topic which will be frequently used in the Nernst equation. Yeah? Sir, do you know Chaitanya sir chemistry? He also teaches in Unacademy from Andhra Pradesh. No, I have no idea who he is. He might be one of the educators in the offline mode of Unacademy in the Andhra. I don't know personally who he is. Okay? Sir, repeat. Bro, just use your common sense a bit. You can drag the video a little back. It'll be automatically the repetition. Okay? So people tell me till now, whatever I've discussed, is every single thing clear? Is every single thing clear till here? Quickly. Everybody in the chats. I want the chats to run. I want the chats to run. I want the chats to run quickly. All clear? All clear quickly in the chats, everybody. Everybody, quickly. Perfect. I believe whatever things I've discussed till now, I believe every single thing is clear to every one of you. Amazing. Amazing, guys. Amazing. Let's move on now. Let's move on and let's try to understand this particular topic as well. How do we write the net cell reaction from a given cell? Understand, people, what exactly I'm going to say. For example, imagine that I'm given with a cell like this. The cell is in this format. Zinc solid, zinc di positive aqueous. This is, for example, salt bridge. Over here, I'm mentioning copper di positive aqueous. And this copper di positive aqueous. And right here, I'm mentioning copper solid. Let's say this is some cell that's given to me. Let's say this is some galvanic cell that's given to me. Now, from this particular galvanic cell, what all things can we write? Okay? What all things can we write? Understand, people, what exactly we are going to do. See, first of all, this is your salt bridge. On the left side of the salt bridge, we are going to write the anode. On the right side of the salt bridge, we are going to write the cathode. You know it. On the left side of the salt bridge, we represent the anode. On the right side of the salt bridge, we represent the cathode. Now, first of all, at anode, what is going to happen? You know, at anode, oxidation is going to happen. At anode, oxidation is going to happen. Understand, your zinc is getting converted into zinc di positive. Your zinc is getting converted into zinc di positive. 0 to plus 2. 0 to plus 2. Increase in the oxidation state. Increase in the oxidation state means oxidation. Oxidation involves loss of electrons. So I would say when this zinc will be getting converted into zinc dipositive, I would say loss of electrons will be taking place. Yeah. So I must say, people, your zinc solid gets converted into zinc dipositive aqueous, and with that, you'll be writing 2 electrons. So this is the reaction taking place at anode. Yeah. Similarly, my dear students, you can easily write the reaction taking place at cathode. At cathode, what happens? A reduction takes place. Understand? Copper dipositive getting converted to copper. Plus 2 to 0. Plus 2 to 0. Decrease. Decrease in the oxidation state is something which we call as reduction. Reduction involves gain of electrons. So I would say this copper dipositive aqueous will be gaining 2 electrons and getting converted into copper solid. So I wrote the reaction at anode. I wrote the reaction at cathode. Now, my dear students, tell me just one thing. Tell me just one thing. In these 2 reactions which I wrote over here, do you see the electrons balanced or not? I would say electrons are already balanced. I'm not supposed to balance the electrons. They're already balanced. If the electrons are balanced, just add these 2 reactions. And when you add these 2 reactions, this 2 and this 2 gets cancelled out. So my net reaction is going to be this one. Zinc solid plus copper dipositive aqueous. What does it give? It gives zinc dipositive aqueous plus what? Plus copper solid. Yeah, plus copper solid. This is your net reaction. This is your net reaction, people. How many electrons got cancelled here? 2 electrons. So basically, N value we got to know as 2. And what is this N? N, already I've told you, it represents the number of moles. It represents the number of moles of electrons exchanged in the net cell reaction. Okay, N value is 2. After getting the N value, I'm supposed to write the reaction quotient expression. I'm supposed to write QC expression. And my dear students, this QC over here, what does it represent? It represents the reaction quotient. And how do you write the expression for reaction quotient? One thing which you are going to remember. My dear students, whenever you see any reactant or product in aqueous state, in aqueous form, for that reactant or product which will be in aqueous form, use the term concentration for that. If you see any reactant or product in gaseous form, use the term partial pressure for that. If you see any reactant or product in pure solid or pure liquid form, right? Okay, that is not taken into consideration. What does it mean? Understand. In order to write the QC expression, I'll be always starting with the product. This is my first product, zinc dipositive aqueous. Since this zinc dipositive is an aqueous state, so I'll be using its concentration. I'll be using concentration of zinc dipositive raised per stoichiometric coefficient 1. Multiplied by. This another product, it's in solid form. I've got nothing to do with this. Now come to the denominator. In the numerator, you'll be always writing the products. In the denominator, you'll be writing the reactants. This is in solid form. Nothing to do with this. This is an aqueous state. Write concentration for it. So concentration of Cu dipositive raised power 1. So this is how you represent QC expression. Do you know Wassim Chemistry from Kashmir? Absolutely, I know him. He's one of my very close friends. Okay? All clear, people? So, whenever a cell is given to you, first of all, write the reaction at anode, write the reaction at cathode, get the electrons balanced, add the reactions, okay? And after that, write the QC expression and get the value of N as well. Okay? All clear? All clear, people? All clear, people? All right. For example, you have got a cell given to you in this particular manner. Or let me just modify it. Just a second, guys. Let me write the cells on my own. For example, I'm taking a cell over here. The cell is like this. The cell is, for example, like this. Ag solid, Ag positive aqueous. This is the salt bridge. Copper dipositive aqueous. And here I'm writing copper solid. Now from this particular cell, I have to write every single thing. The first thing which I'll be doing here, what is that? On the left side of the salt bridge, I'll be writing anode. On the right side of the salt bridge, I'll be writing cathode. So my dear students, the first thing is write the reaction taking place at anode. At anode, silver is getting converted into Ag positive. So 0 to +1. Increase in the oxidation state means oxidation, loss of electrons. So I would say Ag solid would be losing one electron and getting converted into what? Getting converted into Ag positive. Ag solid would be losing one electron, getting converted into Ag positive. Similarly, what would be the reaction at cathode? I would say at cathode, reduction is going to take place. Copper dye positive into copper. So what has to be the reaction? I would say copper dye positive aqueous will be gaining 2 electrons, getting converted into copper solid. Are the electrons balanced in both? I would say no, the electrons are not at all balanced in both. So I'll have to balance the electrons first. I will have to balance the electrons first. 2 and 1. So multiply this particular reaction by number 2. When you multiply it with number 2, this becomes 2 times, this becomes 2 times, this becomes 2 times. Now the electrons are balanced. And once the electrons are balanced, you can directly add them up. Yes, you can directly add them up. And when you add these reactions up, what do we get? Understand. After adding the reactions, 2 electrons cancelled. So my net reaction becomes 2 times Ag solid plus copper dye positive aqueous. What does it give me? It gives me 2 times Ag positive aqueous. And with this 2 times Ag positive, you'll be writing copper solid. So this is my net reaction over here. So what is the N value? Since 2 moles of electrons got cancelled, so N value is 2. If I want to write the reaction quotient, I can do that. I'll be starting from the product. This is an aqueous form. So write its concentration of Ag positive raised power stoichiometric coefficient 2. This is in solid form, nothing to do with this, divided by. This is in solid form, nothing to do with this. This is an aqueous form. So take its concentration. Concentration of Cu dye positive raised power stoichiometric coefficient, that's 1. So this is your QC expression as well. I believe I'm clear to everyone. I believe this is clear to everyone. Joseph, can you please try not to spam in the chats? Okay, just focus on the session. Majority of the students watching me right now, they're from South India. They're not from Kashmir, okay? They won't be knowing who SR is. All clear, people? I hope you exactly got to know. I hope you exactly got to know what to do in this particular case. Yeah? Quickly in the chats, everybody. Perfect. Let me take a few more examples so that it becomes like amazingly clear to you. For example, I'm taking a cell like this. Platinum solid for my H2 gas. This is H positive aqueous. This is your salt bridge. On the right side, let's say I'm taking Ag positive aqueous, which is getting converted into Ag solid. This is your cell, for example, which is given to us. By looking at the cell, I need to write all the things. All the things. So on the left side of the salt bridge, I'll be writing anode. So this is my anode over here. Similarly, this is my cathode over here. Since I identified my anode and cathode, now let's try to focus on the things. So first of all, what is going to be the reaction at anode? My dear students, at anode, if you see, H2 is getting converted into H positive. H2 is getting converted into H positive. Now, for example, you have got one hydrogen atom. One hydrogen atom contains one electron, right? When this hydrogen atom loses one electron, it gets converted into H positive. Now here, we do not have the hydrogen atom, it's H2. So I would say H2 will be losing 2 electrons, getting converted into 2 H positives. So my net reaction is going to be, my reaction at anode is going to be H2 gas gets converted into 2 times H positive aqueous, and with that, you'll be writing 2 electrons. So this is my reaction at anode. In the similar way, if I ask you what is the reaction at cathode? At cathode, what's going to happen? A reduction is going to happen. Ag positive getting converted into Ag. So +1 to 0, decrease in the oxidation state, reduction, gain of electrons. So I would say Ag positive aqueous would be gaining 1 electron, getting converted into Ag solid. Well, in these two reactions, are the electrons balanced? No, the electrons are not balanced yet. So I'm supposed to balance the electrons. Yes. How exactly? I'm supposed to multiply this reaction by number 2. So multiply it with 2. This becomes 2 times. This becomes 2 times. Even this becomes 2 times. Well, now add the two reactions. When we add the two reactions, I must say this 2 electron cancels out. So I would say N value here is 2. Okay. So my net reaction in this particular case becomes H2 gas plus 2 times Ag positive aqueous. What does it give me? It gives me 2 times H positive aqueous, and with that, I'll be writing 2 times Ag solid as well. So this is my net reaction. If you ask me N value, that's 2. If you ask me to write the expression for QC, we can do that too. Start with the product. Aqueous. The one which is in aqueous, use the concentration. So concentration of H positive raised power stoichiometric coefficient, that's 2. This is in solid form, nothing to do with that. Divided by. This in gaseous phase, use the term pressure. So pressure of H2 raised power stoichiometric coefficient 1. This is in aqueous form, use the concentration. So concentration of Ag positive raised power stoichiometric coefficient 2. Yes, all clear? All clear, people? I believe all this stuff you should be in a position to do on your own. Now, I'm giving you one cell wherein you can do a mistake. I'm giving you a cell now wherein I feel you can commit a mistake. For example, the cell is like this. The cell is like this. Platinum solid, Fe di positive aqueous, Fe tri positive aqueous, salt bridge. Imagine you have got MnO4 negative aqueous here, and this, for example, Mn di positive aqueous, and this is, for example, your platinum solid. This is your cell which is given to us. After looking at this particular cell, my dear students, I need to write all the stuff, whatever we have done till now. Yeah. See, guys, my first point. On the left side of the salt bridge, we use anode. On the right side of the salt bridge, we use cathode. My dear students, at anode, what do we do? At anode, oxidation happens. Fe di positive getting converted into Fe tri positive. So how Fe di positive would be getting converted into Fe tri positive? So I would say Fe di positive aqueous would be losing one electron, then would be getting converted into Fe tri positive aqueous. This is the reaction at anode. Similarly, if I ask you what should be the reaction at cathode, people, you should be in a position to write the reaction at cathode as well. Understand how? See, manganese here is in +7 oxidation state, here it is +2. So +7 to +2, decrease in the oxidation state. Decrease in the oxidation state means reduction. Reduction means gain of electrons. So I must say MnO4 negative would be gaining certain electrons, then getting converted into Mn di positive. I must say MnO4 negative aqueous would be gaining some electrons and then would be getting converted into Mn di positive aqueous. Now tell me one thing. How many electrons it would be gaining? +7 to +2. +7 to +2. What is the change in the oxidation state? 5 is the change in the oxidation state. 5 is the change in the oxidation state. Right? Perfect. So 5 is the change in the oxidation state for one atom of manganese. I've got only one. So I would say MnO4 negative would be gaining 5 electrons, getting converted into Mn di positive. Right? Okay. Now, my dear students, are the electrons balanced? Look at the first reaction. 1 electron, 5 electrons. So I'll be multiplying first reaction by number 5. When I multiply first reaction by number 5, it becomes 5 times here, 5 times here, and this becomes 5 electrons. I would say the electrons are balanced now. After balancing the electrons, add these two reactions. When you add these two reactions, this 5 and 5 gets cancelled. My net reaction is going to be 5 times Fe di positive aqueous plus MnO4 negative aqueous. What does it give me? It gives me 5 times Fe tri positive aqueous, and with this you'll be writing Mn di positive aqueous. Now if you ask me whether this is a net reaction, I'll say this is not the net reaction. I'll say this is not the net reaction. Yeah, this is not the net reaction. Why is that? Because the reaction is not completed yet. It's not balanced yet. You've got 4 oxygen here. There is no oxygen on the right side. Balance the oxygen. I mean, balance this reaction in acidic medium. Balance this reaction in acidic medium. And by the way, one more thing which I'm giving you here, I'm writing H positive here, which tells you that net reaction you are going to balance in which medium? In acidic medium. Okay, so balance the reaction in acidic medium now. How exactly? After reaching here, people, after reaching here, Now balance the oxygen atoms. Here you have got 4 oxygen atoms. There is no oxygen atom on the right side. Oxygen atoms are balanced with the help of water molecules. Oxygen atoms are balanced with the help of water molecules. So you have got 4 oxygen atoms on this side. On right side, there is no oxygen, right? So right side is oxygen deficient. How many oxygen deficiencies? There are 4 oxygen deficiencies on right side, right? There are 4 oxygen deficiencies on right side. So add 4 water molecules here on right side to balance oxygen. Now, after balancing oxygen, people, understand. How many hydrogen on this side? 8 hydrogens on this side. How many hydrogens on this side? No hydrogen on this side. So, this particular side, left-hand side, it's hydrogen deficient. How many hydrogen deficiencies? 8 hydrogen deficiencies. So, to cover those 8 hydrogen deficiencies, add 8 H positives on this side. Now, it's a balanced reaction. Now, it is a balanced reaction. My dear students, if it is now the balanced reaction, now you can easily write the QC expression. Start with the product. This is in aqueous form. So you'll be using the term concentration. Concentration of Fe tri positive raised by stoichiometric coefficient, that's 5. This is an aqueous state. Again use its concentration. Concentration of Mn di positive raised by stoichiometric coefficient 1. This is in pure liquid state. Nothing to do with that. Divided by. This H positive is an aqueous state. So concentration of H positive raised by stoichiometric coefficient 8. This is also an aqueous state. So use the term concentration of Fe di positive raised by stoichiometric coefficient 5. This is also an aqueous state. Concentration of MnO4 negative raised by stoichiometric coefficient 1. So this is how you write the QC expression, my dear students, for this. Yeah. Whatever H positives, OH negatives you would be adding, they'll be always in aqueous state only. Okay, remember that. Similarly, my dear students, one last case I'm giving you. With that, we are done with this particular concept. Let me give you one last reaction. Let's say I'm giving it a cell like this. Platinum solid, comma. Let me write it as Sn di positive aqueous, Sn plus 4 aqueous, salt bridge, Cr2O7 di negative aqueous, Cr tri positive aqueous. And here I'm using the platinum solid. This is my, for example, this is the cell that's given to me. And since the cell is given to me, and I'm writing H positive here also, just to mention that you will have to balance the reaction in acidic medium. Okay. So how do I write all the stuff again? Reaction at anode, reaction at cathode, etc., etc. So let's exactly do the following things. Reaction at anode. At anode, Sn di positive is getting converted into Sn plus 4. So I would say Sn di positive will be losing 2 electrons, getting converted into Sn plus 4. This is my reaction at anode. Now, what is the reaction at cathode? At cathode, reduction takes place. Reduction means gain of electrons. So, Cr over is in plus 6 oxidation state. Here it is in plus 3. So, plus 6 to plus 3. Decrease. Decrease means reduction. Reduction means gain of electrons. So, Cr2O7 di negative will be gaining electrons, then getting converted into Cr tri positive. Right? Cr2O7 di negative would be gaining some electrons, would be gaining plus some electrons, and then would be getting converted into Cr tri positive. But, one more thing. Here you have got 2 chromium, right? 2 chromium on this side as well. Now, how many electrons are gained? Plus 6 to plus 3. Plus 6 to plus 3. What is the change in the oxidation state? 3. 3 is the change in the oxidation state for 1 chromium atom. How many do I have? I have 2 chromium atoms. So 3 2s are 6. So it is gaining 6 electrons, getting converted into 2 times Cr tri positive. Yeah. Now you will tell me just one thing. Tell me just one thing. In both the reactions, are the electrons balanced? The electrons are not balanced yet. 6, 2. I'm multiplying this reaction with 3. When you multiply this reaction with 3, it becomes 3 times, this becomes 3 times, this becomes 3 2s are 6 electrons. Now the electrons are balanced. After balancing the electrons, add these 2 reactions. And my dear students, when you add these 2 reactions, this 6 and this 6 gets cancelled out. My net reaction becomes 3 times Sn di positive aqueous plus Cr2O7 di negative aqueous. What does it give me? It gives me 3 times Sn plus 4 aqueous plus 2 times Cr tri positive aqueous. Now, if I ask you whether the reaction is balanced or not, I would say the reaction is not yet balanced. We have to balance the reaction more. Say, 7 oxygen atoms on this side, no oxygen atom here. So, right-hand side is oxygen deficient. How many oxygen deficiencies? I would say 7 oxygen deficiencies. So, to cover those 7 oxygen deficiencies, add 7 water molecules. On that side, which is oxygen deficient. Now, how many hydrogens on this side? 14 hydrogens on this side. How many hydrogens on left side? No hydrogen on left side. So left side is hydrogen deficient. How many hydrogen deficiency? 14 hydrogen deficiencies. So add 14 H positives on this side to cover hydrogens. Okay. Now the reaction is balanced. After balancing the reaction, write the QC expression. You should be in a position to write the QC expression. Start with the product. This is an aqueous state. So use the term concentration. So concentration of Sn plus 4 raised power stoichiometric coefficient 3. Similarly, concentration of Cr tri-positive raised power stoichiometric coefficient 2. Water is in liquid state, nothing to do with that, divided by. This is an aqueous state, so use the term concentration of H positive raised power 14. Here, you can use the term concentration of Sn di positive raised power 3. And here, you can use the term concentration of Cr2O7 di negative raised power stoichiometric coefficient, that is 1. So this is my QC expression. Similarly, if I ask you what is the value of N value is coming out to be 6. So my dear students, I believe now you are in a position to write all this stuff for any type of reaction. If yes, let me know once in the chats quickly. Let me know once in the chats quickly with some fire emojis if you can do this stuff on your own now. All clear, people? All clear? Quick in the chats. Let me tell you, oxygen is balanced with the help of water molecules. Hydrogen is balanced with the help of H positive. Just remember it. You are asking this question because you have not studied. You have not studied redox reactions. Okay? That's why you are asking this question. Now, my dear students, let's enter into one more topic, that is your electrode potential. Okay? Electrode potential. Perfect. Perfect, guys. Perfect. Just give me a second. Just give me a second. Just give me a second. Just people give me a second. All right. So let's have a look now. Electrode potential, right? Electrode potential. What the electrode potential exactly means? What kind of questions can be asked from it? Right? What is the application part of it? Let's exactly understand this particular stuff in detail. Okay? Understand, people. When the session will end. We have started the session like 2 hours before. If you want me to end this right now, I can do it. Till the chapter gets completed, we are here. It might take 10 hours, 12 hours, 13, 14, 15. What? If I'm clear. Others, you'll be able to understand everything. Relax, don't worry. Okay, electrode potential. Electrode potential. How do we exactly define it? My dear students, electrode potential, which we first of all represent with capital E. Electrode potential, which we represent with capital E. How do we exactly define it? It is basically the potential difference. It is the potential difference that gets created. It is the potential difference that gets created that gets created between the rod and the electrolytic solution. My God. Between the rod and the electrolytic solution. The potential difference that gets created between the rod and the electrolytic solution is something which we call as electrode potential. What does that mean? Let's try to understand this. Try to understand this in detail. My dear students, for example, imagine this is the container. Imagine this is the container. In this particular container, for example, I've kept zinc sulfate. And I'm assuming the zinc sulfate has got dissociated into its ions completely. Zinc dipositives, SO4 dinegatives. Here I've introduced a rod, a zinc rod. Should I be calling this particular setup as the electrode? Yes, this is the electrode. Rod is introduced in a solution containing its own ions. It is the electrode. Now, my dear students, this particular electrode which we have, it can behave like anode or it can behave like cathode, right? When it behaves like anode, what is going to happen? When it behaves like anode, what is going to happen? My dear students, the first thing, this solution right now is electrically neutral because there are equal number of cations and anions, right? There are equal number of cations and anions, which I'm assuming here in the container. So the solution is neutral right now. And in the solution, I have introduced a zinc rod. So this setup, I'm calling a zinc electrode. This zinc electrode, it can behave like anode or it can behave like cathode. When this zinc electrode behaves like the anode, what's going to happen? Oxidation. The rod is made up of zinc atoms. Those zinc atoms of which a rod is made up of, those zinc atoms will undergo oxidation. Those zinc atoms will undergo oxidation. I would say zinc solid will be getting converted into zinc dipositive aqueous. With that, you'll be getting 2 electrons. This zinc dipositive, which is coming from the rod, it is going to enter into the solution, due to which the solution gets a positive charge. And these 2 electrons, they are accumulated on the rod, due to which negative charge is developed on the rod. This is the scenario which is happening when the zinc electrode is behaving like what? When the zinc electrode is behaving like anode. Now imagine if the same zinc electrode behaves like the cathode. Imagine if the same zinc electrode behaves like the cathode. What is going to happen at that point of time? Imagine this is a zinc rod. Now, for example, this particular zinc electrode has to behave like cathode. If it is behaving like cathode, what's going to happen? I would say reduction is going to take place. Right? Zinc dipositives which are there in the solution, they are going to collide with the rod. They are going to take 2 electrons from the rod. So I would say zinc dipositives which are there in the solution, they'll be taking 2 electrons from the rod, getting converted into zinc solid. Initially, there were equal number of cations and anions in the solution, due to which the solution was neutral. Now, one of the cation, it got reduced, got converted into zinc solid. That zinc solid got deposited on the rod, due to which cations are decreasing in the solution. If cations are decreasing in the solution, I would say effectively negative charge is developed in the solution. Now, my dear students, what happened basically? Cation collided with the rod, took electrons from the rod. If cation is taking electrons from the rod, I would say rod is getting positive charge. This is the case when the zinc electrode is behaving like the cathode, right? So I made zinc electrode to behave like anode as well as cathode. In both the cases, my dear students, do you see one thing? When zinc electrode is behaving as the anode, rod got negative, solution got positive. Here, rod got positive, solution got negative. In both the cases, do you see a potential difference getting created between the rod and the solution? Dear students, understand. The rod carries negative here, solution carries positive here. I would say potential difference got developed between the rod and the solution. In this particular case also, potential difference got developed between the rod and the solution. And the potential difference that gets created at the interface due to between the rod and the solution, that potential difference developed is something which we call as electrode potential, right? So what is electrode potential? Why we chose zinc? You can choose copper as well. You can choose anything, right? These are the time to ask these sort of questions, that's over. Now just remember what I'm telling, because this will be asked in NEET examination. What you are asking me, that won't be asked, okay? So people, what I'm trying to say is, between the rod and the solution, potential difference got created. Between the rod and the solution, potential difference got created, right? And the potential difference that gets created between the rod and the solution is something which we call as electrode potential, right? The potential difference that gets created between rod and the solution is something which we call as electrode potential. And this electrode potential, we represent the electrode potential by E, right? This electrode potential I'm classifying into two parts. One is called as oxidation potential. One is called as a reduction potential. My dear students, here the electrode behaved like anode. At anode, oxidation took place. So this potential difference, when rod got positive, solution got negative. This potential difference I'm calling as oxidation potential. And here I made the same zinc electrode to behave like cathode. At cathode, reduction takes place. This potential difference between the rod, when rod got positive, solution got negative. I'm calling this as reduction potential. This is your oxidation potential difference. This is your reduction potential difference. Okay. So in general, your electrode potential I'm classifying into two parts. One is oxidation potential, one is reduction potential. Perfect. One is oxidation potential and one is reduction potential. Now, my dear students, what is important here? That is, how do we represent this oxidation and reduction potential? I can represent EOX like this as well. E of M gives Mn positive aqueous. I can represent reduction potential like this as well. E of Mn positive aqueous gives M. Try to understand. 0 to plus N. 0 to plus N. Increase in the oxidation state. Increase in the oxidation state means oxidation. Means oxidation. So this term represents your oxidation potential. Similarly, plus N to 0. Plus N to 0. Decrease in the oxidation state. Decrease in the oxidation state is what we call as reduction. Right? So this particular term, it represents your reduction potential, in short. Yeah, in short. I believe I'm clear with this. I believe I'm clear with this. I believe I'm clear with this. If I'm clear, let me know quickly in the chats. Everybody. Everybody in the chats, people. Everybody in the chats. So this is how you represent your oxidation potential. This is how you represent your reduction potential. Now, people, one more important thing. Let me tell you, when electrode potential is calculated, when electrode potential is calculated under standard conditions. When electrode potential is calculated under standard conditions. What are standard conditions exactly? Standard conditions represent when pressure is kept as 1 bar, concentration of electrolyte in the solution is taken as 1 molar, temperature is kept constant, generally 25 degrees centigrade. At that point of time, we can say that the electrode is present at standard conditions. And when electrode potential, which is the potential difference between the rod and the solution, when it's calculated under standard conditions, at that point of time, you call it as the standard electrode potential represented by E naught. You call that as the standard electrode potential represented by E naught. Perfect. Now, this standard electrode potential also I'm classifying into two parts. One I'm calling as E naught OX, standard oxidation potential. One I'm calling as E naught RED, standard reduction potential. Or is there any other way to represent them? Yes, you can do that. E naught. M gives Mn positive. Similarly, E naught. Mn positive gives M. Perfect. This represents your SOP, standard oxidation potential. This represents your SRP, standard reduction potential. How exactly you can check it? See, 0 to plus N. 0 to plus N means increase in the oxidation state. Increase in the oxidation state is what we call as oxidation. So this particular term, it represents your oxidation, standard oxidation potential. Plus N to 0, plus N to 0, decrease in the oxidation state. Decrease in the oxidation state is what you call as reduction. Decrease in the oxidation state is what you call as reduction. So this particular term, it represents your standard reduction potential. Perfect. Now, people, there are a few more things which I would want to share with you related to this SOP, SRP, etc., etc. Let me tell you, for an element, I'm just giving you the conclusions. I'm just giving you the conclusions. Otherwise, I'll have to show you how to calculate this SOP SRP. You have got nothing to do with that. Okay? I'm just giving the conclusions which you're going to remember, and later on we'll use those applications in the questions. Okay. My dear students, for an element, its SOP is always equal to minus times its SRP. If you have got an element, its SOP will be always equal to minus times its SRP. For example, if I'm writing something like this, if I'm writing E naught of A gives A positive. Let's say this value is, for example, 1.1 volt. What is this value first of all? A gives A positive. So 0 to plus 1. 0 to plus 1 means increase. Increase means oxidation. So this is your SOP. If I want to know the SRP of the same one, SRP is represented like this. A positive gives A. So plus 1 to 0. Plus 1 to 0 means decrease. Decrease means reduction. So this SRP. So its SRP will be nothing but just change the sign. That's all. Right? So if you know SOP of the electrode, you can easily calculate its SRP by just reversing the sign. That's all. By just reversing the sign. Okay? Right, people? By just reversing the sign. Now, understand few more things. My dear students, let me tell you, SOP as well as SRP. SOP as well as SRP of an electrode. SOP as well as SRP of an electrode is measured with the help of a reference electrode. SOP as well as SRP of an electrode is measured with the help of reference electrode, which is what you call as standard hydrogen electrode. So, I believe all of you would have seen the electrochemical series, right? I believe all of you would have seen the electrochemical series. And my dear students, in the electrochemical series, the SOPs and SRPs of different elements are given. SOPs, SRPs of different elements are given. From where do we calculate how do we calculate the values of SOPs or SRPs of different elements? We calculate SOPs or SRPs of different elements with the help of a reference electrode, and that reference electrode is your standard hydrogen electrode. Now, what is this standard hydrogen electrode? Let's try to analyze this first of all, then we'll say all the other things. I'm marking the heading first of all here as standard hydrogen electrode, which is taken as the reference electrode, to calculate the SOPs or SRPs of different elements. Yes? Right, people? So, do you know Anmol sir? Yes, I know him. Why? Okay, see guys, how this standard hydrogen electrode is made. Standard hydrogen electrode, which is my reference electrode. This is my reference electrode, with the help of which we calculate the SOPs and SRPs of different elements. And how exactly? Have a look. Have a look how this standard hydrogen electrode is made. First of all, imagine that you are taking a container. And my dear students, in this particular container, imagine you're taking HCl. Let's say you have got HCl in this particular container. Okay. This HCl would have given what? This HCl would have got converted into H positive ions and Cl negative ions. So there are technically, I would say, there are H positive ions in the container. I'm assuming the concentration of H positives in the container is 1 molar. I'm assuming the concentration of H positives in the container is 1 molar. Now here, what exactly I'm doing? I'm taking an inverted tube like this. I'm taking an inverted tube like this. And people, in this inverted tube, I'm going to keep a platinum wire. Imagine this is the platinum wire which is coated with platinum black. In this inverted tube, I'm taking platinum wire, I would say coated with platinum black. Coated with platinum black. Now people, what we should be doing? See, you can see this particular opening. From this, I'm introducing H2 gas at the pressure of 1 bar. I'm introducing H2 gas at the pressure of 1 bar. What is going to happen? What is going to happen? When you introduce H2 gas at the pressure of 1 bar, I would say the H2 gas molecules will start to adsorb on its surface. Right? I would say the H2 gas would have adsorbed on the surface of this platinum. I'll make sure that I'll introduce H2 gas till entire surface of platinum is covered with what? Till entire surface of platinum is covered with H2 gas. So there will be a scenario when this entire platinum wire will be covered with H2 gas. Perfect. Now, do you see? Does it look like a platinum wire to you, or you can call it as the hydrogen wire? It looks like a hydrogen wire now. This hydrogen wire is introduced in a solution containing its own ions. This hydrogen wire is introduced in a solution containing its own ions. So I'll be calling this particular setup here as the electrode, right? Let's say the temperature I'm keeping constant, and let's say it is 25 degrees centigrade. So do you see, we made the hydrogen electrode under standard conditions, right? And hydrogen electrode, when made under standard conditions, is what you call as standard hydrogen electrode, right? You call it as the standard hydrogen electrode. Now, my dear students, this particular standard hydrogen electrode, it can behave as anode as well as it can behave like cathode. When this hydrogen electrode behaves like anode, what is going to happen? I would say H positives on the rod will start getting converted into, H2 gas molecules on the rod, H2 gas molecules on the rod will start getting converted into H positives. And this is the reaction which you'll be writing. This is the reaction which you'll write when the hydrogen electrode is going to behave like the anode. Similarly, what would be the reaction when the hydrogen electrode would be behaving like the cathode? Just reverse the reaction. I would say H positives in the solution. H positives in the solution. They'll be colliding with the rod, take 2 electrons from the rod and get converted into H2 gas. This is the reaction when hydrogen electrode is going to behave like the anode. This is the reaction when hydrogen electrode is going to behave like the cathode. And my dear students, by convention, E naught, H2 gives H positive, or E naught, H positive gives H2. What do I call this particular term as? Is it the SOP or SRP? 0 to +1, increase. Increase means oxidation. So this is oxidation potential of the hydrogen electrode. +1 to 0, +1 to 0, decrease. Decrease means reduction. So this is SRP, standard reduction potential of hydrogen electrode. And as per convention, both of these terms are taken as 0 as per convention. SOP as well as SRP. SOP as well as SRP. SOP as well as SRP of the hydrogen electrode is taken as 0 as per reference. And every element's SOP or SRP is calculated by taking this hydrogen electrode into reference. I believe I'm clear, everyone. Okay? Now, my dear students, if you think, where do we use the concept of SOPs, SRPs, right? You must be thinking about that. Then have a look on these 2 terms over here, which I'm writing. Significance of standard electrode potential. Significance of standard electrode potential. My dear students, just remember 2 sentences and you can easily solve all the different types of questions. 2 simple things you have to write. First point. More the value of SOP, more the value of SOP of an element, more is the tendency of an element to undergo oxidation. More is the tendency of an element to undergo oxidation. The one which has got more tendency to undergo oxidation, that would be the better reducing agent. That would be called as the better reducing agent. The one that is the better reducing agent, its reducing power will be more. Its reducing power would be more. You just have to remember this particular statement. More the SOP, more the tendency to undergo oxidation, better the reducing agent, more the reducing power. Someone is continuously spamming, sir, are you married or not? What do you have to do with my marriage? I'm still not going to call you for my marriage. What do you have to do? Just learn things. Don't involve yourself in the unnecessary nonsense stuff. Yeah? What do you have to do? I'm not worried about my marriage. Are you worried about my marriage? And tell me. Yeah? Just focus on the things so that you can qualify NEET quickly and get married quickly. Otherwise, you'll have to be like me, right? Just focus on this stuff. Got it? So remember this particular statement, guys. More the SOP, more the tendency of the element to undergo oxidation. More the SOP, more the tendency to undergo oxidation. Better the reducing agent, more the reducing power. More the reducing power. Okay? Similarly, more the SRP of the element. More the SRP of the element. More the SRP of the element. More is the tendency of the element to undergo reduction. More is the tendency of an element to undergo reduction. Better the oxidizing agent. Better the oxidizing agent. More will be its oxidizing power. Remember these two statements. And people, from these two statements, you can easily solve all the different types of questions that can be asked. Okay? Look here. More SOP, more tendency to undergo oxidation, better reducing agent, more reducing power. More the SRP, more the tendency to undergo reduction, better oxidizing agent, more the oxidizing power. Now, for example, understand properly what I'm going to say. Let's say I'm taking certain elements, A, B, C, and D, right? Let's say here I'm writing E naught of M gives Mn positive. I'm writing E naught of M gives Mn positive. Let's say I'm writing for A it is 1.1 volt, for B it's 2.1 volt, this is 3.1 volt, this is 4.1 volt. First of all, tell me, is this particular term representing SOP or SRP? Check it out. 0 to plus N, increase means oxidation. So these are SOP values. Now, among all these, which one has got maximum SOP? This one has got maximum SOP. More the SOP, more the tendency to undergo oxidation, better reducing agent, more reducing power. So you can give the order of reducing power here, right? This will have maximum reducing power, better reducing agent. For example, if I write values like this, E naught of M gives Mn positive. Let's say this is minus 1.1 volt, this is minus 2.1 volt, this is minus 3.1 volt, this is minus 4.1 volt. Now, look at this particular term. Is it SOP or SRP? Check it out. SOP or SRP. 0 to plus N, increase. 0 to plus N, increase. Increase means oxidation, right? So these are again SOP values. Now, which one has got maximum SOP? Minus 1.1, maximum SOP. More the SOP, more the tendency to undergo oxidation, better reducing agent, more the reducing power. More will be its reducing power, right? Similarly, if I write stuff like this, E naught of Mn positive gives M. Is this SOP or SRP? Mn positive gives M. Is it SOP or SRP? Plus N to 0. Plus N to 0 means decrease in oxidation state. Decrease in the oxidation state is reduction. So this represents SRP. Let's say this is 1.1, this is 2.1, this is 3.1, this is 4.1. So these are all the SRP values. So which one has got maximum SRP? This has got maximum SRP. More the SRP, more the tendency to undergo reduction, better oxidizing agent, more oxidizing power. Better oxidizing agent, more oxidizing power. Done and dusted, right? Similarly, for example, I'm writing E naught of Mn positive gives M. Let's say this value is minus 1.1 volt. This is minus 2.1. This is minus 3.1. This is minus 4.1. Now, are these SOPs or SRPs? These are again SRP values. Again SRP values. Which one has got maximum SRP? This one has got maximum SRP. More the SRP, more the tendency to undergo reduction, better oxidizing agent. So this is the better oxidizing agent. So its oxidizing power would be the more. Would be the maximum. I believe I'm clear. If I'm clear, let's see what kind of questions have been asked from this. Look at the first question, guys. Look at the first question. Look at the question carefully and try to solve this. Try to solve this, people. Quick. Quick, people. If you look carefully, first of all, in all these reactions, what is happening? gain of electrons is taking place. Magnesium dipositive is gaining 2 electrons. Gain of electrons. Gain of electrons is what we call as a reduction, right? So these are the SRP values of what? Since Mg dipositive is undergoing reduction, right? So this is the SRP value of it. Zinc dipositive is undergoing reduction. So this is the SRP of this. Nickel dipositive is undergoing reduction. SRP of it. Fe tripositive is undergoing reduction. SRP of it. Okay. We have to give the order of reducing agents. We have to give which one is the better reducing agent. My dear students, reducing agent, a better reducing agent will undergo oxidation easily. A better reducing agent will undergo oxidation easily. Now, which one will undergo oxidation easily? The one that has got more SOP. The one that has got more SOP. So I can solve the question in terms of SOP. But what is given? SRP is given. So I'll be reversing these reactions. When I reverse the first reaction, I'll write it like this. Magnesium gives Mg dipositive plus 2 electron. And now its E naught will be equal to, reverse the sign, it is plus 2.37 volt. Reverse the second reaction. Zinc gives zinc dipositive plus 2 electron. Its E naught, reverse the sign, it is plus 0.76 volts. Similarly, reverse the third reaction. Nickel gives nickel dipositive plus 2 electrons. Reverse the sign, its E naught is going plus 0.73 volts. Similarly, the last reaction, reverse it. Fe gives Fe tripositive plus 3 electrons. Reverse its sign, it is 0.04 volts. Now, in this reaction, magnesium is being oxidized. Zinc is undergoing oxidation. Nickel is undergoing oxidation. Iron is undergoing oxidation. So now these are the SOP values. These are the SOP values, right? These are the SOP values of these elements over here. Perfect. Now, check which is the maximum SOP value. I would say this is the maximum SOP value, right? More the SOP, more tendency to undergo oxidation, better reducing agent. So, magnesium's SOP is maximum. So, magnesium has got maximum tendency to undergo oxidation, right? So, better reducing agent. So, it's magnesium which is going to be the better reducing agent among all. Clear? Clear, people? Clear? It is going to be magnesium which is going to be the better reducing agent, right? Reducing agent is the one which undergoes oxidation. Now here magnesium is undergoing oxidation. Magnesium dipositive is not undergoing oxidation. Magnesium is undergoing oxidation. Here zinc is undergoing oxidation. Zinc dipositive is not undergoing oxidation. I believe I'm clear. I believe I'm clear. You need to give me the oxidizing power order. You need to give me the oxidizing power order. Check it out. Oxidizing power. First of all, oxidizing power. The one that is the better oxidizing agent will have more oxidizing power. Oxidizing agent undergoes reduction. So the one that undergoes reduction easily, better oxidizing agent. The one that has got more SRP will undergo reduction easily, better oxidizing agent, more reducing power. The one that undergoes reduction easily. Now, you have to give the order of oxidizing power. Oxidizing power and SRP, they are directly proportional. More oxidizing power, more SRP. They are directly proportional, right? So which one has got maximum SRP? First of all, in this reaction, cobalt tripositive is gaining electron. So cobalt tripositive is undergoing reduction. Here, this is undergoing reduction. Here, this is undergoing reduction. This is undergoing reduction, right? So these are SRP values. These are SRP values. Perfect. Now, which one has got maximum SRP? Maximum SRP. Which value is maximum among these? This is the maximum SRP. Maximum SRP means maximum oxidizing power. So, cobalt tripositive has got maximum oxidizing power, followed by 1.67, that is for PV plus 4, followed by 1.61, that is for cerium plus 4, followed by Bi tripositive over here. This is the order of the oxidizing powers, right? Simple. I believe all this stuff, people, is absolutely clear to you. I hope you can solve these sort of questions easily from now on. You were just supposed to write the order for the oxidizing power. I just checked one thing. More the oxidizing power, better the oxidizing agent. Now, which one will be the better oxidizing agent? The one that undergoes reduction easily. Which one undergoes reduction easily? The one that has got more SRP. That's all. Yes? Perfect. What should be the answer of this particular question? What do you think? The reducing powers of the metals. Reducing powers. Reducing power. You know, better reducing agent has got more reducing power. Reducing agent is the one that undergoes oxidation. So the one that undergoes oxidation easily, better reducing agent, more reducing power. Now, which one undergoes oxidation easily? The one that has got more SOP. But are these values the SOP values or SRP values? These are SRP values because you see gain of electrons happening. Gain of electrons means reduction, right? So these are all SRPs. So reverse them, make them SOPs. So when I reverse the first reaction, it becomes zinc gives zinc di positive plus 2 electrons. So SOP of zinc here will be 0.76 volts. Now see, this zinc is now undergoing oxidation. It is losing electrons. So this is the SOP of zinc. Similarly, SOP of calcium. SOP of calcium. SOP of calcium, when it gets converted into calcium di positive, will be how much? 2.87 volts. Similarly, SOP of magnesium will be, reverse the sign. Just reverse the sign, plus 2.36 volts. Similarly, SOP of nickel. SOP of nickel will be how much? Just reverse the sign, plus 0.25 volts. Now, which one has got maximum SOP? Check it out. Maximum SOP, I can find out this has got the maximum SOP. So it's for calcium. The one that has got maximum SOP, would have more reducing power. So calcium has got maximum reducing power. Calcium has got maximum reducing power. Calcium has got maximum reducing power. Right? After calcium, which is the next value 2.36, it's for magnesium. After magnesium, which one is the next? 0.76, that's for zinc. After zinc, it is nickel. So this is the order of the reducing powers. Which option satisfies it? Calcium, magnesium, zinc, and nickel. So it has to be option B. Yeah? It has to be option B. Perfect? Simple, guys. You guys just suppose check which of the following has got more reducing power. Reducing power means better reducing agent. Better reducing agent will undergo oxidation easily. Which one will undergo oxidation easily? The one whose SOP is maximum. So SRPs were given. I converted them into SOPs. Right? So I just reversed. Now this zinc is undergoing oxidation. So this would be the SOP of zinc. This would be the SOP of copper, calcium, etc., etc. That's how I did the question. I hope this is clear. If this is clear, then this is one more question which I believe you should be in a position to solve on your own. This is one more question. What do you think? Just solve this question. Let me know its answer. I'll give you the break for 30 minutes. Just tell me the answer of this question. For the reduction of NO3 negative ions in the aqueous solution, E0 for NO3 negative. That means it's the SRP of NO3 negative, right? E0 for some elements are given. The pair of metals that can be oxidized by NO3. Which of the following pair of metals? Is it iron? Is it mercury? Is it vanadium? Is it gold? Which of the following will be oxidized by NO3 negative? Which of the following will be oxidized by NO3 negative? My dear students, if NO3 negative has to oxidize iron, that means NO3 negative itself should undergo reduction. This should undergo reduction. This should undergo oxidation. Right? If NO3 negative has to oxidize iron, that means NO3 negative should undergo reduction. This should undergo oxidation. Now, just compare their SRP values. Which one has more SRP? 0.96 or 0.04? This is more. This SRP is more. If NO3 negative has got more SRP than iron, then NO3 negative will undergo reduction because its SRP is more. Right? It will undergo reduction. If it undergoes reduction, that means this can easily undergo oxidation. So, NO3 negative can oxidize iron. It can oxidize iron. Yes? Now, can NO3 negative oxidize this mercury? Look at compare their values. If NO3 negative has to oxidize mercury, that means NO3 negative itself has to undergo reduction. This should undergo oxidation. Now compare their values. 0.96 minus 0.86. This SRP is more. If this SRP is more, so it will have more tendency to undergo reduction. So this will undergo reduction and this will undergo oxidation. So yes, right? Similarly, 0.96 minus 1.9. Yes. Okay. 0.96, 1.40. Now, Can NO3 negative oxidize gold? Check it out. Its SRP is 0.9. Its SRP is 1.4. Whose SRP is more? Gold's SRP is more. If gold's SRP is more, so it will undergo reduction. If it is undergoing reduction, that means this one will undergo oxidation, right? So gold is oxidizing NO3 negative here. Gold is oxidizing NO3 negative here. Gold is oxidizing, right? Gold is oxidizing NO3 negative here. It is not NO3 negative oxidizing gold. Got it? So answer is going to be iron, Hg, and vanadium. These are the pair of the metals which can be oxidized by NO3 negative. It's simple, guys. For NO3 negative to oxidize them, NO3 should itself undergo reduction. So these should undergo oxidation. For NO3 to undergo reduction, so I would say SRP of NO3 negative should be more, right? So SRP of NO3 negative is more than this value. SRP of NO3 negative is more than this SRP. SRP of NO3 negative is more than this, right? So in these first three cases, NO3 negative can oxidize these metals. Okay? Got it, people? Am I clear? 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 Say it in the chats quickly now. Is it clear now? People are saying, how vanadium? This is minus here. SRP of NO3 negative is more than this value, right? If SRP of NO3 negative is more than this value, that means NO3 negative will undergo reduction. If NO3 is undergoing reduction, that means this vanadium will undergo oxidation. That's something which you are supposed to check. In which of the following NO3 negative will oxidize the metals? NO3 negative can oxidize this vanadium, for sure. So let me know once in the chats if it is clear. Yes, I hope all the stuff is clear. Now we are going to jump into EMF, but we'll take a break over here, and the break is going to be for 30 minutes. But you have to make a promise with me that all of you would be back by 8:30. Is that a promise? Is that a promise? Because at 8:30 we shall be discussing actual stuff which is asked. That is the Nernst equation. Yes, that is the Nernst equation. Perfect. So break till 8:30, people. And it's not the dinner break. Dinner break I'll be giving at 10:30. Dinner break I'll be giving at 10:30. So right now you can have some tea or coffee so that you'll be refreshed quickly. Okay? Chalo, I'll see you exactly at 8:30, but be back on time. Be back on time. Now we have to start something amazing, something interesting. See you in a while. Bye-bye. Is everyone back? Yeah, everyone is back or not? So guys, tell me, whatever things we discussed till now, is every single thing clear? Yeah? Whatever things I discussed with you till now, is every single thing absolutely clear? Everyone? Let me know in the chats, quickly. Everyone in the chats, quick. Perfect. That's great. So let's move on to the next topic now. That is, again, one of the very important topics. I would say this entire chapter will revolve on this particular topic, that is EMF. Okay, this entire chapter of electrochemistry, it's going to revolve under this particular topic. That is going to be the EMF. So first of all, how do we exactly define the EMF? Let me first of all write its definition. My dear students, if you talk about EMF, EMF is defined as the maximum potential difference between the electrodes, maximum potential difference between the electrodes when no current, when zero current is drawn from the cell. The maximum potential difference between the electrodes when no current is drawn from the cell, or I can say when the cell is not in use. When the cell is not in use. What is meant by this, my dear students? What is meant by this? See, first of all, the battery which you get from the market, the cell which you get from the market, the cell which I use here in this particular remote, right? That pencil cell. Perfect. My dear students, when you get the cell from the market, on the cell, there will be something mentioned like 5 volt, right? On the cell, there will be something mentioned as 5 volt or 10 volt or whatever volt, 2 volts, 1 volt. Perfect. What is this 5 volt mentioned on the cell, which you get from the battery, which you get from the market? What is this 5 volt mentioned on the cell, which you get from the market? This is basically the potential difference at which the cell is going to produce the current. This is the potential difference at which the cell is going to produce the current, right? My dear students, when you just get the cell from the market, and let's say you have not used the cell till now, the cell is brand new, and on the cell there is something mentioned as 5 volt. So the cell is going to produce the current, right? The cell is going to produce the current by the virtue of 5 volt voltage which is mentioned on it. Yes? Now, my dear students, when the cell starts working, so right now, let's say the cell was not under the working condition. Let's say I had not used the cell yet. The cell is right now under brand new condition, right? So the cell is not in use. right now. Perfect. Now, when the cell is going to be used, what will happen to the cell? The cell will go under the discharge mode. When the cell is under usage, we say the cell is now under the discharge mode, right? After some time, when the cell keeps on working, you will see the potential difference will fall to 4 volts. After some time, 3 volts. After some times, it's going to be 0 volt. At this point of time, the cell will again stop working. It's not going to produce current. Initially, when the cell was not in use, the voltage of the cell was 5 volts. This was the voltage under which the cell was going to produce the current. Now, with time, when you use the cell is now under the discharge mode. Its potential difference will keep on decreasing. It will keep on decreasing. And finally, the potential difference between the electrodes in the cell will reach 0 volts. At that point of time, the cell will stop working. The cell will be considered as dead. Now, my dear students, as you see, there are a lot of values which I've written over here. Which one is the maximum value among all? I'll say this 5 volts is the maximum value among all. When the cell was not in use. The maximum potential difference between the electrodes when no current is drawn from the cell. The maximum potential difference between the electrodes when the cell is not in use. You call that potential difference as the EMF of the cell, right? So the cell which we got from the market, its EMF is basically 5 volts. Its maximum potential difference was 5 volts when the cell was not in use, when no current was drawn from the cell. Okay? Perfect. Right? So what is EMF? EMF is basically the maximum potential difference when the cell is not in use, when no current is drawn from the cell. So this 5 voltage, this is the maximum potential difference between the electrodes in the cell when the cell was not in use. So I'll be calling this 5 volt here as the EMF of the cell. All these other voltages, I'll be calling as cell voltage. All these other stuff, I'll be calling as cell voltage. Perfect. I'll be calling them as cell voltage. Now, let me tell you, the maximum potential difference between the electrodes when the cell is not in use is something which we call as EMF. And this EMF is measured with the help of, potentiometer. This EMF is measured with the help of potentiometer. Let me give you the slight idea. Of how this EMF is measured basically. I hope you got to know, you got the idea of, you got the glimpse of what EMF is. EMF is the maximum potential difference between the electrodes in the cell when the cell was not in use, when no current was drawn from the cell. Perfect. At that time, right? Whatever was that 5 volts written on it, that was the EMF. That was the maximum potential difference between the electrodes when the cell was not in use. And with time, when the cell was in usage, when the cell was under discharge mode, its potential difference kept on decreasing. All the other voltages apart from that 5 volt is something which I'm calling as cell voltage. The maximum potential difference I'm calling as the EMF, which is measured with the help of potentiometer. Let me quickly show you how it's measured basically. Understand, guys, what I'm going to say. This is something very important. So try to understand it very carefully. See, let's say I've got a cell which we got from the market. In the cell, there'll be 2 electrodes, right? This is electrode 1, this is electrode 2. Let's say this is your zinc electrode, which behaves like the anode, carrying the negative charge. This is your copper electrode, right? Carrying positive charge. Perfect. And here, I'm connecting it with the help of emitter. And here, you've got a solder bridge. This is your cell. Now, my dear students, what this cell does, it produces current. Right? And if you remember, the direction of current was from positive to negative, from higher potential to lower potential. The direction of current was from higher potential to lower potential. This was the direction of current, from positive to negative, from copper till zinc. This was the direction of current. Perfect. Since this galvanic cell, it produces current, and current is produced due to potential difference. So I would say between these two electrodes, there must be potential difference due to which the cell is producing current. I must say there must be potential difference between these two cells, between these two electrodes, right? Due to which the cell is producing current. Okay? Right? And my dear students, the maximum potential difference between the electrodes when the cell is not in use, what do you call that as? You call that as E cell. And in case of Daniell cell, you must be knowing E cell is equal to 1.1 volts in case of Daniell cell. So how this 1.1 volts is calculated basically? How it is calculated? Understand. My dear students, I'll be using an external battery over here. Let's say this is the positive terminal of the external battery, negative, positive, negative. Right? Perfect. This is the external battery which I've used over here. Now, I'm connecting the positive end of external battery with the negative terminal of the cell, and I'm connecting the positive electrode with this negative part over here. For example, right? What I did, I connected the negatively charged rod with this positive end of the external battery. I connected the positive end over here of this particular rod. I connected this positively charged rod with this negative end of the external battery. So basically, what am I doing? I am connecting this external battery with the cell in reverse polarity. I'm connecting this external battery with the cell in reverse polarity. Perfect. All clear? My dear students, imagine if external voltage is kept zero. Imagine right now I'm not using the external battery, right? External voltage is kept zero. What will happen? The cell is normally going to work like a galvanic cell in which current will flow from cathode to anode, right? Perfect. And this emitter will be showing the deflection right now. So I would say the cell is normally working like a galvanic cell. In which current will be going from cathode to anode. This is the case when we have not used the external battery. Now, for example, you are using the external battery, that too with reverse polarity. My dear students, right now, when the external battery was not used, let's say this emitter was showing some kind of deflection. Right? Let's say the emitter was right now showing some kind of deflection when we had not used the external battery. That means this cell was producing current. Now, my dear students, try to understand what I'm going to say. If you slowly increase the voltage of external battery, what is going to happen? Since positive is connected with negative is connected with positive, you are increasing the voltage of external battery. You are increasing slowly the voltage of external battery. I would say this deflection is slowly going to decrease. At some external voltage, the deflection would be zero. At that point of time, cell stops working. When would be the deflection zero? I would say when the voltage of the external battery becomes equal to the EMF of this cell, becomes equal to the potential difference of this particular potential difference between these two electrodes, right? When this scenario arises, when voltage of external battery becomes equal to the potential difference between the electrodes, I would say at that time cell stops working. No current is drawn from the cell. Perfect. When slowly I'm increasing the voltage of the external battery, there will be a scenario when the arrow is going to be straight upwards. Perfect. So I would say the time when the arrow will be upwards properly with no deflection, I would say at that time your external voltage is equal to the potential difference between these two electrodes, right? Perfect. So that particular external voltage that particular external voltage when the arrow was straight upwards. In case of Daniel's cell, that external voltage is equal to 1.1 volts. Perfect. So what is this 1.1 volt now? I would say this 1.1 volt is nothing. It is the EMF of the cell. Was the cell working at this point of time? When external voltage is equal to E cell, the cell was not working, right? So I would say this is basically the maximum potential difference between the electrodes which we calculated with the help of external battery, right? This is the maximum potential difference between the electrodes when the cell was not in use, when no current was drawn from the cell. And that maximum potential difference between the electrodes when the cell is not in use, when no current is drawn from the cell, that is something which you call as EMF. Did you understand what EMF is? Did you understand what EMF is? Tell me quickly in the chats, people. Did you understand what EMF is? Tell me quickly in the chats. So EMF from now onwards, remember it, it is the maximum potential difference between the electrodes when no current is drawn from the cell. Okay? And this is how it's measured with the help of external battery which I've taken. Perfect. All clear? Say yes or no in the chats. All right, people. Now, let me tell you EMF when measured under standard conditions. EMF when measured under standard conditions is called as what? You call it as the standard EMF of the cell. EMF when measured under standard conditions is called as the standard EMF of the cell. And the standard EMF of the cell is represented by E0 cell. Standard conditions means that means the concentration of electrolytes is kept 1 molar, pressure is kept 1 bar, temperature is kept constant, generally 25 degrees centigrade. Whenever under these conditions we calculate EMF of the cell, what do we call that EMF as? We call it as the E0 cell, standard EMF of the cell. And my dear students, how do we calculate the standard EMF of the cell? E0 cell is calculated by the formula E0 cathode minus E0 anode. What is this E0 cathode and what is this E0 anode? Let me tell you, this E0 cathode is nothing but it is the SRP of cathode, and this E0 anode here I'm using as SRP of anode. SRP of cathode minus SRP of anode. It is going to give me what? It is going to give me the standard EMF of the cell. It is going to give me the standard EMF of the cell. Perfect. Now people, one more thing. Do we have only one result to calculate E0 cell? No, there are many other results too. See, what you can do, as I told you, E0 cell is equal to SRP, EMF is equal to SRP of cathode minus SRP of anode. This is one of the results. Now you can convert it into different forms too. Well, instead of SRP of cathode, you can write minus times SOP of cathode, right? Minus times. Instead of SRP of anode, you can write minus times SOP of anode, right? So the formula will become SOP of anode minus SOP of cathode. This can be one more formula with the help of which you can calculate the EMF of the cell, right? Both in SRPs, both in SOPs, or you can keep one in SOP, one in SRP. The choice is all yours, but I would suggest just to remember this particular result. E0 cell is equal to E0 cathode minus E0 anode, where E0 cathode is SRP of cathode, E0 anode is SRP of anode. Right? I would suggest to remember this one. Perfect. Now guys, why am I telling you all this stuff? Because there's a logic behind that. For example, I'm writing something like this. Understand people, E0 of, let's say, A positive gives A. Let's say this value is equal to 1.1 volt. Let's say E0 of B positive gives B. Let's say this value is equal to 2.1 volt. So how many electrodes do we have? We have two electrodes. Let's say I'm connecting these two electrodes externally as well as internally. Yeah. My dear students, When I connected these two electrodes externally as well as internally, can I say I'll be getting one galvanic cell? I'll be getting a cell. Since a cell, a complete cell, consists of two electrodes, I took two electrodes, connected them externally as well as internally, I got one complete cell. If I ask you to calculate the standard EMF of the cell which we made over here, you will say E naught cell is nothing but E naught cathode minus E naught anode. So first of all, you have to understand among these two electrodes, which one is cathode, which one is anode. How you are going to check that? Say, +1 to 0, +1 to 0, decrease means reduction. So this is SRP. +1 to 0, decrease means reduction. So this is SRP. So I'm given with SRPs of both. Now among these two, which one has got more SRP? I'll say this SRP is more. The one that has got more SRP will undergo reduction, and reduction takes place at cathode. So this particular electrode is going to behave like the cathode, and this particular electrode is going to behave like the anode. So I identified in the cell which one is the cathode and which one is the anode. Since, my dear students, you got to know which one is cathode, which one is anode. So E naught cell has to be equaled. E naught cathode means SRP of cathode. SRP of cathode is 2.1 minus SRP of anode. SRP of anode is 1.1. The value comes out to be 1 volt. So this 1 volt is the standard EMF of the cell which we made over here. Am I clear with this? Am I clear with this, people? For example, let's say I'm writing something like this. E naught of, let's say I'm writing E naught of zinc gives zinc dye positive. Let's say it is equal to 1.1 volt. Or let's keep it as it is equal to 0.76 volt. And here I'm taking one more electrode. E naught of H positive gives H2, which is the hydrogen electrode. And you know, SRP as well as SOP of hydrogen electrode is 0. So how many electrodes we have? I've taken two electrodes, zinc and hydrogen. Zinc and hydrogen. Let's say these two electrodes I'm connecting externally as well as internally. Can I say I'll be getting a complete cell? I got a complete cell by connecting these two electrodes. After getting the complete cell, I want to calculate the standard EMF of the cell which I got, which is nothing but E naught cathode minus E naught anode. What is E naught cathode? This is the SRP of cathode. Now, among these two, which one is going to behave like cathode? Which one is going to behave like anode? See, guys, 0 to +2, increase. Increase means oxidation. So this is basically the SOP of zinc, right? And this is SRP of hydrogen electrode. SRP as well as SOP of hydrogen electrode has to be 0. Now, guys, SOP. Among these two, which one has got more SOP? Zinc has got more SOP. The one that has got more SOP will undergo oxidation easily. The one that undergoes oxidation easily, that's going to behave like anode. So this electrode here is going to behave like anode, and this electrode here is going to behave like cathode. Perfect. So E naught cell is equal to E naught of cathode, SRP of cathode. This is SRP of cathode, that's 0, minus SRP of anode. This is SOP of anode. What do I need? I need SRP of anode. So I'll change the sign. So it's going to be minus 0.76. So E naught cell here is going to be 0.76 volts. This is the standard EMF of the cell. I hope you got to know how to calculate the standard EMF of the cell. Right? Right, people? Now, you should be in a position to answer this particular question. Let's say I'm writing E naught of M gives Mn positive. Let's say it is equal to 3.1 volt. Let's say I've got one more electrode. E naught of N positive gives N is equal to 5.1 volts. These two electrodes which I have, let's say I'm connecting them externally as well as internally. And now I'm asking you, the cell which we got, calculate its E naught cell. You will say it is going to be E naught cathode minus E naught anode, right? Now, among these two, check which one is anode, which one is cathode. How exactly? 0 to plus N. 0 to plus N. 0 to plus N. Increase. Increase means oxidation. So this is SOP. Do I need SOP or SRP? I need SRP to check, right? So SRP of this electrode will be equal to minus 3.1 volt. +1 to 0. +1 to 0. Decrease. Decrease means reduction. So this already SRP. So which one has got more SRP? Minus 3.1 or 5.1? Which one is more SRP? Here the SRP is more. More SRP, more tendency to undergo reduction. So reduction takes place at cathode. So this is my cathode here. And I would say this is going to behave like my anode here. So I identified my cathode and anode. If I identified my cathode and anode, it's going to be SRP of cathode SRP of cathode is nothing but 5.1 minus SRP of anode. SRP of anode is minus 3.1. So minus plus 3.1. The value comes out to be 8.2 volts. This is the E0 cell. This is the standard EMF of the cell, which we made by connecting these two electrodes. I believe I'm clear to everyone. Yes? So this is how you calculate standard EMF for the cell. If you got to know how to calculate standard EMF of the cell, then my dear students, this is something which you should be easily solving. This is something which you should be easily solving. Look at the question. Standard oxidation potential values of zinc and iron are given. EMF of the cell is, understand. See guys, this is the net cell reaction which is given to me. Let me write it again. Zinc plus Fe di positive, it gives zinc di positive plus iron. This is my net cell reaction. Oxidation state 0, here plus 2, here plus 2, here 0, right? Check it out. 0 to plus 2, increase. Increase means oxidation. So this zinc is going to behave like the anode here. Plus 2 to 0, decrease in the oxidation state. Decrease means reduction. Reduction takes place at cathode. So I identified my anode and cathode. I identified my anode and cathode. My dear students, if I identified my anode and cathode, now E0 cell is nothing but E0 cathode minus E0 anode. Which one is my cathode? This is my cathode. SRP of cathode. SRP of cathode. SRP of iron here. This is the SOP. This is the SOP. I need SRP. SRP means minus 0.41 minus E0 of anode. SRP of anode. SRP of anode. SRP of zinc here. This is SOP of zinc. I need SRP, so minus 0.76. The value comes out to be plus 0.35 volts. So this is the E0 cell. Correct? I hope you got to know how to calculate the EMF of the cell under standard conditions, right? I hope you got to know how to calculate EMF of the cell under standard conditions. What is EMF? Maximum potential difference between the electrodes when no current is drawn from the cell, right? Whenever EMF comes to your mind, remember the example of battery which we got from the market. When battery was not in use, its potential difference was 5 volts between the electrodes. When it is under usage, its potential difference will keep on decreasing. When the battery was not in use, voltage at that time was maximum 5 volts. That maximum potential difference between the electrodes when the cell is not in use, we call that as the EMF of the cell. Yeah? Perfect, guys? Perfect. Now, there is one more important topic, that is E cell and spontaneity. E cell and spontaneity. This is one important topic, guys. E cell and spontaneity. Or you can say delta G versus E cell. Delta G versus E cell. What is this particular topic all about? What is this particular topic all about? See guys, understand what exactly I'm going to say, because this is something which is very important. Okay, E cell versus spontaneity. Understand. Let me talk about some interesting things over here. For example, I'm making your Daniel cell again. Let's say this is your Daniel cell. And in case of Daniel cell, this is your zinc electrode and this is your copper electrode. Zinc electrode, copper electrode. Connected externally with the help of what? With the help of emitter, and here you have introduced the salt bridge. This is your Daniel cell. This is your Daniel cell. This is your Daniel cell. My dear students, if you remember, in case of in Daniel cell, the movement of electrons was from zinc to copper. The movement of electrons was from zinc to copper. This was the movement of electrons from zinc to copper. Okay? Moment of electrons was from, the direction of the moment of electrons was from zinc to copper. And the direction of current was from copper to zinc in the external circuit. In case of what? In case of your Daniel cell. Now, my dear students, let me tell you, this Daniel cell, which is my system right now, this Daniel cell is under investigation right now. So this is my system. Any part of the universe that will be under investigation. That's what you call a system. So this Daniel cell is under investigation right now. It's my system. Okay. First of all, in the system, we have got two types of energies present. In the system, we have got two types of energies present. One is called as available energy. One is called as unavailable energy. In the system, we have got two types of energies present, available and unavailable. My dear students, this available energy is used for what? There is a work called as useful work. There is a work called as useful work, or you call it as a non-PV work. Non-PV work. For example, electrical work. Electrical work is the example of useful work. Electrical work is the example of non-PV work, right? Electrical work is the example of non-PV work. If you see in the Daniel cell, do you see electron is traveling from anode to cathode? If I look at this part of the circuit, in this particular part of the circuit, what is happening? Electrons are moving from anode to cathode. So can I say over here, electrical work is happening? I would say over here, electrical work is happening. Which is the example of what? Which is the example of non-PV work. You call that work as the useful work. You call that work as the useful work. You call that work as the useful work. Okay. My dear students, as I told you, system has got two types of energies, available, unavailable. This available energy which is present in the system, it is utilized for useful work. It is utilized for what? It is utilized for useful work. And what is the useful work happening over here? Electrical work is happening over here. The useful work which is happening over here, that's electrical work. System has two types of energies, available, unavailable. Leave unavailable aside. I've got nothing to do with this. But the available energy which is present in the system, it is utilized for what? It is utilized for useful work. So I would say system consumes its useful work. System consumes its available energy. System is going to consume its available energy to perform the useful work. To perform the useful work. To send the electron from anode to cathode. For example, let me make you understand like this. Let's say in the beginning, the system had 100 joules of available energy with it. Okay. After some time, when the system started working means when the system started producing current, after some time I analyzed, now the available energy present in the system is not 100, it's only 80 joules. Let's say in the beginning, system had 100 joules of available energy with it. Now when the system started working, when the Daniel cell started working, when it started producing current, after some time, let's say the available energy in it was just 80 joules. So what has happened to the available energy of the system? Available energy has decreased. By how much units? 20 joules. Available energy of the system has decreased. By how much units? 20 joules of available energy has decreased. Let me tell you, this available energy is utilized for useful work. That means initially the available energy was 100 joules. After some time it's 80 joules. That means 20 joules of available energy is utilized for the electrical work here. 20 joules of available energy is utilized for this electrical work here. Right? Electron is being sent from anode to cathode. So 20 joules of energy has been utilized to perform what? To perform the useful work, to perform the non-PV work, to perform the electrical work. Right? So again, I'm recapping the same things. System has got two types of energies, available and unavailable. Available energy is utilized for useful work. Available energy is consumed for useful work. Right? It's utilized for useful work. Perfect. In the beginning, system had, for example, 100 joules of available energy with it. After some time, 80 joules. So how much available energy has decreased? 20 joules. That 20 joules of available energy which has decreased. So that 20 joules of available energy would be consumed by the system to perform this electrical work, to perform the useful work. So can I say decrease in the available energy? Can I say decrease in the available energy of the system? decrease in the available energy is equal to the useful work, which is basically your non-PE work. Okay. And what useful work is happening here? Electrical work. Electrical work is happening here, right? Electrons are sent from anode to cathode. So system will be consuming its available energy to perform this work over here, to perform this electrical work over here. I hope this is clear. Right? Now guys, it's simple. Decrease in the available energy, I'll be representing with minus delta G. Right? Decrease in the available energy is represented by minus delta G is equal to useful work done by the system, which is basically what kind of useful work is happening here? Electrical work. How do you calculate electrical work? Q charge multiplied by potential difference. You must have studied this in physics, right? Electrical work is calculated with this formula. Okay. Now, my dear students, let's assume that n moles of electrons are exchanged between anode and cathode. Let's say n moles of electrons are exchanged, right, between anode and cathode. N moles of electrons are exchanged between anode and cathode. First of all, remember, charge present on 1 mole of electron is equal to 1 farad. Let me tell you that. Charge present on 1 mole of electron. Let me tell you, 1 mole electron carries how much charge? 1 farad. 1 farad is equal to what? It is equal to 96500 coulombs. Okay? If 1 mole of electron carries 1 farad charge, 2 moles of electron will carry 2 farads, 3 moles of electrons will carry 3 farads. So n moles of electrons will carry n farad. So I am assuming if n moles of electrons are exchanged, so how much charge is exchanged? I would say Q here would be equal to n farad. Q is equal to nf. Okay? So n farad of charge is exchanged. Perfect. So my dear students, look at this particular result. I'll write minus delta G is equal to, instead of Q, I'll write NF, and V is basically the potential difference, so which is nothing but your A cell. Perfect. So I got one very, very, very important result here. That is your delta G. That is your delta G. Delta G is equal to minus NF A cell. Delta G is equal to minus NF A cell. Or sometimes you can call it as W useful. They might ask you the question in this format. Calculate the useful work. Calculate W useful. Or they might ask you to calculate the non-PV work. Non-PV work is nothing but useful work only. That means you have to calculate delta G only. Right? Perfect. Is this clear, guys? Okay. Now guys, why am I discussing this stuff? This is the relation between delta G for the cell and EMF of the cell. Now why am I discussing this stuff? There's a reason for that. My dear students, one thing. Is it stuck or something? Is it lagging? Is it lagging, people? No, right? Can you let me know in the chats quickly if it is fine? All right. Look here now. See, guys. If I ask you one simple question, how do you make a galvanic cell? How do you make a galvanic cell? Your answer will be, we need to take 2 electrodes. We'll be taking 2 electrodes. We'll be connecting them externally and internally. We'll be getting a cell. We'll be getting a complete cell, right? You'll be taking 2 electrodes. Perfect. Connecting them externally and internally, you'll be getting one complete cell. No doubt you made a cell. No doubt you made a cell. But will that cell be working? Will that cell produce current? How you are going to check that? How you are going to comment on that? Whether the cell will be working or not? Whether the cell will be producing current or not? How you guys check that? My dear students, when you will be making a cell from two electrodes connecting externally and internally, when you made the cell, if spontaneously at anode oxidation takes place, at cathode reduction takes place, spontaneously, if it happens, that means if the cell reactions are spontaneous, if the cell reactions happen on its own, you just connect the two electrodes externally, internally. If at anode on its own oxidation takes place, on its own reductions takes place, you'll say that the cell reactions are spontaneous. And if the cell reactions are spontaneous, that means electrons will start moving from anode to cathode. Current will go from cathode to anode. That means the cell is working. So for the cell, for the galvanic cell to be working, for the galvanic cell to produce current, its cell reactions must be spontaneous. And for the cell reactions to be spontaneous, delta G for the reaction, it should be negative. Or let me write it properly, delta G should be negative. Delta G should be negative. Delta G for the reactions must be negative. Now what is delta G? Delta G is nothing but, it is minus NFE cell. So this particular term should come out to be negative. When can this whole term come out to be negative? This whole term can only come out to be negative if E cell comes out to be positive. If E cell comes out to be positive. So if I summarize this statement, I'll write it like this. If I summarize it, I'll write it over here like this. For the cell reactions, to be spontaneous, what does that mean? That means for the cell to be working. What does that mean? That means for the cell to produce current, like a normal galvanic cell, in which electrons move from anode to cathode, current move from anode to cathode to anode. I would say delta G has to be negative, or you can say E cell has to be positive. This is the condition which the cell has to follow, then only it will work like a normal galvanic cell. So for the cell to be working, for its cell reactions to be spontaneous, delta G for the reactions should be negative, or EMF of the cell should be positive. Then only I can say the cell reactions will be spontaneous, and I'll say the cell will be working like a normal galvanic cell, in which the direction of electrons will be from anode to cathode, and the direction of current will be from cathode to anode. Yes? Okay. Perfect. Now people, one more thing. Understand. If by chance delta G for the reactions, let's say you took two electrodes, you connected them externally and internally, right? Now, if delta G for the reaction comes out to be positive, right? If delta G comes out to be positive, what does that mean first of all? That means delta G is minus NFE cell. That means minus NFE cell is coming out to be positive. Minus NFE cell, when it can come out to be positive? This whole term can only come out to be positive when E cell is negative. And my dear students, you know, if delta G for the reaction is positive, I would say cell reactions are non-spontaneous. What does that mean? Cell reactions are non-spontaneous. What does that mean? That means the cell won't be working like a normal galvanic cell. It won't be producing current, right? Perfect. The third parameter. My dear students, if delta G for the cell comes out to be 0, that means minus NFE cell value is equal to 0. When is this particular thing possible? It is possible only if E cell is equal to 0. E cell 0 means potential difference between the electrode is 0. If potential difference between the electrode is 0, there will be no current. Cell won't be working. And this particular stage, when E cell becomes 0, this particular stage in the cell, when the EMF of the cell, when the potential difference between the electrodes, it becomes 0, we call that stage in the cell as equilibrium stage, which will be discussed in some time later on. We say the cell is at equilibrium. Okay. Right, people? Perfect. I believe these 3 points are clear to you. Now, from these 3 points, my dear students, you can easily check. You can easily check whether your cell will be working, whether its cell reactions will be spontaneous or not. And when the cell reactions are spontaneous, that means the cell is producing current. And the direction of current will be from cathode to anode. I believe I'm clear. I believe I'm clear. Yes? Perfect. Now, my dear students, one more thing. One more thing. I told you your delta G is equal to minus NF E cell. Correct? If I write the same equation under standard conditions, so at that point of time, I won't be using delta G, I'll be using delta G naught is equal to minus NF. I won't be using E cell, I'll be using E naught cell. This is the result which works at standard conditions, right? Under standard conditions, you can say delta G naught is equal to minus NF E naught cell. Okay. One more thing, guys, which I would want to share with you. What is that? See, you know, delta G is equal to minus NF E cell, or I can say E cell is equal to delta G minus divided by NF, right? Now, first of all, if you have studied thermodynamics anytime soon, you should be knowing delta G. It is an extensive property. And this numerator, the denominator N, it is also an extensive property. It is also extensive in nature. What is, first of all, the extensive property? Extensive property means these are the properties of the system which depends on the size of the system. Those properties of the system which depends on the size of the system, right? You call them as the extensive properties. Those properties of the system which depends on the amount of substance present in the system, you call them as the extensive properties. So this is extensive, this is extensive. Maybe you would have studied sometimes that division of extensive properties. Division of extensive properties. Division of extensive properties makes the new property as intensive. And what is an intensive property? Intensive property is basically the property of the system which does not depend on the size, which is size independent. So if this is extensive, this is extensive, that means E cell becomes intensive. So remember, delta G, it is basically your extensive property. And when you talk about your E cell, it is basically which property? It is basically intensive property. Extensive properties are the ones which are size dependent. Intensive properties are the ones which are size independent. And my dear students, let me tell you, extensive properties can be directly added or subtracted. Extensive properties can be directly added or subtracted. Let me tell you, intensive properties cannot be directly added or subtracted. My dear students, from this particular statement, a question is asked. I'll let you know that question in some time. Before that, let's solve one more simple question. It's a very simple question, and I believe you are in a position to solve this particular question on your own. Check it out. The standard EMF of the galvanic cell. So EMF E naught cell, standard EMF E naught cell is given. Calculate delta G naught for this particular cell. First of all, for this cell, what is the value of N? N value is 2. So delta G naught has to be equal to minus NF E naught cell. Simple formula based. So delta G naught has to be equal to minus N value is 2. Faraday is constant. F is 96500 coulombs. E naught cell is given to me as 1.1. But you have to get the answer in kilojoules per mole. You have to get the answer in kilojoules per mole. You used all the parameters as per SI system. You used all the parameters as per SI system. What is first of all delta G? Delta G is useful work. Delta G is work. So whatever are going to be the units of work, same are going to be the units of delta G. So delta G unit here will be as per SI system, that is joules. Because you used every parameter as per SI system, so delta G will be coming as per SI system as well. But do I have to calculate delta G in joules? Do I have to calculate delta G in joules? No, I have to calculate delta G in kilojoules. So I'll be dividing it with 1000. then the answer will be coming in kilojoules over here. Is it clear, people? Is it clear, people? This sort of a question you should be easily solving from now on. Similarly, if you look at this question, it's again the similar type of question. Again, the similar type of question, people. Calculate delta G naught for the cell. We are given with a cell reaction. Some E naught values are given, right? And what are we supposed to calculate? We are supposed to calculate delta G naught. How do I calculate delta G naught? My dear students, if you talk about delta G naught, you know it. Delta G naught is nothing but minus NF E naught cell. Correct? So first of all, what is the N value for this reaction? N value. I have already taught you how to calculate N, how to calculate QC, etc., right? Yes, people? What is the N value for this particular reaction? N value here, see, make this as the reference. 1 mole is losing 2 moles of electrons. N is 2 here. N is 2 here, right? If N is 2, Faraday's constant already you know, that is 96500 coulombs. Now, one term is missing, that's E naught cell. How do we calculate E naught cell? This is also taught. E naught of cathode minus E naught of anode. So first of all, check which one is your cathode and which one is your anode. Check which one is your cathode and which one is your anode. My dear students, this cobalt, 0 to plus 2, increase in the oxidation state. 0 to plus 2, increase. Increase means oxidation. Oxidation takes place at anode. So this is my anode and this is my cathode. So I identified anode and cathode. So let's calculate the E naught cell first. E naught cell is equal to E naught of cathode, E naught of this cerium, E naught of cathode. Say, plus 4 to plus 3, decrease means reduction. So this SRP. So SRP of cathode is 1.1 minus SRP of anode, plus 2 to 0, decrease. Decrease means reduction. So SRP only. So it's 0.1. The value comes out to be 1 volt. So this E naught cell. If you calculated E naught cell, therefore delta G naught has to be equal to minus. What is the value of N? N is 2. Faraday's constant, 96500 coulombs. E naught cell, 1 volt. Since you used all the parameters as per SS system, so delta G will be in joules. If you want delta G in kilojoules, so divide with 1000, the answer will be in kilojoules per mole. Right? Perfect. उर्दू में ट्रांसलेट करो. बेटा पहले तू चैनल का नाम पढ़ के आए, ठीक है? चैनल का नाम पढ़ के आए, उसके बाद कमेंट किया कर. Perfect, people? I hope this sort of a question you should be in a position to do on your own. Similarly, from delta G only, there is one more question which is asked. This sort of a question can be easily asked. Yeah? This sort of a question can be also asked. And how do we solve this sort of a question? How do we solve this sort of a question? My dear students, I'm given 2 reactions. Their E values are given to me. X volt, Y volt. Right? Their E values are given to me. I'm supposed to calculate E value for this particular reaction. I'm supposed to calculate E value for this particular reaction. Let me call this as reaction number 1. Let me call this as reaction number 2. Let me call this as reaction number 3. So I'm given with the E values for first and second reaction. I'm given with E values for first and second reaction. I'm supposed to calculate E for the third reaction. I'm supposed to calculate E value for third reaction. Remember, my dear students, that reaction whose E value is to be calculated. That reaction whose E value is to be calculated. You are supposed to make that reaction out of those reactions whose E value will be given to us. Remember this stuff. The reaction whose E value is to be calculated. Make that reaction out of those reactions whose E is given. Now, how exactly you are going to make this reaction? See, guys, if I do one thing, if I subtract second equation from the first equation, if I subtract second from first, when I subtract second from first, what do I get? See, I'll be getting something like this. Fe tri positive, 3 electrons minus 2 electrons comes out to be 1 electron. And this becomes minus Fe di positive. Fe cancel. So on this side, nothing. So I'll be writing Fe tri positive plus 1 electron. It gives Fe di positive. Look at this particular reaction. Was I supposed to make this reaction? Yes, I was supposed to make this reaction. I was supposed to make this reaction only. Check it out. Check the third reaction. I was supposed to make this reaction only. How did I make this reaction? How did I make this reaction? My dear students, I got third reaction when I subtracted second from first. When I subtracted second from first. Now, if you're thinking, you'll write it like this now. E3 is equal to E1 minus E2. Then you are doomed. Why is that? Because I told you already. EMF is the intensive property and you cannot add or subtract them directly. Delta G is the extensive property. You can add or subtract them directly. So, this particular question you are not going to solve on the basis of E. You will be solving this particular question in terms of delta G. So, you'll be writing, instead of 3, you'll be writing delta G for the third reaction is equal to delta G for the first one minus delta G for the second one. Right? Perfect. Since we are using the standard conditions, so you can use standard conditions. Delta G3 is nothing but minus NF E03 is equal. Delta G1 is equal to minus N1F E01 minus delta G2 is minus plus N2F E02. So first of all, F everywhere cancelled, multiply throughout with minus. So finally, I'll be getting E03 is equal to N1 E1 minus N2 E2 divided by what? Divided by E3. Not. Perfect. Now people, E03 has to be equal to N1. N1 means how many electrons exchange in the first reaction? 3. So 3 times E01 is X. So 3X minus N2. How many electrons in the second reaction? 2. So 2 multiplied by Y divided by E03. Sorry, this is not E03 here. This is N3 here. This is N3 here. N3 in the third reaction, 1 electron. Perfect. So the answer is going to be in volts. So my point of showing this sort of equation is whenever this sort of equation is to be asked, do not solve the question on the basis of E. Whatever operation you do to the reactions, same operation you'll be doing with the delta G values, not with the E values. Why is that? Because delta G is extensive. You can add or subtract the extensive properties directly. E is intensive. You cannot add or subtract the intensive values directly. Okay? Perfect. Now, similarly, my dear students, I believe you should be in a position to solve this sort of equation on your own. This should be solved. This should be solved. Some reactions are given. Their E0 values are given. One reaction whose E0 is to be calculated. So the reaction whose E0 is to be calculated, we are supposed to make that reaction out of the given ones. Yeah? Perfect. See guys, how do I make them? First of all, this is in +7 oxidation state. Here it is in +6. So +7 to +6. Decrease in the oxidation state means reduction, gain of electrons. So I would say MnO4 negative will be gaining 1 electron, getting converted into MnO4 di-negative. Look here, +6 to +4. Decrease means reduction. So it will be gaining 2 electrons, getting converted into this one. This is +4. So +4 to +2. Decrease. Decrease means reduction, gain of electrons, 2 electrons. Similarly, +7 to +2. It will be gaining 5 electrons. Perfect. The reaction whose E value is to be calculated, we need to make that reaction out of the given reactions. Calling this as reaction number 1, calling this as 2, calling this as 3, calling this as 4. How do we make the fourth reaction? Just look at it. The reaction which we have to make, in that reaction there should be 5 electrons. How can we get 5? 2, 4, 5. If I add first 3. If I add 1, 2 and 3. So this term gets cancelled. This term gets cancelled. 2 plus 2 plus 1 comes out to be 5. So MnO4 negative plus 5 electrons gives Mn di positive. So I would say fourth reaction I'm getting 1 when I'm adding 1, 2 and 3. Now, the operation which we are doing with the reactions, that operation you are not going to do with their E0 values. You are going to do with the delta G values. So I would say this is going to be delta G for the fourth is equal to delta G for the first one, delta G for the second one, delta G for the third one. Now, delta G for the fourth one is nothing but minus N4FE4 is equal to minus N1FE1 minus N2FE2 minus N3FE3. So F everywhere gets cancelled. So I would be getting the value of E4 from here. I would say E4 is equal to, E4 is equal to, it's going to be N1 E1 plus N2 E2 plus N3 E3 divided by what? Divided by N4. Perfect. Now people, what is N1? N1 is 1, N2 is 2, N3 is 2, N4 is 5. Right? So I would say E4 would be equal to N1 into E1. So 1 into 1 comes out to be 1 plus N2 E2. 2 multiplied by 2 comes out to be 4 plus N3 E3. 2 multiplied by 3 comes out to be 6 divided by N4. N4 is 5. So it's going to be 6 plus 4 plus 1, 11 divided by 5. 11 divided by 5, which comes out to be 2.2 volts. Perfect. So this is something which I was supposed to calculate. Am I clear with this? Am I clear with this, people? Yes, I believe you can easily solve this sort of a question on your own. There are some people who have come in the chats. Let me block them. Hide user on the channel, done and dusted. Adil guy was there. Over. Is there any other spammer, guys, who is irritating? Who is this Rifat Ara? My God, such a fancy name. Such dull activities. Done. Is doomed. Who's the next one? Tell me. Give me the names. Give me the names. Quick. Who are these? Give me the names quickly, quickly, quickly. I'll start again, quickly. Whosoever is disturbing in the chats, tell me the names. Some Sadia girl is there, huh? Wait, let me find who Sadia is, where she is. You don't find Sadia in the chats, though? Maybe she's gone. No. Might be before, long back. In Urdu, Sadia is written. Where is Urdu? Any Sadia in Urdu language? Okay, this girl. Welcome. The block list of the channel. Done. Who else? Quick. Who else? Who else? Quick, quick, give me the names. Quick. Yeah? Done? Remove on. Now they can go to some other channel. They can chit chat, whatever they want to do. You're free from our side. Don't ever come to Unacademy NEET English. All right, people. So I believe all the stuff is clear. You got to know the relation between delta G and A cell, right? And I hope you remember the things. In order to check whether the cell will be working, you have to check the value of delta G or E cell. If delta G is negative or E cell is positive, cell reactions will be spontaneous. If delta G is positive or E cell is negative, cell reactions will be non-spontaneous, right? Perfect. I believe this stuff is clear. Now. My dear students, one of the most important topics of this particular chapter, right? That is your Nernst equation. That is your Nernst equation. First of all, before showing you the Nernst equation, let me tell you where do we use the Nernst equation. Where do we use the Nernst equation? My dear students, let me tell you Nernst equation, which I'm going to give you now, okay, is used to calculate a lot of things. It is used to calculate a lot of things. For example, since you know how to calculate the standard EMF of the cell, you know how to calculate standard EMF of the cell under standard conditions. That means E0 cell, which is E0 cathode minus E0 anode. Since you know that, right? But What if the conditions were different? What if the conditions were not standard? What if the conditions were not standard? What are standard conditions? Temperature constant, generally 25. Pressure 1 bar, concentration 1 molar. If the concentration of the electrolyte is not 1 molar, for example, the concentration of electrolytes were 2 molar, that means it's not a standard condition. That means it's not a standard condition. It is a non-standard condition. And in order to calculate EMF of the cell, in order to calculate EMF of the complete cell under non-standard conditions, I'll be using Nernst equation. Okay, I'll be using Nernst equation. So the first usage of Nernst equation is to calculate EMF of a complete reversible cell under which conditions? Under non-standard conditions. Under non-standard condition. First one. Second one. See, SOPs and SRPs of all the elements we already know as given by the electrochemical series. Right? SOPs, SRPs. That means oxidation potential and reduction potential of some electrode under standard conditions. Oxidation potential or reduction potential of the electrode under standard conditions. We know them already as per your this is concerned, as per your electrochemical series is concerned. But what if condition was not standard? What if condition was not standard? What if condition was not standard? At that point of time, I'll be again using Nernst equation to calculate the reduction potential, to calculate the reduction potential of a half cell. Half cell is what we call as electrode. Half cell is basically electrode, okay? Electrode is called as half cell. To calculate the reduction potential of the half cell under non-standard conditions. Under non-standard conditions. Similarly, it is used to calculate oxidation potential. It is used to calculate oxidation potential of the half cell. Of the half cell. Again under non-standard condition. So these are the three important uses of this particular cell. Particular equation. Now, understand what this equation is all about. See guys, let's have a look on the Nernst equation now. My dear students, in order to get the Nernst equation, I'll be writing one equation which maybe you would have studied in thermodynamics sometimes, right? If not, then remember the equation directly. Remember the equation directly. Delta G is equal to delta G naught plus RT ln of QC. This is one equation. Delta G is equal to delta G naught plus RT ln of QC. Now delta G for the cell already we know. That is minus NF E cell. Delta G naught already we know. Minus NF E naught cell. Plus RT and its ln of QC. Let me divide throughout by minus NF. If I divide throughout by minus NF, it becomes like this. I divided throughout by minus NF. Now people, understand. You can write it like this. E cell is equal to E naught cell. Now here you have got ln of QC. Convert this into log. It's going to be 2.303 RT divided by NF. Now it's going to be log of QC. My dear students, this equation which you got over here, this is something which you call as Nernst equation. This is something which you call as Nernst equation. And in this particular equation, if I take the value of R as 8.314 joules per Kelvin per mole, if I take the value of Faraday's constant as 96500 coulombs, if I take temperature 25 degrees centigrade, that means your room temperature, which is 298 Kelvin, right? If I put all these parameters in this equation, what do I get? I get a simplified form of Nernst equation. If I put all these parameters here in this equation, I get a simplified form of Nernst equation, which is E cell is equal to E naught cell minus 0.0591 divided by N and its log of QC. And this is the equation which I'll be using in majority of the questions. E cell is equal to E naught cell minus 0.0591 divided by N log of QC. Now, my dear students, this particular equation, it has got how many uses? 3 uses. First use. If you want to calculate oxidation potential of the half cell under non-standard conditions. If you want to calculate oxidation potential of the half cell, oxidation potential of the electrode under non-standard conditions, then instead of E cell, you'll be writing EOX is equal. Instead of E naught cell, you'll be writing E naught OX minus 0.0591 divided by N and its log of QC. This equation I'll be using to calculate oxidation potential of the electrode under non-standard condition. This represents oxidation potential of electrode or half cell under which condition? Under non-standard condition. This E naught X represents standard oxidation potential of the half cell. N represents moles of electrons exchanged, and QC already you know. Similarly, my dear students, in order to calculate the reduction potential of the half cell, in order to calculate reduction potential of the electrode under non-standard conditions, then instead of E cell, I would write ERED is equal to, instead of this, I'll be writing E naught RED minus 0.0591 divided by N, and it's going to be log of QC. Okay, so this ERED is something which we call as reduction potential of the half cell under what? Under non-standard conditions. What is this E naught RED here? This is SRP of the half cell. Perfect. And my dear students, whenever you are supposed to calculate EMF of the cell under non-standard conditions, then you have to use this particular result. This E cell here represents EMF of the cell, EMF of the complete cell under non-standard conditions. This is your standard EMF, which is nothing but E naught cathode minus E naught anode. Perfect. So like this, you are going to remember them. Okay. So three things: to calculate oxidation potential of the half cell under non-standard conditions, to calculate reduction potential of the half cell under non-standard conditions, to calculate the EMF of the cell, EMF of the complete cell under non-standard conditions. I'll be using the Nernst equation. Okay. I'll be using the Nernst equation. Perfect, people. Now. Let me show you in detail now how to use the Nernst equation for the half cells. Half cells means electrodes. Let me show you how do we use Nernst equation for the half cells, for the electrodes. Okay. My dear students, for example, imagine that this is the container. In this container, for example, what do we have? For example, we have got Mn positive ions in the container, Mn positive ions, and there are some anions as well. And I'm assuming there are equal number of cations and anions in this solution. So this solution is neutral right now. For example, I'm introducing a metal rod. I'm introducing a rod M solid. So should I be calling this as electrode? Yes, I'll be calling this as electrode. Yes, I will be calling this as the electrode, people. Yes, I'll be calling this as electrode. Now, this particular electrode, it can behave like anode as well as cathode. You know it. It can behave as anode as well as cathode. First of all, when this electrode behaves like anode, what is going to happen? Oxidation will happen. This rod, it is made up of M atoms. This rod is made up of M atoms, and those M atoms will undergo oxidation. They lose some electrons. Those M atoms, M solid, will be losing certain electrons, getting converted into Mn positive, right? How many electrons it will lose? N electrons, right? Perfect. This is the reaction which will happen when this particular half cell, when this particular electrode is going to behave like the anode, because at anode oxidation takes place. How many moles of electrons got exchanged here? N moles of electrons got exchanged. If I ask you to write the QC expression, start with the product. It is concentration of Mn positive raised power 1 divided by, this is solid, nothing to do with it. Now, write the Nernst equation. I want to calculate what? Since I made sure that this electrode behaves like the anode, at anode oxidation takes place, right? Concentration here is, for example, P molar. It is not 1 molar. Concentration of electrolyte here, for example, is C molar. It is not 1 molar. So the electrode is not present under standard condition. It is present at non-standard condition. And at non-standard conditions, I'm asking you to calculate the oxidation potential of this electrode. At non-standard conditions, I'm asking you to calculate oxidation potential of this electrode. So you'll be writing the Nernst equation like this. EOX is equal to E naught OX minus 0.0591 divided by N log of QC, that is concentration of Mn positive. This is how you are going to write Nernst equation for the half cell when its oxidation potential under non-standard conditions is to be calculated. I believe I'm clear, right? I believe I'm clear. Now guys, if you think logically, one important thing. My dear students, imagine I'm increasing the concentration of electrolyte here. If I increase the concentration of electrolyte in the container, if I increase the concentration of electrolyte in the container, what will happen? If I increase the concentration of electrolyte in the container, I would say the concentration of Mn positives in the container will increase. Absolutely. The concentration of Mn positives in the container will increase. If this term is increasing, I would say this entire term will increase. And if this entire term is increasing, if this whole term is increasing, the difference between these two will decrease. What does that mean? That means oxidation potential of the half cell will decrease. So what could you conclude from here? What could you conclude from here? More the concentration of electrolyte in the container, lesser the oxidation potential of the half cell. Or you can say oxidation potential of the half cell is inversely proportional to concentration of electrolyte in the container. So my dear students, if you sometimes want to vary the oxidation potential, if you sometimes want to vary the oxidation potential of the electrode, you can vary it with the help of the electrolytic concentration. Okay? What does it mean? See, it's pretty much simple. For example, imagine that this is your zinc rod. Imagine that this is your zinc rod. Let's say you are keeping the concentration of ions here as 10 molar. Perfect. Now, again, for example, you have taken a zinc electrode. Again, this is a zinc electrode, for example. Here, the concentration of electrolyte is 100 molar. So, difference lies in concentration. Wherever concentration of electrolyte is more, its oxidation potential will be less. No doubt, both the ones are the zinc electrodes, but oxidation potential of this zinc electrode will be less than that of this. Why is that? Because I've kept electrolytic concentrations different. Yeah? I believe this is clear. Now, my dear students, this was the scenario when I made the electrode to behave like the anode. Now, the electrode can work like cathode as well. The electrode which worked like anode, it can work like cathode as well. Absolutely. If it works like the cathode, what's going to happen? If it behaves like the cathode, if the same electrode behaves like the cathode, reduction will happen. Reduction will happen. Right? Reduction will happen. So, reverse the reaction. When you reverse the reaction, it's going to be like this. Mn positives in the container, they are going to collide with the rod, take N electrons from the rod, get converted into M solid. Now, get the QC value. QC is going to be nothing to do with this 1 divided by concentration of Mn positive raised per stoichiometric coefficient 1. Since you made electrode to behave like cathode, yeah, at cathode, reduction takes place. Technically, I want to calculate a reduction potential of the half cell under non-standard conditions. Like I calculated the oxidation potential of the half cell under non-standard conditions. In the similar way, now I want to calculate reduction potential of the same half cell under non-standard conditions. So I'll be writing Nernst equation like this. ERED is equal to E naught RED minus 0.0591 divided by N log of QC, which is 1 upon concentration of Mn positive. This is how you guys are going to write the Nernst equation for the electrode when it behaves like a cathode. This is how you write the Nernst equation when you have to calculate the reduction potential of the half cell under non-standard conditions. I believe this is clear. Now, one thing, guys, understand. If, for example, you increase the concentration of electrolyte in the container, if you increase the concentration of electrolyte in the container, what will happen? I would say concentration of Mn positives in the container will increase. If the concentration of Mn positive is increasing in the container, this whole term will decrease. If this whole term is decreasing, if this term is decreasing, that means difference between these two will increase. What does that mean? That means reduction potential will increase. So ERED will increase. So that means on keeping the concentration of electrolyte in the container high, the reduction potential of the half cell, the reduction potential of the electrode will be higher. Yes, so I would say the reduction potential is directly proportional to what? The concentration of electrolyte in the container. Okay? Perfect. Tell me one thing. Imagine I have zinc electrode. Imagine I have got one more zinc electrode. 2 zinc electrodes I have. 2 zinc electrodes I have, people. 2 zinc electrodes. In the first zinc electrode, the concentration of zinc sulfate in the container is 2 molar. In the second electrode, the concentration of zinc sulfate in the container is 10 molar. Whose reduction potential will be more? Zinc electrode where the concentration is 2 molar, or zinc electrode where the concentration is 10 molar. What do you think? What do you think? Quick. Quick, people. Whose reduction potential will be more? Quickly in the chats, everybody. Exactly, it's 10 molar, right? Yes. More the concentration of electrolyte in the container, more is going to be the reduction potential of that electrode. Simple. And if reduction potential is more, so oxidation potential has to be less. So this was how to write the Nernst equation for half cells, right? When it behaves like the anode, when it behaves like the cathode. Now here, one more thing I'm going to show you. What is that? I'm showing you Nernst equation for hydrogen electrode. How do we write Nernst equation for hydrogen electrode? This is also important. How do we write Nernst equation for hydrogen electrode? Understand, guys. We already saw how hydrogen electrode is made. Now, I'm not going to make the hydrogen electrode in that detailed manner. Let me make it like this only, in the simplest way. Let's say this is the container. In this container, there are H positive ions. Concentration of H positive is C molar here. Okay, and here you have got hydrogen rod, for example. And let's say this hydrogen rod was made with the help of platinum solid under the pressure of, let's say, P bar. Or let's say the pressure at which hydrogen gas was introduced, that was 1 bar. For example, yeah. For example, if I ask you whether this is hydrogen electrode or not, hydrogen rod in the solution containing H positive ion. So this is the hydrogen rod. It is the hydrogen rod. I mean, it is the hydrogen electrode. Now this hydrogen electrode, it can behave like anode as well as cathode. If by chance it behaves like anode, my dear students, if you remember, I have told you, when hydrogen electrode behaves like anode, what happens? Oxidation. H2 gets converted into 2 times H positive. If you remember the reaction, H2 gas gets converted into 2 times H positive aqueous, and with that you write 2 electrons. This is the reaction when hydrogen electrode behaves like the anode, right? N value here is 2, and QC, if I want to write, it's going to be concentration of H positive raised power 2 divided by partial pressure of H2 gas. Partial pressure of H2 gas is nothing but 1. Partial pressure of H2 gas, the pressure at which H2 gas was introduced is 1 bar. Yeah? Perfect. So this is concentration of H positive gas square. Now, if you want to write the Nernst equation, since you made the hydrogen electrode to behave like anode, at anode oxidation takes place. So technically, I want to calculate oxidation potential of the hydrogen electrode is equal to E naught OX minus 0.0591 divided by N log of QC. This is how you write. Okay. So EOX is equal to, what is the SOP of hydrogen electrode? Standard oxidation potential of hydrogen is 0. So this is 0 minus 0.0591. What is the N value? That's 2 log of QC. What is the QC value? QC is concentration of H positive का square. Log of M raised power N is N log M. So 2 cancels. 2 cancels. So minus 0.0591. This is log of H positive concentration. Now people, if you look carefully here, I can write something like this. If you look carefully here, I can write EOX, oxidation potential of the hydrogen electrode, is equal 0.0591. I'm writing as such. Minus log of H positive is something which you call as pH. Minus log of H positive is something which you call as pH. So this is the result with the help of which you can calculate oxidation potential of the hydrogen electrode under non-standard condition. But remember, at the pressure of 1 bar. At the pressure of 1 bar. If this is the oxidation potential of the hydrogen electrode, what will be the reduction potential of hydrogen electrode, people? Reduction potential of hydrogen electrode will be just minus of this. So it will be minus 0.0591 multiplied by pH of the solution. What can you conclude from here? See, more the pH of the solution, more will be the oxidation potential of the hydrogen electrode, right? I can say oxidation potential of the hydrogen electrode is directly proportional to pH of the solution. Or you can say reduction potential of the hydrogen electrode is inversely proportional to pH of the solution, because the sign here is minus. Okay, remove these 2 points as well. I believe I'm clear with this, right? So my dear students, this is how you do what? This is how you calculate the oxidation and reduction potential of hydrogen electrodes under non-standard condition. Perfect. Perfect, guys. If you change the pressure, then these results will be invalid. Then you have to follow the general procedure. You cannot neglect this partial pressure of H2 here. Okay, you have to follow the general procedure. I'll show you in the questions. Let me solve certain questions first so that you will at least have an idea of what all things are we doing. Okay, let's solve some of the questions. Look at this question, guys. Look at this question. Let's split this session into 2 parts. Why? Why do you want me to split the session into 2 parts? Do you want the session in 2 parts? Is that? Can you let me know in the chats? Do you want this session in 2 parts, this electrochemistry? Whatever you say, it's okay. Whatever you say. No, right? We are not splitting it. We are not splitting it. We are not splitting it, okay? Listen now. Okay, calculate the oxidation potential of the following half cell. Look at the half cell, guys. Look at the half cell carefully. So as per the question, look at the half cell. Half cell means electrode. So you have taken FeSO4 here. You have taken ferrous sulfate, FeSO4. Now this FeSO4 in the solution, it would have dissociated as Fe di positive and SO4 di negative. What concentration of FeSO4 you have taken over here? You have taken 0.1 molar concentration. This will be 0 in the beginning. This will be 0 in the beginning. At time t is equal to 0. Now imagine this FeSO4. Imagine this FeSO4 has got completely dissociated into its ions. So I'll be left with nothing. 1 mole gives 1, 0.1 gives 0.1. Similarly, 1 mole gives 1, 0.1 gives 0.1. So what did I get first of all? I got the concentration of ions in the solution. I got the concentration of ions in the solution. Now, people, you're introducing iron rod here. You're introducing iron rod here. So, do you see? You have introduced iron rod into the solution containing its own ions. And the concentration of Fe dye positive in the solution is 0.1 molar. What do we have to calculate? We have to calculate oxidation potential of this half cell. We have to calculate oxidation potential of this half cell. Understand? This is 0. Iron here is in +2. So, in order to calculate oxidation potential, I'll make sure that electrode behaves like anode, because at anode oxidation takes place. So, the reaction is going to be Fe solid 0 to +2. Increase. Increase means oxidation, loss of electrons. Fe solid will be getting converted into Fe dye positive aqueous plus how many electrons? 2 electrons. This will be the reaction when this electrode will be behaving like the anode. Yeah? This will be the reaction when the electrode will be behaving like the anode. Oxidation is taking place. Now, what is the value of N here? N value is 2. What is the QC value? QC is going to be concentration of Fe dye positive raised power 1 divided by it's solid, nothing to do with it. And what is the concentration of Fe dye positive in the solution? That is 0.1 molar. 10 raised power -1. It's QC. Now, what do you have to calculate? Oxidation potential. So use the Nernst equation. Oxidation potential of this half cell when the concentration here is 0.1 molar. When the concentration here is 0.1 molar. That means standard or non-standard. At standard conditions, concentration is 1 molar. Here the concentration is kept as 0.1 molar. So condition is not standard, it's non-standard, right? So people, oxidation potential of the half cell under non-standard conditions, when the concentration of Fe dye positive in the solution is 0.1 molar, will be equal, as per the Nernst equation, it will be equal to E naught OX minus 0.0591 divided by N, and it's going to be log of QC, right? So EOX is equal to E naught OX, which is SOP. E naught OX, which is SOP. Check whether this is SOP. +2 to 0. +2 till 0. Decrease in the oxidation state means reduction. So this SRP, what do I need here? I need SOP. So reverse the sign. So it is plus 0.44 minus 0.0591 divided by N value. N value here is 2. Right? N value here is 2. Log of QC. QC is how much? 10 raised power -1. Now a bit of calculation is needed. 0.44 minus 0.0591 divided by 2. Log of m raised power n is n log m. So -1 comes to the front, so plus. Log 10 is 0. Solve this equation and get the answer in volts. This is going to give you the oxidation potential of the half cell. This is going to give you the oxidation potential of the half cell when the concentration of Fe dye positive in the solution was 0.1 molar. If they ask you to calculate the reduction potential of the same half cell, whatever answer you'll be getting from here, just reverse its sign. Just multiply that answer with minus sign. You'll be getting the reduction potential of the half cell, the same half cell. I believe this is clear. One simple question this was. Moving on to the next one. Moving on to the next one. Look at this question, guys. Look at this question. As per the question, if you look carefully, in the container you have kept HCl. In the container you have taken HCl. So this HCl would have dissociated as how? This HCl would have dissociated as H positive plus Cl negative. Initially, its concentration was kept 0.1 molar. So this is 0, this is 0. Now, when the whole HCl got dissociated into its ions, so this will be 0. 1 mole gives 1. 0.1 gives 0.1. Even this is 0.1. So what did we get? I got, first of all, the concentration of ions in the container. I got, first of all, the concentration of ions in the container. Now, my dear students, over here, we have introduced a platinum rod on which hydrogen gas was introduced. So it becomes hydrogen rod. At a pressure of what? At a pressure of 10 atm. At a pressure of 10 atm. If the pressure was 1 atm, then you already had the result. You already had the formula in terms of pH. But here, pressure is not 1 atm. Pressure is 10 atm. So I'll go with the general approach. What do I have to calculate? Oxidation potential. In order to calculate oxidation potential of this half cell, I'll make sure that this half cell behaves like the anode. And my dear students, when this half cell behaves like the anode, what happens when hydrogen electrode behaves like anode? H2 gives 2 times H positive plus 2 electrons, right? H2 gas, it gives 2 times H positive aqueous plus how many electrons? 2 electrons. Okay, so N value, that is 2. Okay, get the QC. QC is nothing but concentration of H positive gas square divided by partial pressure of H2. What is the concentration of H positive in the solution? 0.1 molar. That means 10 raised power minus 1 का square divided by partial pressure of H2 is nothing but 10. So this becomes 10 raised power minus 2 divided by 10. So it will be 10 raised power minus 3. This is QC. If you got QC, what do I have to calculate? Oxidation potential. Use the Nernst equation. EOX is equal to E naught OX minus 0.0591 divided by N log of QC. So E naught OX is basically the SOP, standard oxidation potential of hydrogen electrode, people. That is 0. Minus 0.0591. N value here is 2. Log of QC. QC is 10 raised power minus 3. Log of M raised power N is N log M. So minus 3 comes to the front. So minus minus plus. So it becomes 0.0591 divided by 2 multiplied by 3. Log 10 is 1. And the answer will come in volts. Yes. Perfect, people. Is it clear? Is it clear? Is it clear? Quick, quick, quick. Is it clear? Is it clear? Look at this question. Look at this question. Calculate the oxidation potential of the half cell. Again, we have to calculate oxidation potential. Again, we have to calculate oxidation potential. So, we'll again make sure the electrode behaves like the anode. At anode, what happens? Oxidation takes place. But people, if you look carefully, this is 0. And here it's minus 1. 0 to minus 1 means decrease. Decrease means reduction. So, in order to make sure that this electrode behaves like the anode, we have to write the oxidation reaction. In the oxidation reaction, oxidation state should increase. But here, if you go from 0 to minus 1, it is decreasing. It is decreasing. Decrease means reduction. Right? But we have to write oxidation reaction. So, I'll write the reaction in reverse manner. I'll write 2 times Cl negative. I'll write 2 times Cl negative gives Cl2 gas plus 2 electrons. Did you understand how did I write the reaction? Say yes or no in the chats. Did you understand how did I write the reaction? I need to calculate oxidation potential. So I want this electrode to behave like anode. Oxidation. Oxidation means increase. Right? I have to show increase in oxidation state. Say minus 1 to 0. I have shown increase in oxidation state. I've shown increase in oxidation state. Now guys, rest everything is done. N value here is 2. QC value is going to be, it's going to be partial pressure of Cl2 raised power stoichiometric coefficient, concentration of Cl negative raised power stoichiometric coefficient. What is the partial pressure of Cl2? It is 10. What is the concentration of Cl negative? It is 0.1, means 10 raised power minus 1, a square. It becomes 10 divided by 10 raised power minus 2. So, it becomes 10 raised power 3. Simple. 10 raised power 3. What do you have to calculate? Oxidation potential. So write the inverse equation. EOX is equal to E naught OX minus 0.0591 divided by N log of QC. Perfect. So E naught OX means SOP. Check it. Minus 1 to 0. Increase in the oxidation state means oxidation. So this is SOP. I need SOP only. So minus 1.36 minus 0.0591. N value is given to me as per the question, it seems. That's 2 log of QC. QC is 10 raised power 3. I believe this calculation you can easily do now. Yeah? I believe this calculation you can easily do. Yeah? So it is nothing but EOX is equal to minus 1.36 minus 0.0591 divided by N. Log of M raised power N is N log M. Log 10 is 1. Just solve this equation. Get the answer in volts. Done and dusted. Right? Perfect. All right. Can you solve this question? I believe you can do a mistake here. See how confident I am. Yeah? You are going to do a mistake here. You are going to do a mistake here. Okay, before solving this question, let me tell you one thing. Guys, do you know what is pH? P stands for basically minus log. When it is pH, so minus log of H positive. If you anytime write POH, P stands for minus log. Minus log of what? OH negative concentration. If you sometimes write P of Ka, P stands for minus log. Minus log of what? Ka. If sometimes you write PKW, P stands for minus log. Minus log of what? Minus log of Kw. Right? Okay. Some basic things which I'll be using here. See guys, Understand one more thing. If pH is equal to X, if pH of some solution is equal to X, what does that mean? That means minus log of H positive concentration is equal to X to the base 10. Take this minus here, it becomes minus X. So from this particular equation, can't we calculate H positive concentration? It will be 10 raised per minus 6 molar. In short, one thing I want you guys to remember. If pH of the solution is X, that means H positive concentration will be minus 10 raised per minus 6. If pH of the solution is X, H positive concentration in the solution is 10 raised per minus 6. That's all. If for example, pOH of the solution is X, that means OH negative concentration in the solution is 10 raised per minus 6. Okay, remember all this stuff. This, anyways, we are going to discuss in equilibrium, which is most probably going to be our next chapter. See, a solution containing this shows a pH of 1. Calculate the reduction potential of the half cell. Half cell is given to me. In the half cell, Cr2O7 dinegative aqueous is getting converted into what? It is getting converted into Cr tripositive aqueous. So first of all, the reaction is not balanced. We are supposed to balance the reaction. Understand? 2 chromium to 2 chromium. Here the oxidation state of chromium was +6 to +3, decrease, reduction, gain of electrons. Now +6 to +3, what is the change? Final oxidation state minus initial, the change is 3. 3 is the change for 1 chromium atom, I have 2, so 3 2s are 6. So Cr2O7 dinegative will be gaining 6 electrons, then getting converted into 2 times Cr tripositive. Okay. Now people, is the reaction balanced? The reaction is still not balanced. That's where you are going to do a mistake. I'm pretty much sure you were supposed to write reaction quotient here itself, but the reaction is not in the balanced format. You have to write the reaction first of all in the balanced format. Okay. Here you got oxygen. Look at the pH of the solution. pH of the solution is 1. If pH is 1, that means the reaction is taking place in acidic medium. In acidic medium, how do we balance the reaction? 7 oxygen. So add 7 water molecules. 14 hydrogen. Add 14 H positives. Do you remember in the beginning of the session, I have shown you all this stuff? Yeah. Now people, what is the N value here? N value is 6. What is the QC value here? Start with the product. It is going to be concentration of chromium tripositive raised power 2. Water is in liquid state, nothing to do with that. Divided by H positive concentration raised to the power 14. Concentration of Cr2O7 dinegative raised power 1. What else? Nothing. Now, Cr tripositive concentration is given to me as per the equation. How much? 2 into 10 raised power minus 2. So 2 into 10 raised power minus 2 ka square will be 4 into 10 raised power minus 4 divided by H positive concentration. Since I know pH, 1, if I know the pH, if pH is equal to X, that means H positive concentration is 10 raised power minus 6. So if pH is 1, H positive concentration will be 10 raised power minus 1. Raised power what? Raised power 14. Cr2O7 dinegative concentration is given. That is 4 into 10 raised power minus 4. So this term cancels. The value comes out to be 10 raised power 14. This is QC. If this is QC, what am I supposed to calculate? I'm supposed to calculate the reduction potential. Use the Nernst equation. ERED is equal to E naught RED. SRP. SRP is given. +6 to +3. Decrease. Decrease means reduction. This SRP. SRP minus 0.0591. N value is how much? 6. Log of QC. QC is how much? 10 raised power 14. Now, use this particular equation and get it done. 1.5 minus 0.0591 divided by 6 log of m raised power n is n log m. So 14 log 10. Log 10 is 1. Solve this particular equation. Get the answer in volts. That's all. Am I clear? Am I clear with this question, people? Am I clear with this question? Look at one more question. Look at one more question. A zinc rod is dipped in a 0.1 molar solution of its salt at 25 degrees centigrade. Assume the electrolyte is 20% dissociated. Calculate the electrode potential. Whenever in a question, they are not mentioning whether you have to calculate oxidation potential of the electrode or reduction potential. If they ask you directly to calculate electrode potential, at that point of time, remember, you have to calculate reduction potential of the electrode. So right now, I need to calculate reduction potential of the zinc electrode. Okay. Right now, I need to calculate reduction potential of the zinc electrode. So see what has happened. As per the question, imagine that you have taken a container. In this particular container, imagine you have taken zinc sulfate. Now, this zinc sulfate would dissociate in the form of zinc dipositives and SO4 dinegatives. Okay. Now, for example, initially the concentration of zinc sulfate was taken as how much? 0.1 molar. Initially, this would be 0. This would be 0. I need to calculate the reduction potential of this electrode. I need to calculate the reduction potential of this electrode when 20% electrolyte was dissociated. I need to calculate the reduction potential of this electrode when 20% of the electrolyte is dissociated. So, when 20% electrolyte gets dissociated, what does that mean? What does that mean? What is 20% of 0.1? 20% of 0.1 is 20 by 100 into 0.1. That is 0.02, right? That means out of 0.1 moles of zinc sulfate, 0.02 moles of zinc sulfate are getting converted into products. So I'll be left with 0.1 minus 0.02. This is the concentration of zinc sulfate left in the container when 20% of the electrolyte has dissociated. Right? Now, 1 mole gives 1, 0.02 gives 0.02. Even this gives 0.02 molar. So basically, I got the concentration of ions in the container when 20% of the electrolyte has dissociated. When 20% of the electrolyte has dissociated. When 20% of the electrolyte has dissociated, right? At that point of time, the concentration of zinc dipositive in the container was 0.01 molar. The concentration of SO4 dinegative in the container is also 0.02 molar. What am I supposed to calculate? I am supposed to calculate the reduction potential of this electrode when the concentration of zinc dipositives in the solution is 0.02 molar. I hope you're getting. Okay. Now, people, we are almost done. In order to calculate reduction potential, I'll make sure that the electrode behaves like cathode. And when this electrode behaves like cathode, what happens? Reduction takes place. Zinc dipositives in the solution, they are going to collide with the rod. They'll take 2 electrons from the rod. So the reaction is going to be zinc dipositive aqueous will be gaining 2 electrons, getting converted into what? Zinc solid. This would be the reaction when this electrode would be behaving like cathode. Now, N value here is 2. Get the QC value. Start with the product. It is in solid, so 1 divided by concentration of zinc dipositive. So it's 1 divided by what is the concentration of zinc dipositive when 20% electrolyte is dissociated? It is 0.02. 1 divided by 0.02 comes out to be 50. So QC value is 50. Right? We are done. Calculate the reduction potential. Use the Nernst equation. ERED is equal to E naught RED. E naught SRP is given to me as minus 0.76 minus 0.0591 divided by, what is the value of N? N value is 2. Log of QC. QC is 50. 50 you can write 5 into 10. Now it's just a matter of calculation. And I believe you can easily do this calculation. So this equation is going to give me the reduction potential of this electrode when 20% of the electrode, when 20% of the electrolyte has got dissociated. When 20% of the electrolyte has got dissociated. I believe I'm clear. I believe I am clear to everyone. Okay. One last question, and after that I'll be giving the break. One question, and after this we'll take the dinner break. This is the last question before the dinner break, people. It's a good question. This is a good one. In order to solve this question, your concepts of equilibrium, they should be slightly clear. Okay? Your concepts of equilibrium should be slightly clear. Look at the question carefully. Calculate the reduction potential at the pH 14 for Cu dipositive copper. So this electrode is given. KSP, solubility product, is given. Something also E naught of SRP. SRP of copper is also given. See guys, what I'll be doing. What do I have to calculate? I need to calculate reduction potential of this electrode. In order to calculate reduction potential of the copper electrode, what should happen? Reduction. Copper dipositive should be gaining 2 electrons. So first of all, let me write the reaction. Copper dipositive aqueous in the solution will be colliding with the rod, will be taking 2 electrons from the rod, getting converted into copper solid. So N value, first of all, I got known as 2. QC value, Start with the product. It is in solid. So 1 divided by concentration of copper dye positive raised power 1. Okay. Now people, tell me one thing. Is the concentration of Cu dye positive given anywhere? I don't think so. Concentration of Cu dye positive is not given anywhere. No. We have to calculate concentration of Cu dye positive by somehow. How am I going to calculate that? A parameter is given to us. pH of the solution is 14. Temperature 25. My dear students, in your class 11th, maybe you would have studied somewhere at 25 degrees centigrade, pH plus pOH is equal to 14. If pH is given to me as 14. So 14 minus 14, 0. So I would say pOH is equal to 0. pOH is 0. If pOH is X, what is the OH negative? 10 raised power minus 6. So 10 raised power minus 0. 10 raised power 0 is 1. So I got the OH negative concentration. But I do not need the OH negative concentration. Yeah? I need Cu dye positive concentration. How am I going to get the Cu dye positive concentration? For that, Ksp of this one is given to me. So first of all, CuOH whole twice. How it would have undergone dissociation? Copper dye positive plus 2 times OH negative. If I ask you to write the expression of Ksp for this particular cuprous hydroxide, it is going to be concentration of Cu dye positive raised power 1, concentration of OH negative raised power 2. Because when you write the Ksp expression, you only write the products, right? You do not write the reactants. Okay. Now Ksp is given to me as 10 raised power minus 19. Well, this is Ksp, solubility product. It is not equilibrium constant. How do we write equilibrium constant? Products divided by reactants. But when you write Ksp, you do not write reactants in the denominator. You have got nothing to do with the reactant. Only you have to write the products. So Ksp is this, is equal to concentration of Cu dye positive. OH negative concentration is 1. 1 raised power anything is 1. I got the concentration of Cu dye positive, 10 raised power minus 19. It is 1 divided by 10 raised power minus 19. The value comes out to be 10 raised power 19. This is Qc. This is Qc, people. If you got Qc, we are done now. What do we have to calculate? Reduction potential. Use the Nernst equation. ERED is equal to E not RED, standard reduction potential. This is SRP given. Plus 2 to 0. Decrease means reduction. So this SRP. So 0.34 minus 0.0591 divided by N. N value is how much? 2. Log of QC. QC is how much? 10 raised power 19. So this is going to be 0.34 minus 0.0591 divided by 2. Log of M raised power N is N. Log 10 is 1. Solve this and get the answer in volts. This is the reduction potential of the half cell. Am I clear, guys? Remember this particular question, okay? As I told you, this was the last question before the break. So let's take the dinner break. Break till, what is the time? 10:24. Break till 11, huh? I think 11 is 5. 11:05. Yeah. What is happening? Oh my God. Why am I not able to draw this? Okay. Okay. So guys, but you have to be there. Are you willing to come back or you are going to sleep? Go for the dinner break, but be back exactly at 11:05 sharp. Okay, 11:05 sharp. I would want every one of you to be here. All right. अब आपकी हाइट क्या है? fit का हूँ मैं. Chalo, I'll see you after the break, guys. Let me have my dinner. I'm not done yet. You guys also have. See you in a while. Take care. Is everyone back? Yes. Everyone back? Yeah, perfect. Perfect, guys. All right, so should we start, people? A lot of Wasim's or fake IDs are there in the chats. Yeah, guys, be careful, huh? It's not me. A lot of students are, texting me on my Telegram to break this chapter into two parts. Do you actually want it in two parts? Yeah? Do you actually want it in two parts? A Hello, let me first of all complete the AMF part. Then I'll create a poll, right? I'll create a poll and then I'll get to know what to do. Okay? So first of all, let's complete this part. So what exactly we did? We were discussing the Nernst equation, right? And I showed you how do we calculate the oxidation and reduction potential of the half cells under non-standard conditions. Now, my dear students, what we are going to discuss now, we are going to discuss now the Nernst equation. Nernst equation for the complete cells. Or you can write Nernst equation for the complete reversible cells. Nernst equation for the complete reversible cells. See, guys, understand. Guys, we'll discuss it afterwards, okay? Focus on the session now. Focus on the session now. We'll discuss the parts afterwards. Focus on this particular part now. So till now we discussed about how do we write the Nernst equation for the half cells in order to calculate their oxidation and reduction potential. Now we are going to discuss how do we write the Nernst equation for the complete cells. You know, a complete cell is basically made up of two half cells, right? A complete cell is basically made up of two electrodes connected externally as well as internally. How do we exactly write Nernst equation for them? My dear students, for example, I'm writing a cell over here. Let's say the cell is in this format. Zinc solid, zinc dye positive aqueous, salt bridge, copper dye positive aqueous, and this is copper solid. For example, this is the cell that is given to us. How do we write Nernst equation for this cell? My dear students, first of all, on the left side of the salt bridge, what do we have? We have got anode. This is zinc dye positive, okay? On the left side of the salt bridge, we have got anode. And what happens at anode? You know it. At anode, oxidation takes place. Zinc gets converted into zinc dye positive. So the reaction has to be zinc solid at anode getting converted into zinc dye positive aqueous. And with that, we are writing 2 electrons. This is the reaction taking place at anode. Similarly, my dear students, what would be the reaction taking place at cathode? You know, at cathode, reduction takes place. Copper dye positive getting converted into copper. So the reaction has to be copper dye positive aqueous plus 2 electrons gives copper solid. This is the reaction at cathode. Perfect. Now, my dear students, are the electrons balanced? Yes, the electrons are balanced. So I can directly add these 2 reactions. And when I add these 2 reactions, I would get the net reaction as zinc solid plus copper dye positive aqueous. It gives zinc dye positive aqueous plus copper solid. This is my net reaction. In this net reaction, if I ask you how many moles of electrons got exchanged, you will say 2 moles of electrons got exchanged. Can we exactly get the value of QC? Yes. Start from the product. It's going to be concentration of zinc dye positive raised by stoichiometric coefficient 1. This is solid, its hectomass is unity, divided by, this is solid, its hectomass is unity, divided by concentration of copper dye positive raised by 1. Perfect. So QC we have written over here. Similarly, we can easily calculate E naught cell as well. What is E naught cell? E naught cell is E naught cathode minus E naught anode. So if you know the SRP of cathode, if you know the SRP of anode, you can calculate E naught cell. My dear students, once you get E naught cell, then easily you can write Nernst equation. Nernst equation says E cell is equal to E naught cell minus 0.0591 divided by N and its log of QC. See, E naught cell, this is how you'll calculate. N value, this is how you'll calculate. QC value, this is how you'll calculate. Put all the values into this expression and get the value of E cell, right? So whenever EMF of the cell under non-standard conditions is to be calculated, this is the approach which you will be using. This is the approach which you'll be using. Reaction at anode, reaction at cathode, N value, net reaction, QC, E naught cell, then the Nernst equation. Okay, this is the approach which you should be using over here. For example, let's try to solve a few questions so that you'll understand how exactly we are going to do this. See guys, look at this particular question. Look at this particular question. Look at this particular question. Calculate the EMF of this particular cell, right? I'm given with a cell, its EMF is given. Just give me a second. This is the reduction potential. This is potential more. Yeah, perfect. So we have to calculate EMF of the cell that's given to me. Again, the same approach which I told you. First of all, these 2 lines, they represent your salt bridge. On the left side, you'll be writing the anode. So reaction taking place at anode is going to be tin is getting converted into SN dye positive. So SN solid, I would say, would be losing 2 electrons and then getting converted into SN dye positive. This is the reaction at anode. Similarly, if I ask you, as per you, what should be the reaction at cathode? At cathode, you can see PB dye positive getting converted into PB solid, right? So I would say PB dye positive aqueous would be gaining 2 electrons and then getting converted into PB solid. This is the reaction at cathode. Since the electrons are already balanced, if the electrons are balanced, then you can directly add these 2 reactions. This 2 will get cancelled out. My net reaction would be SN solid plus PB dye positive aqueous. What does it give me? It gives SN dye positive aqueous, and with this, you'll be writing PB solid. This is your net reaction. N value here will come out to be 2. 2 moles of electrons have been exchanged. Now, what is the next thing? I'm supposed to get the QC value. You'll be starting with the product, which is an aqueous form. So it's going to be concentration of SN dye positive raised by stoichiometric coefficient 1. This is solid, its hectomass is unity, nothing to do with that. Divided by, this is solid, nothing to do with that. This is aqueous, so write its concentration raised by stoichiometric coefficient 1. Now, what is the concentration of SN di positive? It's 1 molar divided by. What is the concentration of PB di positive? It is 10 raised power minus 3. So the overall value comes out to be 10 raised power 3. What is the next thing which I need to calculate? I need to calculate E naught cell, which is technically E naught cathode minus E naught anode, right? Which is equal to SRP of cathode, SRP of cathode, SRP of lead. SRP of lead electrode is given to me as minus 0.13 minus SRP of anode. This is the SRP of anode that's given to me as minus 0.14. So minus plus 0.14. This value after solving comes out to be 0.01 volt. This is your E naught cell. So you have calculated all the parameters which are used in the Nernst equation. So as per Nernst equation, E cell is equal to E naught cell 0.01 minus 0.0591 divided by N is 2 log of QC. What is QC? QC is nothing but 10 raised power 3. So it is nothing but 0.01 minus 0.0591 divided by N value is 2. This becomes 3 log 10. Log 10 is 1. Just solve this particular equation. Get the answer in volts. That is the EMF of this cell which we were supposed to calculate. Yeah? Is that clear, people? Is it clear? Is that clear quickly? Is it clear? This is the fake ID of Yavar Manzoor. Don't pay any attention to this. Someone has just mentioned Yavar Manzoor. He must be sleeping right now. He must be in third sleep. He sleeps at 9 p.m. Okay? So I hope this particular question is clear to everyone. Perfect. Moving on to one more question, guys. Look at this particular question carefully. Look at this particular question carefully. See, we are given with a reaction. So one thing, we are not supposed to write the reaction. The reaction is given to us in this question. As far as the question, E cell is equal to E naught cell. Okay, E cell is equal to E naught cell. And Fe di positive concentration, partial pressure of O2, and pH is equal to X. We have to calculate the value of X. Correct? Now understand how exactly we are going to solve this question. My dear students, first of all, the reaction that's given to us. Can we write its QC expression? Start with the product. So it's going to be concentration of Fe tri-positive raised by its stoichiometric coefficient 2. This water, it's in liquid state, nothing to do with it. Divided by solid, nothing to do with it. O2, use its partial pressure. Partial pressure of O2 raised by stoichiometric coefficient multiplied by concentration of H positive raised by its stoichiometric coefficient. This is the QC expression. Okay, this is the QC expression. Now put the values here. Concentration of Fe tri-positive as per the question. Fe tri-positive should be given to us. This is Fe tri-positive here, by the way. This Fe tri-positive. It is 10 raised power minus 3. 10 raised power minus 3 ka square comes out to be 10 raised power minus 6 divided by. What is the partial pressure of O2? Partial pressure of O2 is 10 raised power minus 2. Concentration of H positive. Well, pH is given to me as X. If pH is X, that means concentration of H positive will be 10 raised power minus 6. So 10 raised power minus X raised power 4. Right? So I would say QC is equal to 10 power minus 2, 10 power minus 6. So it becomes 10 raised power minus 4 divided by 10 raised power minus 4x. This is QC. Now guys, look carefully. Look carefully. As per the question, E cell is equal to E naught cell. Do you know your Nernst equation? Nernst equation says that E cell is equal to E naught cell minus 0.0591 divided by N log of QC. Now in the question, they are mentioning that E cell is equal to E naught cell. When can be E cell equal to E naught cell? E cell can only be equal to E naught cell if this term becomes 0. Now how this term is going to become 0? When QC will become equal to 1, right? If QC is equal to 1, then only E cell becomes equal to E naught cell. This is the condition, right? Because log of 1 is 0 then. If QC is equal to 1, then only E cell is equal to E naught cell. Now QC is equal to 1 means that 10 raised power minus 4 divided by 10 raised power minus 4x. It has to be equal to 1. So it implies 10 raised power minus 4 has to be equal to 10 raised power minus 4x. When is it possible? When x value is equal to 1. Right? LHS, RHS will come out to be equal only if x is equal to 1. Weren't we supposed to calculate this x only? Done and dusted? Calculated? Yeah? Perfect? Perfect, guys. I believe this is clear to everyone. And you should be in a position to solve this sort of a question on your own. Look at the next one. Look at this particular question, guys. Look at this particular question. Calculate the EMF of the cell. Fe plus 2 gives Fe tri positive is minus 0.17 volts. Okay. This is the cell that's given to me. So let me write the cell in again over here correctly, because I feel the cell is not given in the correct form, or it is given in the correct form. The cell is not given in the correct form. Why is that? Because aqueous, they should be separated by comma. Here you can remove this arrow, remove the slash, and instead of that you can put the arrow. Right? Rest everything is fine. Perfect. So what is the first thing, guys? Follow the process. Write the reaction at anode first of all. At anode, H2 giving H positive. So the anode is your hydrogen electrode. So H2 gas would be getting converted into 2 times H positive aqueous. And with this, you'll be writing 2 electrons. This is the reaction at anode. Similarly, if you want to write the reaction at cathode Fe tri positive gives Fe di positive. So I would say Fe tri positive aqueous would be gaining 1 electron and getting converted into Fe di positive aqueous. Right? The electrons are not balanced yet. So try to balance the electrons. How do you balance the electrons? I'll be multiplying this reaction by number 2. So it becomes 2 times. This becomes 2 electrons and this becomes 2 times. The reaction is balanced. After balancing the reaction, add these 2 reactions. When you add these 2 reactions, this 2 and this 2 gets cancelled. So I would say my net reaction becomes H2 gas plus 2 times Fe tri positive aqueous. It gives us what? It gives us 2 times H positive aqueous, and with this you write 2 times Fe di positive aqueous. This is my net reaction. Correct? What is the N value? N value here is 2. Okay. If I ask you what is the QC value, start with the product. Concentration of H positive raised by stoichiometric coefficient. Concentration of Fe di positive raised by stoichiometric coefficient divided by partial pressure of H2 gas raised by stoichiometric coefficient. Concentration of Fe tri positive raised by stoichiometric coefficient. Now what is the concentration of H positive? It's given to me as 10 raised power minus 3. 10 raised power minus 3 ka square is 10 raised power minus 6. Concentration of Fe di positive 0.01. That means 10 raised power minus 2 ka square will be 10 raised power minus 4 divided by partial pressure of H2 gas 0.1 bar. 0.1 means 10 raised power minus 1. Concentration of Fe tri positive is given to me as 0.1. That means 10 raised power minus 1 ka square, 10 raised power minus 2. When you solve this, in the numerator you get 10 raised power minus 10. In the denominator you get 10 raised power minus 3. So the overall value comes out to be 10 raised power minus 7. So this is QC. This is your QC, guys. Right? This is your QC. Yeah? This is your QC. If you got the value of QC, now what is the next step? We are supposed to calculate E naught cell. How do we calculate E naught cell? E naught cathode minus E naught anode. This is your cathode, right? SRP of cathode. This is SOP of cathode. Plus 2 to plus 3. Increase, oxidation. So this SOP of cathode. I need SRP of cathode. So reverse the sign. Minus SRP of anode. Anode is hydrogen electrode. Its SRP is 0. So the value has to be 0.17 volts. This is your E naught cell. Perfect. N value here we have calculated. QC we got. E naught cell we got. Now it's time to use the Nernst equation. E cell is equal E naught cell minus 0.0591 divided by N, and its log of QC. QC is 10 raised power minus 7. Now it is just the matter of calculation. 0.17 minus 0.0591 divided by 2. Log of m raised power n is n log m. So minus 7 comes to the front. Log of 10 is 1. Solve this equation. Get the answer in volts. That's going to give you the EMF of this particular cell. I believe this is clear to everyone. Yeah? Right, people? Is it clear? Is it clear? Tell me the names. Tell me the names. Sir, please tell us about your family. Why not? Why not? Why not? Anything else do you want to know about me? Anything else? You're blocked. Okay. Give me the names. Give me the names. Quick, quick, quick. I hope this particular question is clear. Yeah? All right. Let's have a look on one more question then. All right, guys. Look at this particular question. Look at this particular question. The EMF of the cell is given to us as 0.81 volt. This is the cell that's given to us. M gives Mn positive. Its concentration is given H positive, 1 molar H2 gas. Okay. Calculate the charge on the metal. So we have to calculate charge on this metal ion basically. We have to get the value of N. How exactly we are going to get the value of N? First of all, I'll follow the complete process which we have discussed till now. So the reaction at anode. At anode, your M solid is getting converted into Mn positive aqueous. Plus how many electrons? Plus N electrons. This is the reaction at anode. Similarly, reaction at cathode. H positive gives H2. So it is 2 times H positive aqueous plus 2 electrons gives H2 gas. This is the reaction at cathode. Are the electrons balanced? No. Balance the electrons. This is N, this is 2. So I'm multiplying this reaction with number 2. I'm multiplying this reaction with number N. So when I multiply them and add them finally, what do I get? I'll be getting 2 times M solid plus 2N times H positive aqueous. It gives 2 times Mn positive aqueous. And with this, I'll be writing N times H2 gas. This is the reaction. This is the net reaction. How many electrons are cancelled? I'll say 2N moles of electrons are cancelled, are exchanged. 2N. Right? Now, people, if you want to write the QC expression, start with the product. It is simple. Concentration of Mn positive raised power stoichiometric coefficient 2. Partial pressure of H2 gas raised power stoichiometric coefficient N divided by. This is solid, its active mass is 1, nothing to do with this. Concentration of H positive raised power stoichiometric coefficient 2N. Now, what is the concentration of Mn positive? 0.02. Ka square means 0.04. I mean 0.02 ka square. So basically, Mn positive concentration is 2 into 10 raised power minus 2. Ka square becomes 4 into 10 raised power minus 4. Partial pressure of H2 is 1. Partial pressure of H2 is 1. Concentration of H positive is also 1 molar. Right? So this is my QC. Yeah. Now, E naught cell. E naught cell is equal to E naught of cathode. E naught of hydrogen electrode. That's 0. Minus E naught of anode. SRP of anode. Well, this is SOP of anode. What do I need? I need SRP. So reverse the sign. Minus minus plus 0.76 volts. Right? So this is your E naught cell. You got E naught cell. You got QC. Now use the Nernst equation. And just a bit of calculation is needed. Just a bit of calculation is needed, people. So in this particular question, what exactly I'll be doing? I'll be just using the Nernst equation. E cell is equal to E naught cell minus 0.0591 divided by. Should I be writing N or 2N? Should I be writing N or 2N? Quick. I should be writing 2N in this particular case because 2N moles of electrons are being exchanged. Yeah? Right, people? Then it's going to be log of QC. What is the QC value? QC value I got to know as 4 into 10 raised power minus 4. 4 into 10 raised power minus 4. Now, as per the question is concerned, E cell value is given to me, 0.81. E naught cell also we have calculated, 0.76. So 0.81 minus 0.76, that comes out to be 0.05 is equal to minus 0.0591 divided by 2N, and it's going to be log of M into N, which comes out to be log of 4 plus log of 10 raised power minus 4. Log of M into N is nothing but log of M plus log of N. Right? Perfect. Now, again, it is now the matter of calculation only. Again, now it's just the matter of calculation. So approximately, I'll be cancelling out these two things. So 2N comes to that side, or I'll say N is equal to minus 1 by 2 approximately. Log of 4 is nothing but 0.6. Log of 10 raised power minus 4 will be minus 4 log 10. Perfect. When you solve this, n value will be approximately 1.7 because I've used the approximation over here. So n cannot be fraction, charge cannot be fraction. So what is the closest integer here? That is 2. So I would say the charge on this m over here is nothing but plus 2. I believe this is clear to every one of you. Yeah? Am I clear, people? Am I clear with this particular question? Am I clear with this particular question? Quick. This sort of a question you should be in a position to solve on your own from now onwards. So this was how do we use the Nernst equation for the complete reversible cells. Yeah? This is how do we use the Nernst equation for complete reversible cells. How 0.05? E cell is given to me as 0.81. E naught cell we calculate as 0.76. So 0.81 minus 0.76 is nothing but 0.05. Okay? Perfect. Now guys, there is one more topic, important one, that is Nernst equation at equilibrium. Nernst equation at equilibrium. Nernst equation at equilibrium. Nernst equation at equilibrium. See guys, try to understand what exactly I'm going to say. Okay? This is again important. First of all, if you talk about your galvanic cell, I mean the Daniell cell, which we have discussed long back. In your Daniell cell, if you remember, you took 2 electrodes. One was your zinc electrode and one was your copper electrode. Zinc electrode, copper electrode. And if you remember, you connected them with the help of ammeter, and here you connected them with the help of salt bridge. So this was your Daniell cell. My dear students, in your Daniell cell, if you remember, this copper electrode, it was behaving like the cathode, and the zinc electrode, it was behaving like the anode. Perfect. At anode, what happens? Oxidation takes place. And at cathode, what happens? I would say reduction takes place. At cathode, reduction takes place. So in your Daniell cell, which we have discussed, at your cathode, reduction takes place. At your anode, oxidation takes place. Now, can I say, at this copper, reduction can only take place if the reduction potential of copper is more than that of reduction potential of zinc? Yeah? I would say at this particular electrode, reduction can only take place here if the reduction potential of copper electrode is more than that of reduction potential of zinc. Then only reduction can take place here and oxidation can take place here. Let me just make you understand by taking some random values. For example, arbitrary values I'm taking, random values I'm taking, just to make you understand. Let's say the reduction potential of this electrode is, for example, 5 volts. And the reduction potential of this electrode is, for example, 1 volt. Okay. So which electrode has got more reduction potential here? This one. Yeah. Okay. This electrode has got more reduction potential. The one that has got more reduction potential, it will undergo reduction. And reduction takes place at cathode. So for the copper electrode to behave like the cathode, its reduction potential should be more. So I'm taking the random arbitrary values just to make you understand. Let's say its reduction potential is 5. Its reduction potential is 1 volt. Now guys, if you remember, at anode what happens? Oxidation takes place. This zinc rod is made up of zinc atoms. Those zinc atoms will undergo oxidation and will enter into this particular solution. So what is happening to the concentration of anodic container? Concentration of electrolyte in anode. With time, is it going to get increased or decreased? Concentration of electrolyte in anodic container. It will increase with time. Right? Similarly, my dear students, the copper dye positives in this solution, they'll be colliding with the rod, taking 2 electrons from the rod, getting converted into copper solid, due to which the cation concentration here in the container will decrease. Or I'll say in general, the concentration of electrolyte in the cathode will decrease with time. Will decrease with time. Concentration of electrolyte in anode will increase with time. Concentration of electrolyte in cathode will decrease with time. And my dear students, we have discussed one thing. If you remember, reduction potential is directly proportional to concentration of electrolyte in the container. Long back we have discussed this. Okay. So initially, the reduction potential of zinc was 1 volt. The reduction potential of copper was 5 volts. Now the concentration of electrolyte here is increasing. If the concentration of electrolyte in the anodic container is increasing, reduction potential of anode will increase. So reduction potential of anode will be increasing with time. Similarly, concentration of electrolyte in the cathode is decreasing. So reduction potential of cathode will be decreasing with time. So initially, the reduction potential of zinc was 1 volt, less. The reduction potential of copper was high, 5 volts. Perfect, just to make you understand. Now, the reduction potential of anode is increasing and the reduction potential of cathode is decreasing. As the cell starts working, reduction potential of anode is increasing, reduction potential of cathode is decreasing. Can I say there will be a scenario when the reduction potential of both these electrodes will be same, will be equal? One is increasing, one is decreasing. I'll say there will be a scenario when the reduction potential of both the electrodes will become equal. If the reduction potential of both the electrodes becomes equal, at that point of time, the potential difference, if the potential of both the electrodes has become equal, therefore potential difference becomes 0. And when the potential difference becomes 0, at that point of time, no current is drawn from the cell. And that stage in the cell, at which E cell becomes 0, at which potential difference between the electrodes becomes 0, that is something which we call as equilibrium stage, right? So, I must say, when the cell attains equilibrium, I must say E cell value will be equal to 0. If E cell is equal to 0, therefore delta G, which is equal to minus N of E cell. If E cell is equal to 0, therefore delta G also is equal to 0. When is it? It is at equilibrium. It is at equilibrium. It is at equilibrium. Okay, it is at equilibrium. It is at equilibrium. Perfect. Now, my dear students, do you remember your actual Nernst equation? Your actual Nernst equation used to be like this. E cell is equal to E naught cell minus 2.303 RT divided by NF and log of QC. This used to be your actual Nernst equation. So if I write this Nernst equation at equilibrium, where E cell is equal to 0, if this E cell is equal to 0, E naught cell comes this side. So minus cancelled. So I'll be getting a result. E naught cell is equal to 2.303 RT divided by NF. Now it's going to be log of. At equilibrium, QC is replaced by equilibrium constant KEQ. Now this is going to be KEQ. This is the equation which is valid at equilibrium. This is the equation which is valid when equilibrium is achieved in the cell, right? This is the equation which is valid when equilibrium is achieved in the cell. Perfect. My dear students, one way of calculating E naught cell was E naught cathode minus E naught anode. That was one way of calculating E naught cell. This becomes our one more way of calculating your E naught cell. 2.303 RT divided by NF log of KEQ. Or if you take the value of R as 8.314 joules per Kelvin per mole, if you take the Faraday's constant as 96500 coulombs, if you take the value of temperature as 25 degrees centigrade, that means 298 Kelvin. 298 Kelvin. If you take all these parameters into this particular equation, then our final equation is going to become like this. Our final equation is going to become like what? It is going to be E naught cell is equal to 0.0591 divided by N, and it's going to be log of KEQ. This is the equation which is used at equilibrium. This is the equation which is used when equilibrium is attained in the cell. Okay. Similarly, guys, if you remember, there was one more equation. Delta G is equal to delta G naught plus RT ln of QC. This used to be one equation. If I write the same equation at equilibrium, at equilibrium, your delta G is equal to 0. If delta G is equal to 0, therefore delta G naught becomes minus RT ln of, instead of Q, you'll write KEQ, right? Or if you want to write the equation in terms of log, it's going to be minus 2.303 RT ln of KEQ becomes log of KEQ. Perfect. Right? So these equations, they are used when equilibrium is achieved in the cell. Perfect. So remember, simple. At equilibrium, delta G is 0, your E cell is 0. Rest, these are the new equations which are used when the cell attains equilibrium. Perfect. What kind of question can be asked here? See guys, this is one simple question. One very simple question. For the cell involving one electron, n value is 1. E naught cell is equal to 0.059. E naught cell is also given 0.59 volts. What do we have to calculate? We have to calculate equilibrium constant. In order to calculate the equilibrium constant, I'll assume the cell is at equilibrium. In order to calculate the equilibrium constant, I'll assume the cell is at equilibrium. And my dear students, when the cell is at equilibrium, I can use this equation. E naught cell is equal to 0.0591 divided by n, and it's going to be log of KEQ if the cell is at equilibrium. Now E naught cell, that is 0.59, right? Multiplied by n value is 1, is equal to 0.0591 log of KEQ, and this is to the base 10. Perfect. This is 1, this is 10. So 10 is equal to log of KEQ to the base 10. So I would say equilibrium constant is equal to 10 raised power 10. Equilibrium constant is equal to 10 raised power 10 here. This is something which I was supposed to calculate. Right, people? Perfect. Similarly, I'll come up with one more question like this, and I believe you can easily solve this particular question. Here you have to calculate equilibrium constant. Cell reaction is given. From the cell reaction, you can calculate N. E naught cell is given. And what are we supposed to calculate? Equilibrium constant, KEQ. Done and dusted. Right? This can be, you can take this as the homework question, and you should be in a position to solve this particular question on your own. Because it is a similar type. All the parameters are given. We have to calculate the KEQ value, equilibrium constant value. I hope I'm clear with this. Now guys, we are going to enter into one more part of the chapter, that is concentration cells. Okay, concentration cells. This is again one very, very, very important topic. Concentration cells. First of all, what are concentration cells? My dear students, till now, whatever galvanic cells we saw, in every galvanic cell, we took two different electrodes. We connected them externally and internally. We used to get a galvanic cell, right? Now, in case of your concentration cell, what are we going to do? In case of the concentration cell, my dear students, I'll say two same electrodes, not different ones. Two same electrodes are used. I'll show you in some time. Just take a note of these things first. Two same electrodes are used. Two same electrodes are used. For example, let's say this is one zinc electrode. This is, let's say, zinc sulfate. Similarly, this is one more zinc electrode. This is one more zinc electrode. I'm connecting them externally as well as internally. Do you see two same electrodes being used or two different electrodes? Two same electrodes being used over here. Two same electrodes being used over here. Poll I'll take after this topic. Okay? Poll I'll take after this topic. Poll I'll take after this topic. Just wait. Wait, guys. After 1 hour, I'll be taking a poll. Okay. I've taken two same electrodes. Perfect. Now, if I've taken two same electrodes, I'll be calling this particular cell as the concentration cell. In the concentration cell, let me tell you, in the concentration cell, we use two same electrodes. Okay. And my dear students, in the concentration cells, I would say EMF is generated EMF is generated either due to concentration difference or partial pressure difference. What it means, you'll get the idea in some time. In 5 to 10 minutes, you'll understand this particular statement. EMF in case of concentration cells is generated due to either concentration difference or partial pressure difference. Number 3, E naught cell here in case of concentration cell. E naught cell. What is E naught cell basically? E naught cathode minus E naught anode. Since your cathode and anode is same, so instead of E naught cathode, I'll be writing SRP of cathode means SRP of zinc minus, it's again going to be SRP of zinc only because anode cathode, they are same, zinc electrodes. So SRP of zinc minus SRP of zinc comes out to be 0. So remember, in case of your concentration cells, your E naught cell here is equal to 0. Your E naught cell is equal to 0. Perfect. These are, first of all, the 3 points which I would want you guys to remember. And now I'm going to discuss this concentration cell in detail. But these 3 points are to be remembered. In case of concentration cells, we'll be using 2 same electrodes, right? EMF is generated either due to concentration difference or partial pressure difference. E naught cell in case of concentration cells is equal to 0. Perfect. It is equal to 0. Now, my dear students, let me tell you, these concentration cells, these are actually of 2 types. Concentration cells. If we talk about the concentration cells, these are actually of 2 types. Number 1 is your electrolytic concentration cell. Number 1 is your electrolytic concentration cell, and number 2 is your electrode concentration cell. Electrode concentration cell. Now, people, few things which please take a note of. In case of electrolytic concentration cells, I would say EMF is generated due to concentration difference, comma, keeping the partial pressure same. In case of your electrode concentration cell, I must say EMF is generated due to what? Due to partial pressure difference, keeping concentration same. For example, you will understand it like this. See, my dear students, imagine this is a salt bridge, right? Let's say on the salt bridge, I'm using zinc electrode. Zinc solid gives zinc dye positive aqueous. Let's say the concentration here is C1 molar. Similarly, on the right side, again, I've got zinc electrode only. Zinc dye positive, whose concentration is, for example, C2 molar. It gives zinc solid. Look at this particular cell representation. Over here, in your anodic container, the concentration of zinc dye positive is C1. In your cathodic container, the concentration of zinc dye positive is C2. So concentration of electrolytes in both the containers, anodic container and cathodic container, is kept different. Perfect. Whenever you see such kind of the cell, in which partial pressure is kept same, but concentration of electrolytes in both the containers is kept different, you call this particular cell as electrolytic concentration cell. Perfect. Or wait for this representation. Okay, I'll teach you this in detail. So first of all, tell me whether you got the idea of what these cells are. In case of your concentration cells, we have got, first of all, 2 types of concentration cells: electrolytic, electrode. In electrolytic concentration cells, partial pressure is kept same, concentration is kept different. In electrode concentration cells, I would say concentration is kept same, partial pressure is kept different. Okay, let's try to analyze this in detail. See, guys, let's try to analyze this particular thing in detail. So I'm marking the heading here as electrolytic I'm marking the heading here as electrolytic concentration cell. I'm marking the heading as electrolytic concentration cell. Okay. See guys, for example, just to make you understand, let's say I've taken two containers. Okay. And these are the two rods. This is the rod of metal M. Even this is the rod of metal M. So here in this particular container, you have got Mn positive ions with the concentration C1 molar. In this particular container, again you have got Mn positive ions with the concentration C2 molar. Join them externally with the help of ammeter. Perfect. And internally with the help of salt bridge. This is the cell in which the concentration of electrolytes is kept different. So I'll be calling this particular cell first of all as concentration cell because same electrodes are used. Now concentrations are different, so it is electrolytic concentration cell. So first thing, how do I represent it? How do I represent it? Simple guys. Salt bridge, on the left side of the salt bridge, you'll be writing anode. This is your anode here, this is your cathode. At anode, M gets converted into Mn positive. At anode, I would say M solid will be getting converted into Mn positive with the concentration C1 molar. On the right side, it's cathode. At cathode, Mn positive will be getting converted into M solid. At cathode, I would say Mn positive with the concentration C2 molar will be getting converted into M solid. My dear students, this is how you represented this electrolytic concentration cell, wherein two same electrodes are used, but there is a difference in the concentration. Okay. So let's exactly frame a condition. Let's exactly frame a condition of when and how this electrolytic concentration cell is going to work. Understand properly what exactly I'm going to say. See guys, for this electrolytic concentration cell to be working, at anode what should happen? At anode oxidation should take place. M should get converted into Mn positive. So the reaction should be M solid should get converted into Mn positive with the concentration C1 molar plus N electrons. This should be the reaction at anode. Similarly, what should be the reaction at cathode if I ask you? Reaction at cathode should be Mn positive giving M. So Mn positive with the concentration C2 plus N electrons giving M solid. Okay, this is the reaction taking place at cathodic container. Mn positive colliding with the rod, taking N electrons from the rod, getting converted into M solid. Yes. So reaction at anode, reaction at cathode. Are the electrons balanced? Yes, the electrons are balanced. Right? Now add the reactions. My dear students, when you add these two reactions, what all things will get cancelled out? M solid cancelled. N electrons cancelled. So my net reaction has to be Mn positive with concentration C2 molar gives Mn positive with concentration C1 molar. This is my net reaction. If this is my net reaction, can I write the QC expression? QC is going to be concentrations of this Mn positive C1 divided by concentration of this Mn positive C2. What is C1 and what is C2? C1 is basically concentration of electrolyte in cathodic container. Concentration of electrolyte in cathodic container, right? Divided by what is C2? C2 is the concentration of electrolyte in the anodic container. I think I wrote the reverse. C1 is concentration of electrolyte in anode. C1 is the concentration of electrolyte in anode, and similarly C2 is the concentration of electrolyte in cathode. Yeah, in cathode. Now guys, first of all, since it is a concentration cell, so I must say it's E0 cell. Its E0 cell is equal to 0. Okay. Now people, if I write the Nernst equation, Nernst equation says that E cell is equal to E0 cell, that is 0, minus 0.0591 divided by N log of QC used to be C1 by C2. QC used to be C1 by C2. Now you can write it like this as well. E cell is equal to, take this minus inside, it is 0.0591 divided by N minus log of this. It becomes log of, take the reciprocal, C2 divided by C1. I have multiplied this log with minus sign, so it becomes log of C2 by C1. So people, now tell me one thing. For this particular cell to be working, for a cell to be working? For a cell to be working. Tell me one thing. What is the criteria? What is the criteria for the cell to have its cell reaction spontaneous? I would say for the electrolytic concentration cell. For the electrolytic concentration cell. Involving which electrodes? For the electrolytic concentration cell involving metal ion electrodes. Involving which electrodes? Metal ion. Involving metal ion electrodes to be working. To be working. That means for its cell reactions to be spontaneous. That means for its cell reactions to be spontaneous. You know the condition is E cell should be greater than 0. E cell should be greater than 0. Now you tell me, when can be E cell greater than 0? E cell can be greater than 0 if this term is greater than 0. If log of C2 divided by C1. If log of C2 divided by C1 is greater than 0. Now when is log of C2 by C1 greater than 0? When is log x greater than 0? When x is greater than 1. So C2 by C1 has to be greater than 1. C2 by C1 has to be greater than 1. Which means C2 has to be greater than C1. Right? So this is the condition which is to be followed. Then only EMF of the cell comes out to be positive. Then only the cell reactions involved in the cell will be spontaneous. Right? Right, people? So C2 has to be greater than C1. What was C2? C2 was concentration of electrolyte in cathode. C1 is concentration of electrolyte in anode. So I would say in general, concentration of electrolyte in cathode should be greater than that of concentration of electrolyte in anode. Then only the EMF of this particular cell will come out to be positive. And once the EMF of the cell comes out to be positive, I would say its cell reactions would be spontaneous and the cell would be working like a normal galvanic cell in which electrons are going to move from anode to cathode and current is going to shift from cathode to anode. As simple as that. Yes? Perfect. So this is the criteria. Do remember this particular criteria. And if this particular criteria is clear, tell me the answer of this particular question. Tell me the answer of this particular question. Quick. Tell me the answer of this particular question. Maran, I'll text you back. I'll text you back. I'll text you back. I saw your message, but I was in the session basically. Could not reply. What is the answer of this question? Quick. If you look at the question carefully, guys, if you look at the question carefully, we are given with the cell. There's a salt bridge. On the left side, zinc electrode. On the right side, zinc electrode. So it is the concentration cell. Same electrodes have been used. Now, concentration in both the containers is kept different. So it is electrolytic concentration cell. Now, since we identified it is the electrolytic concentration cell, the first option is saying cell reactions will be spontaneous if C1 will be greater than C2. What is C1? C1 is the concentration of electrolyte in cathode. C2 is the concentration of electrolyte in anode. And we know, few minutes back only we have discussed, for the electrolytic concentration cell involving metal ion electrodes to be working, concentration of electrolyte in cathode should be greater than that of anode. So C1 has to be greater than C2. C1 has to be greater than C2. Then only I would say C1 has to be greater than C2. Then only we would say that this cell reactions would be spontaneous, right? So the first option is correct. Look at the second one. If C2 is greater than C1, current will flow from cathode to anode. Nothing. C1 should be greater than C2. Then only cell reactions will be spontaneous. And if cell reactions are spontaneous, at anode and oxidation will happen. At cathode reduction will happen. Electrons will move from anode to cathode. Current will go from cathode to anode. Right? If C1 is greater than C2, current will flow from cathode to anode. This is correct. If concentration of electrolyte in cathode is more than that of anode, cell reactions will be spontaneous. So at anode oxidation, electrons will move from anode to cathode. Current will go from cathode to anode. If C1 is equal to C2, cell will not work. It's again simple. If C1 is equal to C2, if C1 is equal to C2, this becomes log of 1, log of 1 0. This term becomes 0. So E cell is 0. If E cell is 0, cell is not going to work. So this is also the right one. Perfect. So I believe this particular question is clear to you. This was a multiple option correct. Yes. Now, my dear students, here, in case of electrolytic concentration cell, there is one more cell involved. What is that? That's called as electrolytic concentration cell involving hydrogen electrodes. Electrolytic concentration cell involving hydrogen electrodes. What this cell exactly is all about. See, for example, this is your hydrogen electrode. This is your one more hydrogen electrode. So basically, this is your hydrogen rod in which H2 gas is introduced at a pressure of P, at a pressure of, for example, P bar, right? Here you have got again the hydrogen rod in which hydrogen gas is introduced at a pressure of P bar, right? And this is your emitter, for example. This is your salt bridge. Over here, the concentration of H positive ions is equal to C1 molar, and concentration of H positives here is C2 molar. Do you see? Have I used two same electrodes or different electrodes? Look at it. Are we using two same or different? Hydrogen electrode, hydrogen electrode. I'm using two same electrodes. So it is the concentration cell. It is the concentration cell, right? It is the concentration cell first of all. So if it is a concentration cell, its E naught cell has to be 0, right? Partial pressure of the gases I'm keeping same. Concentration I'm keeping different. Partial pressure same, concentration different. So it is basically your electrolytic concentration cell in which we have introduced hydrogen electrodes. So first of all, how do I represent this? See guys, how do we represent this? Platinum solid, comma, H2 gas at a pressure of P bar. H2 gas at a pressure of P bar gets converted into what? H positive, whose concentration is C1 molar. Salt bridge, on the right side cathode. At cathode, reduction is going to take place. H positives into H2. So H positives, whose concentration in the right container is C2 molar, gives H2 gas, whose pressure is again P bar only, and this is your platinum solid. So do you look at this particular cell? Two same electrodes have been used. Partial pressure same, concentration different. Partial pressure same, concentration different. That means it is electrolytic concentration cell. It is electrolytic concentration cell involving hydrogen electrodes. Now for this cell to be working, what should be the criteria? See guys, the criteria is at anode, first of all, oxidation should take place. H2 should get converted into H positive. H2 whose pressure is P bar, right? It should get converted into 2 times H positive whose concentration is C1 molar plus 2 electrons. This has to be the reaction at anode. Similarly, what should be the reaction at cathode? 2 times H positive. 2 times H positive with the concentration C2 molar should be gaining 2 electrons and getting converted into H2 gas whose pressure is again P bar. So these are the two reactions which should be happening at anode and cathode respectively. Since electrons are balanced, right, the net reaction. When you add these reactions up, this particular term cancelled. So my net reaction is 2 times H positive with the concentration C2 gives 2 times H positive with the concentration C1. How many moles of electrons exchanged? 2. So N value is 2. First of all, this is my net reaction. If this is my net reaction, get the value of QC. QC is going to be concentration of H positive here, that is C1, C1 ka square, divided by C2 ka square. So C1 divided by C2 ka square. What is C1 basically? C1 is the concentration of H positive in the anodic container. So instead of C1, I'll write concentration of H positive in anode ka square. Concentration of H positive in anode divided by C2 is going to be concentration of H positive in cathode. Whole raised power 2. Whole raised power 2. Okay? Whole raised power 2. Whole raised power 2. Okay. Now guys, since QC value you got, N value you got. If I write the Nernst equation now, Nernst equation says that E cell is equal to E naught cell is 0 because it's a concentration cell minus 0.0591 divided by, what is the N value? N value here is 2 log of QC. QC is going to be concentration of H positive in anode divided by concentration of H positive in cathode whole raised power 2, right? Whole raised power 2. I would say this 2 and this 2 will get cancelled out. In short, 2 and 2 gets cancelled. When 2 and 2 gets cancelled out, so I would say your E cell is equal to minus 0.0591 minus 0.0591, or let me write here, E cell is equal to minus 0.0591 multiplied by log of A by B is log of A minus log of B. So it becomes log of H positives in anode minus log of H positives in cathode. Okay, I would say your E cell is equal. I'll just write 0.0591 minus log of H positive. Minus log of H positive becomes pH. So this is pH of anode. This minus I'm writing as such. This minus log of H positive of cathode, minus log becomes P. So this is pH of cathode here. So this becomes my general expression. To calculate EMF of the electrolytic concentration cell involving hydrogen electrodes, right? For its E cell to calculate, it becomes the general expression. E cell is equal to 0.0591 pH of anode minus pH of cathode. Now, for this particular cell to be working, I would say for its cell reactions to be spontaneous. I would say E cell value has to be greater than 0, right? When can be E cell greater than 0? When pH of anode should be greater than that of pH of cathode. So this is the condition for this particular cell to have its E cell positive. Therefore, its cell reactions eventually will be spontaneous. Yeah? I hope this is also clear to every one of you. Right? This was your electrolytic concentration cell involving hydrogen electrodes. Why is it important? Have a look. From here you'll understand. See guys, look carefully. Salt bridge, hydrogen electrode, right? Partial pressure same, concentration different. So it is electrolytic concentration cell involving hydrogen electrodes. And few minutes back only we saw its E cell is equal to 0.0591 multiplied by pH of anode minus pH of cathode. So we have to calculate pH of anode. In the anodic container, what do we have? H2SO4. In the anodic container, we have got H2SO4. In the anodic container. And this H2SO4 would have dissociated as 2 times H positive plus SO4 dinegative. So what was the concentration of H2SO4 taken in anodic container? 0.05 molar. This would have been 0, this would have been 0. Now when the H2SO4 will be completely dissociated, this would be 0. 1 mole gives 2. So 0.05 gives 2 into 0.05, which is 0.1 molar. So this is the concentration of H positive in the anodic container. I got the concentration of H positive in the anodic container. It is 0.1, meaning 10 raised power minus 1 molar. So pH of anode will be equal to minus log of H positive concentration in anode, right? The value comes out to be 1. I got the pH of anode. Now, talk about cathode. In the cathodic container, what do we have? In the cathodic container, we have got HCl, which would have dissociated as H positives plus Cl negatives. Concentration 10 raised power minus 3. Initially 0, 0. Now this is 0. This will be 10 raised power minus 3. This will be 10 raised power minus 3. So, concentration of H positive in the cathodic container is how much? 10 raised power minus 3 molar. If concentration of H positive in the cathodic container is 10 raised power minus 3 molar, so I would say pH of cathode will be simply equal to 3. Minus log of this, right? 3. So people, you got pH of anode as well as pH of cathode. So E cell is equal to 0.0591. pH of anode here is 1. pH of cathode here is 2, right? When you solve this, will this value come out to be positive or negative? This value will be coming out to be negative. And when E cell is equal to negative, I would say cell reactions will be non-spontaneous. Cell reactions will be non-spontaneous, right? Cell reactions would be non-spontaneous, which is something I was supposed to check. Nothing more than that, right? Am I clear? Am I clear, people? Am I clear? Can you solve this question on your own? pH of anode is given, right? Concentration of H positive in cathode is 1 molar. Partial pressure is same, concentration is different. So it is again electrolytic concentration cell involving hydrogen electrodes, right? And its E cell is nothing but 0.0591 pH of anode minus pH of cathode. Now, E cell is nothing but 0.2364 is equal to 0.0591 pH of anode is given to me as X minus what will be pH of cathode? Concentration of H positive in cathode is 1. So, concentration of H positive in cathode is 1 molar. Therefore, pH of cathode will be equal to minus log of H positive of cathode. So, minus log of 1 comes out to be 0. So, pH of cathode is 0, right? So, X value will be equal to 0.2364 divided by 0.0591. And this value after solving comes out to be 4. So, X value, which I was supposed to calculate as per the question, this is coming out to be 4. I believe this is also clear to everyone. Now guys, at the end of the concentration cells, there is one last concentration cell, which is what you call as electrode concentration cell. It is what you call as electrode concentration cell. Okay. What this electrode concentration cell is all about? I told you in the beginning itself, electrode concentration cell is the one in which concentration is kept same. Concentration is kept same, but partial pressure is kept different. Concentration same, partial pressure different. You can represent it like this. Platinum solid, H2 gas with a pressure of P1 bar, H positive, whose concentration, for example, is C molar, H positive, whose concentration is C molar, or H2 gas, whose partial pressure is P2 bar, and this is platinum solid. This is one way of representing it, or you can represent it like this as well. See, this is H positive with concentration C, H positive with concentration C. Instead of them, you can write only one H positive with a concentration C molar, right? No need to represent the salt bridge. It is already understood. So H2 with the partial pressure of P1, and this will be H2 with the partial pressure of P2, right? On this side, you are using platinum solid. On this side also, you are using platinum solid. Perfect. Any of the two ways you can represent these cells. Right, guys? Either represent it like this or you can represent it like this. The choice is all yours. If you look carefully, on both the sides, same electrodes are used. So concentration cell. Concentration of electrolytes is kept same. Partial pressure is kept different. Concentration same, partial pressure different. So which electrode, which cell it's going to be? Concentration same, partial pressure different. It is going to be your electrolytic electrode concentration cell. Now, for this electrode concentration cell to be working, what should happen? At anode, oxidation should take place. H2 should get converted into H positive. H2, whose pressure is P1, should get converted into 2H positive, whose concentration is C, plus 2 electrons. This has to be the reaction at anode. Similarly, reaction at cathode should be 2 times H positives, 2 times H positives with the concentration C molar plus 2 electrons gives H2 gas with the pressure of P2. Electrons are balanced, so add the two reactions. This term will get cancelled out. So it will be H2 with the pressure P1 gives H2 with pressure P2. N value here is 2. QC is going to be nothing but QC is going to be P2 divided by P1, right? E naught cell here is going to be 0 because it's a concentration cell. If E naught cell is equal to 0, then what is next? Use the Nernst equation. Use the Nernst equation. E cell is equal to E naught cell 0 minus 0.0591 divided by N value is 2 log of QC. QC is P2 divided by P1. So I would say your E cell is equal to multiply this minus with the log, you'll be getting something like this. Log of P2 by P1, you can write log of P1 by P2. Log of P1 by P2. Perfect. And for the cell reactions to be spontaneous, I would say for the cell reactions over here to be spontaneous. For the cell reactions to be spontaneous, I would say E cell should be greater than 0. When can be E cell greater than 0? When this term is greater than 0. When can be this term greater than 0? When P1 divided by P2 will be greater than 1, which is only possible if P1 is greater than P2. So what was P1 and what was P2? P1 was the partial pressure of the gas in the anode, and P2 was partial pressure of gas in the cathode. So I would say partial pressure of anode here should be greater than that of partial pressure of cathode, then only. Partial pressure of anode should be greater than that of partial pressure of cathode, then only E cell will come out be positive. And if E cell is positive, then only you can say that the cell reactions are spontaneous. Okay? So for this electrode concentration cell to be working like a normal galvanic cell, in which the moment of electrons has to be from anode to cathode, moment of current has to be from cathode to anode, I would say partial pressure of anode here should be greater than that of partial pressure of cathode when the electrodes are the hydrogen electrodes. I hope this is also clear to everyone. I hope this is clear to everyone. Okay? One question, people. One question. Look at it. Look at it properly. Look at it. Look at it. Look at it. Okay, till I solve the question, let me post a poll over here. Okay, you are supposed to give the answer in the poll, okay? I would want the honest opinion from everybody. Just a second. Sorry. Can you see the poll? Oh my God. 73% people are saying yes. See, if you want this chapter to be complete in this session itself, then it will exceed 12 hours. You won't be able to get the recording of this particular session afterwards. Okay? Perfect. Still, we have to solve this question. After that, we have to do one more topic also, if you want this chapter to be done in 2 parts also. Okay, let's first of all solve this particular question, and afterwards we'll decide whether to do this chapter in 2 parts or not. Let's first of all solve this question. My dear students, if you look this question carefully, this is your salt bridge, right? On the left side of the salt bridge, you've got hydrogen electrode. On the right side of the salt bridge, hydrogen electrode. Partial pressure 2 atm, partial pressure 1 atm. So different. Concentration 10 raised by -3, concentration 10 raised by -1. Concentration as well as partial pressure, both are different. Concentration as well as partial pressure, both are different, right? Concentration as well as partial pressure, both are different, people. So here you are not going to use any formula directly. You'll follow the general process. And what is the general process? You'll be first of all writing the reaction at anode. What is happening at anode? H2 giving H positive. So the reaction has to be H2 gas whose pressure is 2 atm, right? It gives 2 times H positive whose concentration is 10 raised power minus 3 molar plus 2 electrons. This is your reaction at anode. Similarly, reaction at cathode. This will be H positive giving H2. So the reaction has to be 2 times H positive with the concentration 10 raised power minus 1 molar plus 2 electrons gives H2 gas with a pressure of 1 atm. Perfect. Electrons are balanced, so add the two reactions. When you add the two reactions, 2 and 2 gets cancelled out. So it's going to be H2 gas whose pressure is 2 atm plus 2 times H positive whose concentration is 10 raised power minus 1 molar. It gives 2 times H positive whose concentration is 10 raised power minus 3 molar plus H2 gas whose pressure is 1 atm. This is your net reaction. So you can easily write the QC value, right? QC is going to be concentration of H positive 10 raised power minus 3 ka square, that is 10 raised power minus 6. Partial pressure here is 1 atm divided by partial pressure here is 2. Here the concentration is 10 raised power minus 1 ka square, 10 raised power minus 2. So it becomes 10 raised power minus 4 divided by 2. Or you can say it is 5 into 10 raised power minus 5. This is QC. Since it's a concentration cell, because same electrodes have been used, so E naught cell has to be 0. E naught cell has to be 0, right? E naught cell has to be 0. Okay. Now, Nernst equation, E cell has to be calculated is equal to E naught cell is 0 minus 0.0591, n value is 2 log of QC. QC is 5 into 10 raised power minus 5. Just the matter of calculation. Get the E cell value, right? Get the E cell value. Perfect. I hope this particular thing is clear, right? Now, my dear students, in the EMF part, there is one last topic. In the EMF part, there is one last topic that is asked. What is that? Thermodynamics of the cell. It's simple. It will not take more than 15 minutes. Thermodynamics of the cell. My dear students, you are asked 3 types of questions here. Sometimes you'll be asked to calculate delta G for the reaction. Sometimes you'll be asked to calculate entropy change during the reaction. Sometimes you'll be asked to calculate enthalpy change of the reaction. These are the 3 questions which will be asked. Calculate delta G for the reaction, calculate entropy change delta S for the reaction, calculate delta H for the reaction. Right? These are the 3 questions which will be asked. Now, how do we deal with these questions? You'll be given with a galvanic cell. You'll be given with a galvanic cell, right? You'll be asked to calculate delta G for the cell, delta S for the cell, or delta H for the cell. Now, first thing, my dear students, I'll be writing one equation over here. The equation is from the chapter Thermodynamics. Okay, you can remember this equation directly. dG is equal to VdP minus SdT. This equation is what you call as Maxwell's equation, and it is valid only for reversible processes. It is valid only for reversible processes. My dear students, if I write this equation at constant pressure, your dP has to be 0. So I would say dG is equal to minus SdT. dG is equal to minus SdT. Since we are talking about the cell reactions, and for the reactions we do not define G, for the reaction we define delta G. For the reactions we do not define entropy. We do not define entropy for the reaction. We define entropy change for the reaction. We defined entropy change for the reaction, right? For the cell reactions, for the reactions. For the reactions, we do not define G, Gibbs free energy. We define Gibbs free energy change for the reaction. Similarly, we do not define entropy of the reaction. We define entropy change of the reaction. So, I'll be replacing G with delta G. I'll be replacing S with delta S. So, in this particular equation only, I'll write D of, instead of G, I'll write delta G for the reaction is equal to minus times. Instead of S, I'll be writing delta S for the reaction multiplied by what? Multiplied by dt. Multiplied by dt. Perfect. Now guys, we are almost done. We are almost done in order to get the expression. See what the expression will be. See what the expression will be. I'll write d upon dt. I'll write d upon dt of delta G for the reaction is equal to minus delta S for the reaction. Okay. Delta G is equal to minus NF E cell. So minus outside, NF outside. So this becomes dE upon dt. And this is mentioned at constant pressure. At constant pressure is equal to minus delta S for the reaction. Perfect. So delta S for the reaction is calculated with this formula. NF dE divided by dt at constant pressure. This is the result with the help of which we calculate delta S for the cell. This is the expression with the help of which we calculate delta S for the cell. And this dE by dt is something which I call as temperature coefficient of the cell. dE upon dt at constant pressure. This is something which we call as temperature coefficient of the cell. Temperature coefficient of the cell, right? This is one of the results. Second result you already know. Delta G for the cell is nothing but minus NF E cell. This is something which we know already. Minus NF E cell. Now, if delta S we got, delta G we got, we can use the equation. Delta G is equal to delta H minus T delta S, right? We can use the equation. Delta G is equal to delta H minus T delta S. From this particular equation, we can calculate delta H, which is nothing but delta G plus T delta S. Since we are talking about the cell reactions, so this is delta G for the reaction, delta S for the reaction, delta H for the reaction, right? So, your delta H for the reaction is equal to delta G is minus NF E cell, delta S is NF temperature coefficient, dE divided by dt at constant pressure. At constant pressure, right? Multiplied by T. Multiplied by T. So, if you take certain things common here, let's say I'm taking minus NF common, so it becomes E cell. It becomes E cell minus dE divided by dt at constant pressure multiplied by T. Okay? If I take minus NF common, or let me not take minus NF common, let me only take NF common. If I take NF common, it becomes minus this and plus this, right? This is the expression with the help of which you can calculate delta H for the reaction. So, you got delta G for the reaction. You got delta G for the reaction whose units are going to be, if I talk about SI system, its units are going to be in joules. Delta S for the reaction, its units are going to be in joules per Kelvin as per SI system. And delta H is nothing. Its units are also going to be in joules only as per SI system. As per SI system, right? So, my dear students, three results you are going to remember here. First of all, how do we calculate delta G for the cell? How do we calculate delta S for the cell? And similarly, how do we calculate delta H for the cell? Perfect. One more thing is asked here. What is that in thermodynamics part? That is efficiency of the cell. Sometimes you are supposed to calculate efficiency of the cell. And let me tell you, efficiency of the cell is nothing but magnitude of delta G divided by magnitude of delta H multiplied by 100. Right? Sometimes you'll be asked a question on efficiency of the cell as well. And this is how you calculate efficiency of the cell. Calculate delta G, delta H will be given to you. Multiply that with 100, you'll be getting the cell efficiency. Okay? Before solving the question on this, one thing I would want to share with you. What is that? That is the variation of EMF with temperature. Variation of EMF with temperature. My dear students, we have got two types of cells. First cell is the one for which temperature coefficient is taken to be positive. Second cells are the ones for which temperature coefficient is taken to be negative. We have got two types of cells. The first cell for which temperature coefficient is positive. The second type of the cell for which temperature coefficient is negative. Right? Now, first of all, temperature coefficient positive means dE divided by dt for the cell at constant pressure. This is positive. Temperature coefficient negative means dE divided by dt for the cell at constant pressure. This is negative. Now, what happens to this particular cell whose temperature coefficient is positive? What happens to this cell on increasing the temperature? Similarly, what happens to this cell on increasing the temperature? What happens to their EMF? Will they increase or decrease? Will they increase or decrease? See guys, simple. If you increase the temperature, what will be the dt, change in temperature? If you increase the temperature of the cell, change in temperature, final temperature minus initial temperature will come out to be positive, right? Final minus initial will come out to be positive if you are increasing the temperature of the cell. See, dt is coming out to be positive. That means denominator is coming out to be positive. For this whole term to be positive, for this whole term, entire term to be positive, this dE should be positive as well, right? So I would say dE should be positive. dE should be positive. What does that mean? What does that mean? That means E2 should be greater than E1. So what it indicates? On increasing the temperature, what is happening to EMF? EMF of the cell increases. So EMF of the cell is directly proportional to temperature. But this is valid for only that particular cell whose temperature coefficient is taken to be positive. Remember this. Yeah? Right, people? Is it clear? Is it clear? Is it clear? So that particular cell whose temperature coefficient is positive, its EMF is directly proportional to temperature. On increasing the temperature, the cell EMF is going to increase. Look at the second case. Look at the second case. That particular cell whose temperature coefficient is negative. If you increase the temperature of this particular cell, what happens first of all? dt is equal to positive. dt is positive. But overall sign has to be negative. For the overall sign to be negative, dE has to be negative. dE has to be negative. What does that mean? dE can be negative only if E2 is less than E1. So, on increasing the temperature, what is happening to EMF? EMF is decreasing. So, I would say E cell is inversely proportional to temperature when it comes to that particular cell whose temperature coefficient will be negative. Whose temperature coefficient will be negative. So, EMF, this is how EMF varies with temperature. First, for that particular cell whose temperature coefficient is positive, then for that particular cell whose temperature coefficient is negative. Remember, it can be asked directly in the statement-based questions. Okay? In the statement-based questions, these might be asked. On increase the temperature, EMF of the cell will increase. Similarly, on increase the temperature, EMF of the cell will decrease. Basically, it depends on whether the temperature coefficient of the cell is taken to be positive or the temperature coefficient of the cell is negative. Okay? Let's try to solve one question on this so that you'll understand it. See guys, you are given with a cell. You are given with a cell reaction. N value here is 2. N value here is 2. What do we have to calculate? E cell is given. Temperature coefficient is given. Delta G, delta S, delta H. Simple. So first of all, delta G has to be equal to minus NF, E cell. Right? N value is 2. F value is 96500. Perfect. And E cell is given to me as per the question. 1.018. Since I have used all the parameters as per SI system, so the answer is going to be in joules as per SI system only. The first question is done. Second, delta S for the cell is equal to NF dE divided by dt. NF dE by dt at constant pressure. What is N? N value is 2. Faraday is constant, 96500. dE by dt, temperature coefficient. Temperature coefficient is given to me as minus 5 into 10 raised power minus 5 volt per Kelvin. All the parameters are used as per SI system. The answer is going to be as per SI system, joules per Kelvin. The last one, delta H for the cell is equal to NF. This is minus E cell plus dE divided by dt at constant pressure multiplied by T. So, N value is 2. Faraday's constant is 96500. 96500 minus E cell is given. At temperature 25 degrees centigrade, E cell is equal to 1.018 plus d by dt is given to me as minus 5 into 10 raised power minus 5. Temperature is given to me in degree centigrade, so make it in Kelvin. 298 Kelvin. Solve this, get the answer of delta H, that too in joules, because every parameter was used as per SI system only. Yes? So with this, your EMF part is clear. Now there is a second part, a smaller part of this chapter, which will take some 3 to 4 hours to complete, right? The major part of the chapter is done. So what do you want now? Do you want the chapter to be completed today only, in this session only? Or should I post recording of the part 2, not tomorrow, day after tomorrow, in the morning? Whatever is feasible for you. Well, I have created a poll here. 72% students want this chapter to be done in 2 parts. First part is 8 hours, which we are done with. Second part will be 4 hours, right? People have started to write good night, huh? See, 72% students are saying to complete it in 2 parts, huh? And 28% are saying poll is already there. Poll has been created, right? You can check it. You can check it. I'm creating a poll again, okay? I'm creating the poll again. Tell me, what do you want? And majority wins here, huh? I'll listen to the majority only. See, there's only point I can finish the chapter today only. The point is, a lot of people are texting me on Telegram saying that, see, on YouTube, if basically the live stream goes beyond 12 hours, that session you cannot see in the recorded format then. That session won't be there in the recorded format. Okay, anyways, I'm creating a poll here. Tell me what do you want? Just a second. I'm posting a poll. I want the genuine answer from you all. The poll has been created. Quickly. Selva Kumar, that is not in my hands. I cannot create the new stream. The stream is created from the backend team, and right now the backend team would be sleeping. I hope you get it. Guys, are you seeing the poll results? Hmm. So I'll go with majority here. I'll go with majority here. Let me show you the poll results. I hope you are able to see poll results. 69% are saying to do it in two parts, and 30% is saying to complete in one go. So I'm going with majority here. So what I'll be doing now, listen. Listen. Today was Monday. Now today is Tuesday, Wednesday. Wednesday, 9 a.m. I'll be posting its part 2, but I'll be posting this in recorded format. Okay, recorded format, and that will be almost for 4+ hours, and do complete that. And in that part 2, let me tell you, there will be topics like electrolysis, followed by products of electrolysis, followed by Faraday's laws of electrolysis, and then comes your conductance, followed by Kohl-Royce law and its application. Kohl-Royce law and its application. This is going to be the part 2, which I'll be posting on Wednesday. Okay. All right. I know some of you wanted to, cover it today only, but there are a lot of majorities asking like to do it in 2 parts. It's okay. No worries. Tomorrow only I'm posting the other one. You need not to worry, guys. And yes, there is one more thing I want to tell you. There is a topic called as batteries, right? There is a topic called as batteries here. Well, in batteries, you have to remember certain things. So for that, I'll be sharing a sheet with you on my Telegram. That 1-page sheet, you'll just have to remember about batteries. Nothing else you have to discuss about that. Okay? That batteries part will be done. I'll be sharing a sheet on my Telegram, Wassim Bhat Chemistry Official, which contains all the important points about the batteries, which is something you have to remember. There is no concept involved there. There are no concepts involved there. Okay? And next chapter will be either GOC or chemical equilibrium. And you can let me know in the comment section of this particular video, which chapter do you want the next. One thing I would want in the comment section, guys. So today it's day 20, right? Today it's day 20. And being consistent for 20 days, it is, trust me, not a joke. You're halfway done. Now, another half is just pending. You're halfway done. By December end, we'll be completing the entire syllabus here on YouTube itself. That too in the detailed manner. Okay? That too in the detailed manner. Perfect? Perfect. So on Wednesday, that means tomorrow, I'll be sharing at 9 a.m. exactly the part 2 of this particular chapter, which will be the electrolysis part and this particular part, right? PDF of this particular session, I'll be sharing the Telegram right after this particular, right? The session ends. And one thing I would want in the comment section of this particular video, what is that? That is electrochemistry done and dusted. Perfect. please share DPP today, please, sir. As if I never share the DPPs, the way you are begging for DPP. I don't know, like, why you're doing this. Perfect, guys. So I'm ending the session. I'll share the second part tomorrow at 9 a.m. Okay? Chalo. Take care. Take care, guys. God bless you all. Bye-bye. And I don't like these spammers, these nonsense spammers. Who are these? Who is the Srinath? Srinath, I'll have to block you at the end of the session. I'm really sorry, okay? You are nonsense. You will remain nonsense. Okay? Chalo. Chalo, guys, I'll see you in the next session and wait for this particular session. Tomorrow, 9 a.m., I'll share the second part of this particular chapter, which you guys are going to see. Well, guys, it's good only because the recording of the today's session will remain as such on YouTube itself. It's good only. Okay? Chalo. Take care, guys. Bye-bye.